for Science and Engineering, National Institute of Technology, Silchar. I am really privileged to have the pleasant task of welcoming the distinguished gathering for the 18th International Conference on Natural Language Processing, ICON 2021. The main conference is scheduled for 2 days and will be graced by the presence and presentation of different experts from various prestigious institutes from India and abroad. I am grateful to all the guests who graciously and readily accepted our invitation. We are eagerly looking forward to listen to our guest speakers. The main objective of the conference is to focus on both theory and applications in the broad areas of natural language processing. In the effort to fulfill the objectives of the conference, we hope that the presentations, discussions, and exchange of experiences will help generate ideas and solutions and enrich the knowledge about the use of natural language processing in the trending research areas. We fully appreciate all the honorable guests for finding time for this conference despite their busy schedule. We take this opportunity to thank Honorable Director of NIT Silchar, Professor Shivaji Bandyopadhyay Sir, Patron and Program Chair of ICON 2021, for his constant support and help, without which the conference would not have been possible. We welcome Honorable Director of NIT Silchar, Professor Shivaji Bandyopadhyay Sir, Professor Nalin Bihari Dev Chaudhary Sir, Dean, Research and Consultancy, Dr. Saroj Kumar Biswas Sir, HOD CSC Department, and Dr. Thaudan Doran Singh, Organizing Chair of ICON 2021. Now, we invite all the dignitaries to please come forward to the dais and occupy their distinguished chairs. We also welcome Professor A.K. Barbhunia, Dean Academics, to come to the dais. Now, we welcome Professor Rajiv Sangal from IIT Hyderabad, Professor Pushpak Bhattacharya from IIT Bombay, and Professor Deepti Mishra Sharma from IIT Hyderabad, who are joining us online in this inaugural function. We would like to felicitate our honored guest. So I request Dr. Ujjwala Barua Madam to kindly come forward and felicitate Honorable Director Sir of NIT Silchar, Professor Shivaji Bandyopadhyay. Thank you. I request Dr. Samir Borgohai Sir to kindly come forward and felicitate Professor Nalin Bihari Dev Chaudhary Sir, Registrar of NIT Silchar. Thank you. I request Dr. Pinky Roy Madam to kindly come forward and felicitate Professor A.K. Barpuya Sir, Dean Academics of NIT Silchar. Thank you. I request Dr. Arup Bhattacharya Sir to kindly come forward and felicitate Professor S. Boishro Sir, Dean, Research and Consultancy. Thank you. I request Dr. Sudhana Devi K. Madam to kindly come forward and felicitate Dr. Saroj Viswas, HOD CSC Department. Thank you. I request Dr. Partha Bakre Sir to kindly come forward and felicitate Dr. Chaudham Doran Singh, Organizing Chair or ICON 2021. Thank you. Light symbolizes knowledge, purity, and is the dispeller of the darkness. If you light a lamp for someone else, it will brighten your path and also it will brighten your path also. Now I request the dignitaries on the dais to come forward and light the lamp as we inaugurate the conference. Let's all stand. Thank you, everyone. Now, let us have a virtual tour of NIT Silchar. Now, I would like to request Honorable Director of NIT Silchar, Professor Shivaji Bandyopadhyay Sir, who is also Program Chair of ICON 2021, to come forward and speak a few words about ICON 2021.
Can we start? Okay, you start from there. Very good morning to all my distinguished friends who are online. Professor Sangal, Professor Pushpak Bhattacharya, Professor Dipti Mishra Sharma, other distinguished friends, my colleagues here who are present in the auditorium now. At the beginning of the ICON 2021 18th International Conference on Natural Language Processing, I would have wished to organize this in a hybrid mode so that at least those who are present at the NIT Silchar campus today, we have tried to arrange them following all the protocols, and our wishes for our online friends also, distinguished friends, to join us in the near future when the time permits. The ICON 2021 is organized by NLP Association of India, the association which organizes NLP activities all over the country. In the Department of Computer Science and Engineering, we have a Center of Excellence in Natural Language Processing, CNLP. So CNLP is also another co-organizer. The program is sponsored by DST SARV and Samsung Research. Next. So now we'll be felicitating our distinguished friends online. So advisory committee chair, Professor Rajiv Sangal, who is actually the man behind, along with Professor R.M.K. Sinha, who actually spearheaded, initiated the NLP activities in India. So Professor Rajiv Sangal, who is currently at IIIT Hyderabad. So we are felicitating him with an online Jhapi. And so Professor Sangal, in the near future, when you are in our campus, so we'll be sharing this same moment with you also. Then along with the Jhapi, we, in the state of Assam, we felicitate our guest with a gamosa and with a flower bouquet. Thank you, Professor Sangal, for guiding us all throughout our years.
Thank you. Thank you.
Next, we have the General Chair for ICON 2021, Professor Pushpak Bhattacharya of IIT Bombay. He was the past president of Association of for Computational Linguistics, ACL. We felicitate him with the traditional Jhapi, with gamosa and a flower bouquet. So Pushpak, please accept this, even if it is online.
Thank you.
Next, we have Professor Dipti Mishra Sharma as a computational linguist who has guided us and with her vast knowledge of various languages. So always guided us in different scenarios. From IIIT Hyderabad, again a Jhapi for Madam and the traditional gamosa and a flower bouquet. So thank you, Dipti ji, for being with us. Yeah.
Thank you so much. Yeah.
And along with Dr. Shobha, I am the program chair of ICON 2021. In fact, I had the privilege of being part of organizing ICON in 2017. So again, an additional level of Jhapi and gamosa are coming to me. Then with Dr. Shobha from AUKBC Research Center. So Shobha, one Jhapi and one gamosa and one flower bouquet to welcome you to this ICON 2021. We had a nice experience of working since the last, say, more than 20 years. Now, the program, the ICON 2021, say initially we thought of organizing, as I have said before, in an hybrid mode. And I wish that in near future, we'll be able to host all of you in the at NIT Silchar. So that traditionally, the main conference is of 2 days. That is currently it is the 17th and 18th of December 2021. Already the pre-conference events have already started yesterday. So we had nice set of tutorials. AI for Bharat initiative, safety and moderation AI in social media, conversational AI and neural machine translation for low resource languages. Now it is at this point I share with you, that is now the current trend, that is whatever the direction the NLP activities in India will go on, is basically the area of multilinguality and multi-modality. Because we have worked for so long in the text domain, so now it is the time for us, and the whole community is actually working in the area of speech processing. Traditionally, speech processing work was carried out by signal people, that is from the electrical science group. But what we see that in the computational linguistics community, the computational group also, they are more on the speech research side. And in this particular ICON 2021, we have made it a point that not only tutorials, workshops, but also in the main conference. Good set of papers, good set of contributions are there in the multi modality domain as well. And so besides the tutorials, we had workshops already started yesterday. Again, one is on conversational AI, and you can see that that is in the area of multimodality in the conversational AI, that is chatbots and the virtual agents, and the sentimentality appended with it. We had one tutorial and one workshop. So in the area of speech and music processing, we have also another workshop that started yesterday. And along with this multimodality and the multilinguality, obviously the language itself, the parsing and its application and with respect to Indian languages. Because no matter whatever levels of, say, the deep learning methods we use, whatever tools we use as a black box, but the language itself, so that's the root is in its grammar, the parsing, the syntax. So all these have been taken care of in yesterday's workshop. We had doctoral consortiums also, two nice presentations that happened yesterday. Then say I will come to the main conference descriptions later. So among the post-conference tutorials, again, speech-to-speech machine translation. This is a domain which at the national level, the whole country is actually working towards it. Then fake news and fact verification, that has become an important area. Then code mixing, because in a multilingual country like India, so people talk in, that is, every person actually knows more than one language, and while talking with other fellows, so this kind of code mixing in the general communication, in the dialogue area, that happens. And in fact, Assam is a nice test bed for a multilinguality and the multimodality in India. Several languages are spoken and several dialects also. So those who work in the speech domain and looking at its languages and the dialects, so coming to the and working in the state of Assam will be an interesting scenario for it. And then we have the graph deep learning for NLP, that is a tutorial. And so our students, many of them are, say, they have not been called back to the campus. Only the PhD and the master students are here. But we have invited all our students, and similarly, I invite all the students in other institutions as well, so that they can join the tutorials, because these are experiences of lifetime. We'll have another workshop, that is the continuation, natural language processing for digital humanities, which attracted the large number of submissions also. We had shared task on 2 areas where there were various participations. We have special sessions which will be held on 19th of December. One is application areas are interesting for legal, text and agriculture. Then interpretation, speech, articulatory dynamics. Again, you prosody and language in layers. So you can see that the thrust on speech processing from a language point of view that we have put in this year's icon. Tools and demos. So that is another session on 19th. Then in the main conference, I think the attraction for the main conference actually, along with the presenters, so lies in the keynote talks. So we have 4 keynote talks, and as we have been able to have the best of the people in this domain. So today, after this inaugural program, after some break, because the time zone integration, I think that is the most important part in today's world. That is when, because of online activity, so the mobility has increased, but in the sense that time zone management has to be done. So Professor Genavith will be talking. Then after lunch, Professor Philip Resnick from University of Maryland, USA, he will be there. Followed by that in the evening, we'll have Dr. Louis-Philippe Morency from CMU. And tomorrow, we'll have the talk from Professor Rada Mihalcea, University of Michigan, USA, who is currently the ACL president. So we are honored to have all of them as our keynote presenters. And we believe that those who are present physically in the campus, those who are present online in different institutions, they will be enjoying these keynote talks and interacting with the professors. The main conference was a multi-track event of 9 technical sessions, 3 parallel technical sessions each day, and 6 parallel technical sessions on day 2. We had a total number of 193 submissions and 81 papers got accepted. So acceptance rate is 41%. Something we can say on a bit hard side, but the quality of the presenters, because we had reviews, and in many cases we had more than 3 reviews of the papers as well. And out of the 81 accepted papers, 23 are from outside of India. And the countries include Germany, USA, UK, Japan, Korea, China, Czech Republic, the Netherlands, Sri Lanka, Hong Kong, Nepal. So we see that not only from the Asian subcontinent, Europe, as well as from the USA, we had good number of paper presenters. And all of them, that is all the 81 papers, the authors have will be presenting the paper. The proceedings will go to ACL anthology. That is what all the people who work in the area of the natural language processing or computational linguistics who aspire to have their papers included there. So it will include the main conference proceedings, workshop proceedings, shared task, and tools and demo. So today, after the inauguration and the keynote talk by Professor Joseph Van Genabit, we'll have in the second half from 2:30 to 6, we'll have technical sessions on machine translation, natural language text generation, speech and multimodality. Then tomorrow, the first half will start at 9 in the morning, 9 to 12. And we have sessions like machine learning in NLP, syntax and semantics, NLP applications. Then second half of 18th December, we have computational psycholinguistics, sentiment analysis, and emotion recognition. Then session 8 is on question answering, information extraction, information retrieval, and text mining. And session 9 is on language resources and evaluation. So there was no definite order among these organizing the technical sessions. It was basically based on the availability of the session chair of the paper presenter, because along with the keynotes, we have the presenters from different parts of the world. So their time zone we had to keep in mind so that people are not inconvenienced, not to present their paper in the middle of that is in the midnight or very early morning. With this, I wish to thank all of my distinguished friends who are online, those who are present at different parts of the world, the presenters, authors of ICON 2021. And before concluding, so I wish to share that is at the beginning, we shared a video of NIT Silchar campus. So it was not only a campus tour video, it was actually a dream that we shared with all of you. A dream that the world comes back to its normalcy when people can meet with each other, maybe maintaining some bit of social distancing, but again, actual level of interactions. Because as we say that in a conference, the breaks that we have, the tea break, the lunch break, and the dinner breaks, where people interact with each other and new ideas actually come in. So these we miss in an online program like this one. But I do wish that all the delegates who are present, all the participants who are present in different corners of the world, you take maximum advantage of the online presentation. And we'll be having a group also, that is online group of the authors and the paper presenters, so that in the future you communicate among yourselves, because communication is basically the key to take the world to the next level. With this, I wish thank you to all of you. Thank you.
Thank you, sir, for your enlightening words. Now, may I request Professor Rajiv Sangal from IIIT Hyderabad to speak a few words.
Thank you, Professor Shivaji. It was wonderful to see the video tour of NIT Silchar, and not just a tour. I think you said it. It conveyed a dream. It conveyed the feelings of an upcoming and a institution. I feel sorry that I've not been able to join physically, and hope that I'll sit there sometime. As mentioned, newer areas are coming in, multimodality, and in particular speech and language, speech and text, they are coming together, and not just coming together in research, but even at the level of delivery of technology. So people are looking forward to speech machine translation, for example. One question that I want to draw your attention to: how do we move forward in research? What innovations do we do? Should we just shoot in the dark, or we move with some understanding? Of course, our intuition also. And this is where it's important to realize that we have to move in a knowledge intensive way. We move forward with an understanding of what we know. And this is where linguistics and language understanding is so important. Sometimes in a hurry for doing things by machine learning alone using brute force, it works for some time, but it doesn't continue. It doesn't have longevity. And also it does not have satisfaction for the researcher. So we have to make use of our understanding, advance that understanding further through research, and use innovation when we are combining these multimodalities. More groups I know, they are coming in, and as the newer, younger groups come in, I think they need to understand that machine learning without domain knowledge, without the knowledge of the area, it will neither satisfying nor will it take us very far. And life is multidimensional, as the NIT Silchar video showed so well. And let us not make it unidimensional through machine learning by being agnostic. Sometimes the word agnostic is used, but agnostic should not mean no knowledge, not making use of any knowledge about language and also about specific languages. So I hope that our field will move forward with these newer challenges that have come in, and look forward to that journey. And once again, welcome to everybody to this conference. Thank you.
Thank you.
Thank you. Next, may I request Professor Pushpak Bhattacharya, sir, from IIT Bombay to speak a few words.
Good morning to everybody. Am I audible?
Yes, sir, you are audible.
Yeah. So it is indeed my great pleasure that the 18th edition of ICON is happening in 2021. And what better place than NIT Silchar in the northeast region of this country, where we know a great amount of diversity exists in terms of the linguistic landscape. And also people of Northeast are eager to join the mainstream natural language processing research and development. I myself have had experience of working on Northeast languages when we created the Indo-WordNet, different parts of Indo-WordNet being Northeast languages WordNet, Dravidian WordNet, and also WordNet of the Western region, apart from Hindi WordNet, which was the hub of all these. Now, in this 18th edition, as Professor Shivaji Bandyopadhyay described, there is a great diversity in terms of areas of NLP and in terms of representation from different parts of the world. So we were told that the acceptance ratio was 41% in the conference, which means ICON is quite selective. Also, out of these accepted papers, about 25% are from outside India, which is also a very happy state of affairs. The international character of ICON is on the increase, and I attribute it to one of the important factors, which is the availability of these papers indexed under ACL anthology, which is, of course, a very quality platform for obtaining information on recent research and development in natural language processing. Many of my very distinguished colleagues are in the conference, and we are grateful to them that they could find time to submit their research in this conference, and many of them are present in this particular inaugural session. Now, as the general chair of the conference, I'd like to thank all the participants, all the speakers, all the tutorial presenters, all the workshop organizers for making it possible to have dissemination of NLP ideas and NLP findings. The mode of the conference is hybrid, and in October, I attended a hybrid conference called AI/ML Systems in Bangalore. There was a huge screen in which paper presenters' slides and their appearances also were seen. Hybrid conference is going to be a new reality coming out of a new situation in the world caused by COVID-19. It has its pros and cons. The reach is much more expanded, though we miss the face-to-face personal interaction amongst ourselves. But of course, the situations would change, and we will be able to go back to pre-COVID situations, but online experiences will remain and continue. The importance of multilinguality and multimodality was emphasized by Professor Sangal. Professor Shivaji Bandyopadhyay also mentioned these two dimensions of current natural language processing research. Professor Sangal also mentioned the importance of insight into the task and into language phenomena, not only for the concerns of performance saturation and hitting a wall, but also because of the importance of the satisfaction that a researcher gains from such insights. They provide the energy to move forward. In our lab in natural language processing at IIT Bombay, we have a slogan: linguistics is the eye and computation is the body. The annotation of the data, the analysis of errors, the understanding of where we should give emphasis on, these are impossible without a deep insight into the task and language phenomena. This we have seen again and again, and I repeat, in data annotation and result analysis, linguistic insight is absolutely inevitable. To give you an example, take this situation of question answering. Now I have a sentence in front of me. Oh, what an interesting place Delhi is. Oh, what an interesting place Delhi is, the capital of India. Now, if the question is, what is the capital of India? The answer is Delhi. And which word is important here? Capital and Delhi. If it is a sentiment analysis situation and we ask, what is the polarity of this sentence? Positive, neutral, or negative? The sentiment is positive. What signals the fact that the sentiment is positive? The phrase, wonderful city. What a wonderful city Delhi is. Now see, for sentiment analysis, wonderful is the signaling word. For question answering, capital and Delhi are the signaling words. So you see, if you take a probabilistic point of view, the probability mass shifts from capital and Delhi to wonderful city. So for the task of sentiment analysis, the probability mass should be concentrated on wonderful. For question answering, the probability mass should be concentrated on capital. All right. So this is the play of the probability, its distribution decided by the data. And this is exploited in machine learning. But the fact that the phrase wonderful is important comes from linguistic insight. So these kind of concerns and these kind of understandings are enriching data-driven, probability-based, machine learning-based, but linguistically enriched natural language processing research. To this point of multilinguality and multimodality, I would also like to add multitasking. There are umpteen number of papers, many from our research too, which propose machine learning architectures, which at the same time do question answering and sentiment analysis, question answering and summarization, emotion analysis, sentiment analysis, and dialogue processing. So this is an example of multitasking apart from multilinguality and multimodality. Recently, in September, I was in CERN, Geneva, on invitation to discuss the future of artificial intelligence. The phrase AGI, Artificial General Intelligence, was mentioned again and again, which implies zero-shot learning and approximation and adaptation. An important insight which I draw your attention to is the fact that while machine learning systems work with a predefined loss function, human beings most probably don't. If we ask the doctors, did you know in your childhood that you would become a doctor? I think 80% of them would say no, we didn't know we would become a doctor. The goals sort of emerged as time passed, and we passed through many sub-goals to reach this current state of our life. So, an important difference between human intelligence and artificial intelligence is the ignorance of the objective function. Human beings most probably, at least not consciously, know the objective function that they have to optimize. This is an important difference and has a strong bearing on AGI, Artificial General Intelligence. It is important to have serendipity in AI, which data, machine learning, and linguistic insight affords. New directions keep emerging all the time. Surprises keep coming. Word embedding has taken the center stage. We did not anticipate in this, I think, 20 years before. So very exciting times are ahead. And the NLP researchers have become courageous, taking on more and more problems, encouraged by the data that comes forward. But it is important to give importance to linguistic insight, task insight, language insight. Linguistics is the I, computation is the body. Thank you very much.
Thank you, sir. Now, may I request Professor Shobha L. to speak a few words.
Good morning to everyone. Dr. Shivaji, Dr. Pushpak Bhattacharya, Dr. Deepti Mishra Sharma, and Dr. Rajiv Sangal. It's a honor that we could hold the Icon 18 at Silchar. In spite of having so much of problems that we are going through, the world is going through. And we could do that with lots of help from all of you in making it possible. And I welcome all the members, the participants, those who have submitted the papers. It was a very challenging experience that we had so many papers and people were working on reviews. Many people worked on reviews and the reviews came on time and we could finalize the results on time. We didn't have to make people wait for that. So it was a group effort that has made it to this day. So I thank everyone who worked day in and day out, making it a success now. So the coming days, we see the real part of ICON. And as Dr. Shivaji has mentioned, there are interesting talks, interesting paper presentations, and a lot of students and others are participating in it. With that few words, I would like to wish all the participants a good knowledge sharing as well as a good event. Thank you.
Thank you.
Thank you, madam. Now, may I request Professor Deepti Mishra Sharma, Hyderabad, to speak a few words.
Good morning, everyone. Thank you for giving me this opportunity to talk about NLP. I'm not getting into the details, but ICON. This is the 18th chapter of ICON, and we've been. Many of us have been going through this journey of having organizing ICON over the years in India, in different parts of India. It's very, very heartening to see the diversity of the areas which are represented in this ICON. I mean, we've been having it, but it's particularly more diverse because NLP in general is approaching now in the directions where more diverse research can be taken up. It's also very heartening to see the large number of, a representation of geographical regions which are here. So both these contribute towards a very, very rich knowledge sharing experience for people who are here. India itself is a multilingual country. In fact, it is a heaven for someone who wants to look at languages and their diversity. Diversity in India of language is in terms of not just large number of languages, but the number of families these languages come from, and the diverse linguistic properties that these languages have. So some of them are SVO, although by and large, a lot of them are SOV, but some are SVO. The diversity also ranges from highly analytical languages to highly, highly morphologically rich languages. And with all this diversity, a lot of commonalities exist in Indian languages. So that makes it a very, very interesting and very good source of learning for us to develop models for Indian languages. Multilinguality is something, multilingual learning is something which is, as Pushpak mentioned, is becoming more popular because one wants to cover more languages and languages which are lower, which have lower resources. So that is what one can exploit from the commonalities of that Indian languages have. At the same time, the diversity there also draws our attention to where there are limits to what we want to do and where we need to think differently. So, so that is something very unique. And for this, one point I would like to mention, in ICON, it has been kind of discussed and decided and also happening, is the regional ICONs. So the diversity that we see here of a large number of participation from, I mean, international participation is one aspect, and the other would be to go in the direction where we have more number of people participating from within India, from, institutes which are not so much into research, but people they are getting motivated to start working. And Reg Icons was an idea in that direction. It would be nice to have more languages represented in the papers that we see in the conference, because then more people from different regions, and not just within India, from outside India also, can come forward, and we can have more languages with lower resources, because that's something that people need to also work in the direction of. So I'm sure, I mean, we have had reg icons, and I'm sure icon can now start thinking more actively in the direction of having reg icons more regularly. With that, I thank you all and welcome all of you to this chapter of icon, which I'm sure is going to be a very, very interesting and enriching experience. Thank you.
Thank you, Madam. As we come to the close of our inaugural program, I invite the organizing chair of ICON Conference, Dr. Thardan Doran Singh, to deliver vote of thanks.
Respected dignitaries on the dais, guest faculty members, and my beloved student friends. It's a matter of pride for me that I'm proposing a vote of thanks for this inaugural function. I, on behalf of the organizing committee of the 18th International Conference on Natural Language Processing, ICON 2021, spread my most sincere thanks to one and all. I want to thank Honorable Director NIT Silchar Professor Sivaljiban Upadhyay, who gave his vital time from his busy schedule to grace this inaugural function. I want to thank all the speakers for doing their necessary work and sharing with us graceful opinion. Further, a big thanks to Natural Language Processing Association India, NLP for giving the opportunity to host this conference in the northeast part of India for the first time. And I would like to place my hearty thanks to the advisory committee chair, Professor Rajiv Sangal from IIT Hyderabad, General Chair Professor Pushpak Bhattacharya from IIT Bombay, Program Chairs Professor Sivaji Bandyopadhyay from NIT Silchar and Professor Shobha from AUKP Center, and all the area chairs, technical program committee members for their timely submission of reviews, volunteers and participants, because of whom we made this conference a successful event. I also want to thank all the NIT Silchar administrative officials, faculty members for their kind cooperation and support in the conference. We are fortunate to thank the dedicated and well-motivated team of our institute who are aware of their tasks and are very concerned about such events. I cannot give enough thanks to everyone for their participation and mobility to take on the accomplishment of this conference. Once again, I would like to state that we are glad to all the keynote speakers. We thank you for being with us. It has remained a pronounced pleasure. Have a great day ahead. Thank you.
Thank you, sir. Finally, this is an opportune time for us to declare the official opening of the conference ICON. And we wish all 2 fruitful days of interesting and beneficial program. With this, I once again welcome all of you. Thank you. Now it's time for high tea. Everyone is requested to move forward to have tea. We shall meet here at 11:30 a.m. for keynote talk. Thank you. Professor Joseph Van Genabit sir will be with us for the first keynote session. Thank you.
Will the link be the same?
The inaugural session will start again at 11:30. Thank you.
Will the link be the same, Shivaji?
Yes, sir.
Yes, sir. Link will be same, sir. Link will be same.
So please join in the same link. Okay, thank you. So now, notice all kind of experimentation that you can do now. Huh? Projector is not working.
Morning, guys. Can you hear me?
Yes, Professor.
Hi, how are you?
I'm doing good. How are you?
Great. Hello, good morning. Hello. How are you doing? How's it going? How many people are in Silchar and how many people do we have online?
So how many people online? Any statistics?
I can see 36 people online from
Yeah,
where.
I think
Hi,
36 at this
Joseph.
moment.
Deepti here.
Hi.
But
Good morning.
say after the inauguration, we put a small gap. So
Yeah.
from 11:30, your talk will start. So we can expect that more people will be there.
Oh, there were many more people in the inauguration. There were.
Yeah,
And
in
how
fact,
many
in the
people?
hall itself, auditorium, we had more than 30 people present here.
Yeah. And how many
So it
people
is
are in
truly
Silchar?
an hybrid nature.
Yeah. How many people are in Silchar? How many people are at NITS?
Yeah, so in the NIT campus, more than 1,000.
No, I
Because
mean for the conference.
for the conference, around 50 people.
Yeah.
Yeah, in the auditorium itself.
Fantastic. Yeah.
Yeah, so we have made it a point that those who are in the campus, so they assemble at the same point.
Shivaji, we would have come. In end of November, we were planning to book the tickets.
Yeah.
Then
But
came Omicron, and Omicron said, don't go, so we didn't come.
No, obviously, because we don't want to lose anyone because of Omicron. Na? So it is
No, we wouldn't have. I mean, nothing. I wouldn't, I'm sure. It's just that travel is not safe. So,
Yeah. So as long as we can avoid the travel, that is better. But I wish that in the next 3-4 months.
Also, I think this online mode is started to grow on us because now it's much more comfortable than traveling all the way.
YouTube live is going on with this.
Okay. Acha, so now I think because the YouTube is also on, so there is a live streaming from these WebEx. So we'll be joining in the same link, maybe 15 minutes after this, 11:14 it is now, Indian time.
Okay.
Okay, sir. Thank
Excellent.
you. Okay.
Okay, so
Hi, Doran.
hi,
Everything
Dr.
okay?
Joseph. We will be joining again at 11:30.
Great, good stuff.
Yes. Till then, we will have a tea break and resume.
Enjoy your tea.
Okay.
Okay. Kaya ba? Kaya join to rekin. Si join to rekin. Kaya no. Okay. Yari sim to. Okay. Ako ba sim to tawid na ikisi. Mani mani to siya. Si yari si.
Correct, sir.
Yes. Yeah, no rest. Now we can who are the participants now we can see. We have 53 participants. I think we can start up keynote talk now.
Yes, already. More than 10 minutes.
Yes. Well, mic to help us to talk. Okay. Professor Joseph, we are sorry, we are a little late here. We want to start a keynote talk. I just want to introduce our keynote speaker, Professor Joseph Van Genavit. Professor Joseph Van Genavit is one of the scientific directors of the DFKI, the German Research Center for Artificial Intelligence, where he has the multilingual language technology MLT lab. He's full professor at the Zerland University, where he holds the chair of translation-oriented language technologies. He was the founding director of CNGL, the Center for Next Generation Localization, now ADAPT, director of the National Center for Language Technology, NCLT, and an associate professor, senior lecturer, and lecturer in the School of Computing at Dublin City University, DCU, Ireland. He worked as a postdoctoral researcher at IMS, the University of Stuttgart, Germany, and obtained an MA and a PhD from the University of Essex, UK. His first degree is in electronic engineering and English from RWTH Aachen, Germany. Professor Joseph, please start the talk.
Good morning, everybody. And it's a great honor for me to be here. Thank you very much for the invitation, especially as we're collaborating with Professor Sivaji at NITS and his team, his natural language processing team under the SPARK program of the Indian government. And I had the great pleasure to visit Silchar and NITS in 2019 for 3 weeks' time, and that was really, really wonderful. So I'll go and grab the screen and start my talk. Can you see the screen?
Yes, yes.
Yeah, excellent. Gonna make it large. And yeah. So good morning, everybody, again. And the title of my talk is Self-Supervision and Phrases in Neural Machine Translation. And in rough outline, I'd like to talk a little bit about where I'm coming from. This is the DFKI, the German Research Center for Artificial Intelligence, our group at DFKI, and then really focus on some of the machine translation work that we do in language technologies. And one is self-supervised neural machine translation with my colleagues Dana, Christina, Dietrich, and the other one is, so this is focusing more on data and good use of data and architectures that support good use of data. And the second one is more on the architecture of one of the workhorses of modern language technologies, and this is transformers in neural machine translation. And the idea here is to try to learn source phrase representations for transformers. Some of you might remember statistical machine translation, in particular phrase-based statistical machine translation, and using phrases in phrase-based statistical machine translation made a big jump in quality. So can we do something similar in neural machine translation as well, in particular in the transformer architecture? Okay, so let me tell you a little bit about DFKI. It's a research center that's focusing on artificial intelligence. It's actually a company, but a company that works as a non-for-profit. It's owned by many other companies, or it's not really owned, it's like a shareholdership, I should say. And a lot of these companies are German companies, like you see the car companies here, but also international companies like Google, Microsoft, etc. It's quite diverse in that we have a lot of software, hardware companies in the fold, but also things like big companies that do agriculture, agricultural science, agricultural industrial products, and they use a lot of AI. We are very international. Our colleagues at the moment come from more than 65 countries across the world, and you can see a distribution over here. So, of course, we're all based in Germany, but it's a very, very highly diverse and international team. We're about 1,000 people at a couple of sites in Germany, and I think it's one of the oldest centers in artificial intelligence, and it covers almost every aspect of AI. And you can see here like educational technologies, intelligent networks, but also things like interactive textiles. So these are smart clothes that have some computing power. They can do some stuff for you, do displays, react to the environment, etc. Marine perception, machine learning. And it's probably fair to say that almost all of the research teams, or labs as we call them, also do some language technology stuff, because language is really, really important in AI. But there's two labs that really just focus on language technologies, and that's the Speech and Language Technology Lab in Berlin and our Multilinguality and Language Technology Lab in Saarbrücken. We work closely together. The idea for DFKI is really to connect basic research with applications. That's really the idea. And in order to be able to do this, a lot of the projects that we do have a very strong industry focus, but a lot of the projects are also really basic research, because we're trying to connect the two. Yeah, and I mentioned this already, like, the two labs that really focus on language technologies, and I'm going to concentrate on this one here, multilinguality and language technology. So in my lab, we have 4 groups. There's question answering, information extraction group. There's the machine translation group, which is headed by Christina. The talking robots group, and the data and resources group. The data and resources group is there because most of our approaches are machine learning based, not all of them, but most of them. And of course, we need data and resources in order to be able to do this. And here I'm just going to focus on machine translation and some of the aspects of the work that the machine translation group does. One of the things that we're doing in the area of translation that is not research is we're working for the European Commission to collect data across Europe and all the EC member states, and we pre-process that data and then pass it on to the EC and feed the neural machine translation systems of the EC with this. But not just those, but also speech data, vision data, etc. And we do this across Europe. So we've created a structure called the ELRC, the European Language Resource Coordination, that is rooted in all of the member states, and it's gathering, collecting data, and passing it on to the EC, but also making it available to anybody. So if the data is unencumbered by any IP, then it goes into the EU's open data portal, and it's meant to help grow a budding language technology in Europe, but also beyond Europe. The data is available to everybody on the planet. And so far, we've collected more than 200 billion words from all of the member states. And I think around 80% of this, or maybe even 90%, is publicly available at the Open Data Forum and at a number of other fora. We also worked for the German government. In the second half of 2000, Germany was the president of the EU Council. You may know that in the EC, the president rotates every 6 months. In the second half of 2020 was Germany, and then it was followed by Portugal. And I can't remember who holds the presidency at the moment. And usually the holder companies, the countries, they do sort of like, some nice technology that they offer to the world. And in Germany, this was a machine translation system, the EU Council Presidency Translator, which we at DFKI led, and we collaborated with a German company, DeepL, and a company from Riga, Tilde over here, and of course the EC, to provide machine translation between all of the 24 official EU languages. And to date, the system has translated more than 200 million words. It's still online, but it doesn't have sort of like the computational power anymore that it had in the period in the second half of 2022. It was used a lot. Okay, some of the research that we're doing, this is just machine translation, and I won't go into this into any detail, but you see some of the basic science work that we do, and you see the conferences like NLP, ACL, NACL, ICHCAI, etc. These are from last year. And I can leave this in the slides. So the first thing that I would like to concentrate on is self-supervised neural machine translation. It's a string of 3 papers. The original idea is this paper over here, self-supervised neural machine translation. And then we developed it a bit further. We investigated the curriculum learning that is automatically induced by these systems. And then more recently, this year, we integrated some techniques from unsupervised machine translation with self-supervised machine translation. There's many similarities between them, as I hope to explain. The original idea for self-supervised neural machine translation is Christina's, and Dana, one of our, at the time, master students, made it all work in her MSc thesis. She's now working on her PhD. Okay, so what's the background? You all know there's quite a few languages on the planet. Here you see a screenshot of the languages of tweets in Europe a couple of years ago, and you can see there's there's a big mix in many European languages, but not just European languages. There's also Afrikaans, Swahili, Thai, and etc. I'm sure Hindi is in there somewhere, and of course you're used to the situation. It's the same in India. India has more than 20 official languages and many more really large languages in the country, and of course no single human being can ever master all of these languages. Completely impossible. So can machine translation help? With these 7,000, actually, our colleagues in linguistics estimate that there's about 7,000 living languages on the planet at the moment. So there's no hope that any one of us could master them. So can machine translation help? It looks promising because recently you've probably heard that there's been quite a lot of talk about a human parity of machine translation. And here you can see the results from a few years ago, actually, from the WMT 2019. This is English-German machine translation. Of course, this is richly resourced. There's a lot of training data, a lot of experience. And what you can see here is the human ranking, the leaderboard. And everywhere where it's gray, you go from first place to second place to third place to fourth place, fifth place, etc. Some of these are shared because although there are differences between the systems, the differences are not statistically significant. And as machine translation, neural machine translation got so good over the last couple of years, for some time the organizers of WMT have smuggled in a human professional translation, masqueraded as machine translation, which is also ranked by the human assessors. And in 2019, I think some of the systems, some of the machine translation systems in the human ranking outperformed the human professional translation. Of course, there's a big debate about whether this really means human parity, and we could do a lecture on this in its entirety. But anyways, I think what the takeaway from this particular slide is that if there's enough training data for a particular language pair, machine translation can get pretty good and might help us with this problem, like coping with 7,000 languages across the planet. But unfortunately, it's not. There's a spanner in the works. It's not that easy. We have two problems. One of the problems is a problem of scale. If we want to have machine translation between any of the 7,000 languages on the planet, that means we need about 50 million direct machine translation systems, and we need about 14,000 if we use a single pivot, for these machine translation systems. So that's a problem of scale. But that maybe could be solved. But there is in various ways. But there is a more fundamental problem, and it's not just scale. But most modern machine translation is, of course, machine learning based, and it's not just any kind of machine learning; it's supervised machine learning. So what we use in machine translation is parallel data, pairs of target and source sentences, or source and target sentences, and many of them, ideally like 1 million, or I don't know, maybe 10 million, 20 million, 30 million, or some, like the more the better, if it's good data and clean data. And then we estimate machine translation using statistics, as in the old statistical machine translation data, or we model that statistics by using neural networks. But the important point here is that we need these parallel data, and that's a very, very strong supervision signal. And of course, the problem is that data is not available for most of the languages on the planet, and that means for most of these systems. At a reasonable guess, we have data for maybe around 100 to maybe 200 of the world's languages, and you can work out the mathematics, that for the vast majority of these possible direct machine translation systems, we simply don't have the data. So that's a big problem, and of course it motivates strong motivation for searching for possible solutions addressing this problem. And there are many of them. There's pivot translation. I mentioned this already before. There are massively multilingual machine translation systems. There is like few-shot learning and so on. So many possibilities. But two of the major approaches that have been developed to address this in a different way are unsupervised machine translation and self-supervised machine translation. Unsupervised machine translation was developed by our colleagues in the Basque Country and at Facebook, and some of the people here in this team, like Mikel Artesh, is now also is now part Facebook, and then our own approach, self-supervised machine translation or self-supervised neural machine translation, which we developed at DFKI. So let me just very, very briefly outline unsupervised machine translation, and just to sort of like contrast it with the way we do it. So it's motivated by the lack of parallel data. It uses monolingual data only in the two languages. All this should be L1 and L2. That's a mistake in the slide. So two languages, like monolingual data in the two languages. And then usually these systems start as follows. They, induce word embeddings from this language and from the other one, and you get two spaces, and they align those two spaces, like minimizing distances, usually a linear mapping. And then from these two aligned spaces, they induce a bilingual word-based translation dictionary. And then they use this bilingual word-based translation dictionary in order to bootstrap a statistical machine translation, a neural machine translation system, actually in some papers mixes of the two, and then they start translating using, for example, very, very strong target language models, using very smart back translation, and then sort of like generating additional artificial bytext data to learn from. They bootstrap themselves, and this is very, very successful. So what we do in self-supervised neural machine translation is slightly different. It's also motivated by the lack of parallel data. But instead of looking at parallel data, we look at comparable data. So not parallel, but comparable. And comparable data is data where the data is not translations of each other, but texts in two languages about the same topic. This might be, I don't know, a football match, I don't know, Wikipedia entry of a country, etc. So these are not translations of each other, but they're about the same topic. And because they are about the same topic, they may contain similar sentences, and even sentences that are close enough that they could be used, if you find them, they could be used as translations of each other and then used to train a neural machine translation system. And one big source of such comparable data is the Wikipedia, because the Wikipedia is available in many languages and they're usually not translations of each other. And an example is, for example, the webpage for India. Here you see the German webpage, here you see the UK, no, this is the English one. This is the English webpage for India. This is the German one for India. The English webpage is, about 50 pages, 80 pages. The German is about half the size. And it's about the same topic. And if you look really, really closely, you can see that sometimes you find sentences like this one. It is the 7th largest country by area. This is India. And in German, of course, German is always a bit longer, a bit more roundabout. Hinsichtlich der Landesfläche ist Indien das flächenmäßig siebtgrößte Land der Erde. So you find these nuggets in here, but the problem is, of course, finding them and learning from this. And this is what self-supervised neural machine translation does. Okay, and in addition, there's also one thing that's very, very attractive about Wikipedia, and these are these language links. So this is again the webpage from India. It's the English webpage, and you can see the entries on India in Wikipedia pages of 266 languages altogether. Kind of like actually more languages, so including those guys here. And so you see this is a potential source of training data. And you might want to use these links in order, once you have found a particular article, you find articles on the same topic in all of these languages. So this is a rich a treasure trove potentially of useful data for machine translation. So the research question is, how can we now build systems that find their own supervision signal in comparable data? And self-supervision is maybe a key to this. You're probably familiar with self-supervised learning in terms of learning where the data brings its own supervision signal. And these systems usually have an auxiliary task. And this auxiliary task is just a stepping stone towards what you're really interested in. And that's your primary task. So they have an auxiliary task and a primary task. So an example of this would be like, an autoencoder, for example, where you put some data in, you kind of like have a bottleneck here, like a neural network where the dimensionality is reduced compared to this one over here. And then from this representation here, you try to reconstruct the original data. And so it's self-supervised. Like, the supervision signal comes with the data. You don't have to do anything. You're just trying to predict what you fed in. And this prediction task is the auxiliary task, but what you're really interested in is this latent space. Maybe you want to use them as embeddings or something like this, or as a knowledge representation or something like that. So this would be the primary task, this would be the auxiliary task. And you're all very familiar with with the word embeddings, for example, the static word embeddings developed by Tomasz Mikolov, where the auxiliary task is just simple language modeling. And the primary task is really the embeddings that you're interested in, these guys over here. Okay. We do something similar, but it's a little bit different in the sense that we have to find, in our data, it's not obvious, what should we predict, and we have to find this. So it's a more complicated version of this. Like here, we always know, like given the previous two words and the next two words, we predict the one in the middle, or given the word in the middle, we try to predict the previous two ones or the following two ones. So we know exactly, we can hardwire this into the structure of the problem. Over here, we can hardwire it into the structure of the problem. We know that from this one, we want to predict this fella here, no problem. But of course, in self-supervised neural machine translation, we don't know. We have to find the sentence pair. So it's a bit more complicated than this, but it's a similar idea in terms of auxiliary task and primary task that we're interested in. And I come to this. So some of the work that led to this was, of course, work in machine translation that looked at what people call the context vector over here. So this is an encoder-decoder neural machine translation system, and the encoder encodes your input, the decoder decodes it, and it does the decoding based on this context vector that, in an RNN-based neural machine translation system, encodes all the knowledge that the system has learned about the source sentence. And now what people did, quite some time ago, it was actually Christina and a few other people, is they trained bilingual systems. So where you have you train translation between two languages in both directions at the same time. And then they observed these representations here, these context representations across the different languages. And they observed that they actually converge in embedding space. So this is a two-dimensional representation of embedding spaces of sentences in English, German, Netherlands, I think Romanian, Italian. There's always these 5 languages. And all of these sentences, these different colors encode a proposition, the same proposition in these different languages. So here you can see same proposition, like by proposition I mean the same sentence, but translated into the different languages, And this is coded by the color. So these guys here, those guys. And you can see that they always cluster together in this multilingual space. That actually, the meanings of these sentences, is the same, but, they're in different languages, but they cluster together. And that was done in this paper over here. That actually comes from a paper that's a little bit later. And that's sort of like one of the ideas that informs self-supervised neural machine translation, or I should say this observation informs self-supervised neural machine translation. And of course, like, in what comes below, we use transformer architectures, but I'm going to use RNN-based machine translation presentations in the presentation, because conceptually it's sometimes a little bit easier to see what goes on. Okay, so how can we make the system find its supervision signal in the data? So the basic idea is to enable a single system to jointly learn to translate and to find and extract parallel data from comparable data. And this is done by a single system, by a single multilingual NMT system that does this from scratch in a loop and online. So in kind of like a virtuous loop. And here's the loop. And the loop consists of NMT training and parallel sentence extraction. So this is our auxiliary task, the parallel sentence extraction. And once we found these parallel sentences, we train the NMT system, but the NMT system helps us to find these parallel sentences. So it's a virtuous loop. So this is our auxiliary task, and this is our primary task, because we're really interested in developing good neural machine translation systems. Okay. So let me show how this happens. So the starting place can be, and often is in our case, like in unsupervised neural machine translation, we just take the data, let's say in English and French, and we compute word embeddings, and then we just align these word embeddings to induce an initial bilingual word translation dictionary. Actually, these are word embeddings, static word embeddings, where the same words in the different languages are close in the embedding space, really. So that's one way of doing it. In practice, we usually don't do it like that. In practice, we just start training a bilingual neural machine translation system, like a bilingual self-supervised neural machine translation system, and that automatically does this step here. But if you don't want to do that, you could do it this way as well. If you have enough data or like sufficient amounts of comparable data, you can just train it from scratch. You can skip this step, and you'll get this out, for free, as it were. And this is then how the system works. And, this is kind of like an RNN-based neural machine translation system. So let me talk you through this. So we have our inputs. So there's a Chinese sentence and an English sentence. And, from the word embedding, we get, this sequence here for this sentence, this sequence here for that sentence. And it goes into this. And then we got, this is here, these are then the context vectors. This is the output of the encoder that's handed over to the decoder. And then what we do is we have some scoring. We look at these vectors, at these outputs, but also at those outputs, the word embeddings and the sentence embeddings. And then we look at them, and if they are close, then we use the sentence pair for training. So you see these are the word embeddings, and these guys here, the sentence embeddings. So if they're close, we can include them in a batch. If they're not close, we discard the pair, and we keep searching. So we start with the first sentence of the first document and compare it with all the other sentences of the second document. If they're close, we keep them. If they're not close, we discard them. And once we've filled a batch, we train the neural machine translation system, which is the system here. It's all part of the same system. So you can see the loop going like this. And training the system, makes the system better at discriminating between similar sentences and dissimilar sentences at the word embedding level, but also at the sentence embedding level, at the context vector level, as it were, in a neural machine translation system. So you can see that this works in a virtuous loop. And that's what you can, the loop is sort of like indicated in this graphic over here. It's one and the same system. It's working online. It's not the case that we do sort of like a pre-processing step, run through the data, select all these sentences and stuff like this. It's really just it's part of the evolving neural machine translation system. And the auxiliary task, like learning to discriminate between sentences, helps us train, and training improves that auxiliary task. But at the end of the day, we're just really interested in coming up with a good neural machine translation system. So we use two sources of information. We use the word embeddings, so we just sum over the word embeddings, or for input sentences, and we sum over the hidden states of the RNN or encoder outputs in the transformer to have our sentence representations. And then what we do is we have a similarity score, so we just compare a sentence pair, a potential sentence pair, using these scores with a similarity score. Simple cosine similarity doesn't work because in n-dimensional space, the too many things that clump and cluster together. So we use the margin-based score from Atesh and Schwenk, that sort of like downweights sentences that are really, really close, that have many, many close neighbors in embedding space over here. And with that, you get it to work. So penalized sentences scoring a high cosine similarity with many, many sentences. And then we filter. So the method is actually parameter free. So we don't use a threshold or anything like this. And what enables us to do this parameter free is that we compare source to target with target to source. All the pairs here, all the pairs there, we intersect them. Okay. And then we do the same thing for the word embedding based representations and for the sentence representations, where the sentence representations, of course, are already based on the contextualized embeddings, from the transformer or from the RNN-based system. And we use the intersections of the intersections. Actually, a few variants of this, but mainly the intersections of the intersections. And that's what makes the method parameter free. So to give you some experiment results, so we use the Wikipedia English-French for the initial experiments. The comparable part of these Wikipedia is about 12 million sentence pairs in English and about 8 million in French. So you can see that these are subsets of the total Wikipedias of English and French. And the validation and test sets are the news test 2012 and news test 2014. And this is to compare it with what our colleagues do in an unsupervised neural machine translation. Here's some of the results. So you can see the actual experiments are done on transformers. Here's the scoring method. Here we use simple cosine. Here we use the margin-based scores. And here you can see different combinations of using, the scores for the word embeddings and the scores for the contextualized embeddings. Here we also only using the word embeddings, but not the contextualized embedding. Here's some filtering. We also ran some experiments with thresholds, but these are threshold free, where we just use intersections of intersections. And here you can see the results. So for English to French, around 29 bleu scores, and this should be English to German, and that's about 27. No, it's the other direction, and this is about 27 bleu scores. So these are quite respectable results, and they compare well. with our colleagues. So here you can see unsupervised neural machine translation at the time of publication of this paper, the best results that were achieved on the same test sets. Of course, our colleagues in unsupervised neural machine translation use much larger data sets because there's these are just monolingual data. And compared to that, the data sets that we use, the comparable data sets are smaller. At the time, we were a little bit better than unsupervised neural machine translation, and also even at the time, kind of like on a par with combinations of unsupervised neural machine translation with statistical machine translation. They're very sophisticated ways of combining the two that were presented in these papers. But that didn't last long, and more recent work on unsupervised neural machine translation has pushed the boundary. In some of our later papers, we show that using methods from unsupervised neural machine translation in self-supervised neural machine translation gets you results in that quality rank as well. So how does self-supervised neural machine translation learn what it learns? And just be brief to have a little bit of time for the phrases. It turns out that it self-induces curriculum learning. So normally curriculum learning is externally imposed. You as a designer, you design a curriculum. You go from simple to complicated or complicated to simple or something like this. This self-induces curriculum learning. It's naturally evolving. And unlike most curricula, is not externally imposed. There are three curricula that we look at. There's a denoising curriculum, accuracy, similarity curriculum of increasing closeness to the final task. Remember that we have an auxiliary task and a final task, and complexity curriculum of increasing complexity. And I show you just some results over here. You see recall and precision over here. This is the denoising curriculum, and you can see that fairly soon. The systems get up to high precision and high accuracy. And this is broken down in terms of the different types of embeddings that we use. Here's the word embeddings, here's the contextualized embeddings. And what you can see here, if we had enough time, is that initially the word embeddings do most of the work. And the contextualized embeddings, because the systems are not trained, are pretty abysmal. But then they sort of like learn quickly and they catch up very, very quickly. This is the curriculum of increasing closeness to the final task. If you measure the average similarity between the sentence pairs that we extracted, that actually extracted, you can see that initially they're quite noisy and it sort of like jumps around a little bit and then it stabilizes. And if you're wondering why these similarity measures are higher than 1, this is because of the margin-based similarity measure that we use, that I introduced earlier on. And then finally, in terms of curriculum, you could use many things here. We use the Gunning-Fox index. The Gunning-Fox index is an index of the text, of the complexity of text, and it maps it to years of schooling. So first grader, second grader, 12th grader, 16th grader. And you can see that initially the system learns on text that is similar to sort of like a final year high school student. And then it learns and goes up to text complexity at sort of like, I don't know, a final year undergraduate student, an entry level MSc student, and this is sort of like, a bit of fun if you like. Okay, so this was self-supervised neural machine translation, and it's joint training it's a single system. It does this online in a loop, joint training of machine translation and finding parallel data in comparable data, and it does this online in a loop. It's learning to translate and finding its own supervision signal, and it has a self-induced curriculum of different dimensions. Okay. All right, and we use it in low resource NMT, in domain adaptation, corpus cleaning, and last year Christina had a project with Facebook on this because they were interested in the technology. Okay, so let me switch gears now and so far go into the other part of the talk, and this is on transformer technologies. I'm trying to improve the transformer architecture to see whether it's possible to make it even better. And this is based on this paper with Hong Fei, one of our PhD students, and our colleagues in China, Dei, Kui Hu, and my colleague at DFKI, Jing Yi. So transformers are, I guess, it's pretty fair to say that they are the workhorses of much of modern natural language processing. You can find them in neural machine translation, in the big language models, BERT, GPT, etc. And one of the big differences is, of course, like the slogan is like, attention is all you need. And one of the big differences between transformers and RNN or LSTM-based systems is that if you look at long distance dependencies in an RNN-based system, that actually spans potentially many computation steps. So if this thing here is impacted by that guy here, you have to go all the way back. In other words, the information that's in here has to propagate, through this long line to get to here, to be effective, to be used in order to do this. And in self-attention, cross-attention, that's no longer the case. If here's an example of self-attention, for example. So this it can be related to animal directly. So the distance between any of these guys and themselves is just one. It's linear. Okay, so there's so in some sense these guys should be very good at long distance modeling, non-local dependencies, long distance dependencies and long test sequences. So that's the intuition, kind of like. And of course, like, this is much easier to parallelize than this. This is inherently sequential, and it's very hard to parallelize. And you can't really do it, but you can approximate it. But this is easy. This is designed for parallelization and fast training, etc. But surprisingly, it turns out that transformers are not actually that great at modeling long-distance dependencies. So there's work by Tang et al. So he's or she's one of the PhD students, or one of the students of Rico Zenrich's team. And if you compare transformers with RNN LSTMs and like sophisticated RNNs and LSTMs, like many layers, etc., transformers don't do any better. They're actually sometimes even outperformed on long-distance dependencies by these guys. And the thing that really seems to count for transformers is actually the number of heads in multi-headed attention. It is crucial for transformer performance over long distances. And they use subject-verb agreement to test this. And that was part of the motivation for us, when we looked at phrases. And should we try modeling phrases, like, in phrase-based statistical machine translation? Should we try to do something like this in transformers? And can this help, making results even better? Because it made a huge difference in phrase-based statistical machine translation. So if you remember, for example, the secret sauce of phrase-based statistical machine translation is alignments. Here you can see the alignment points between two sentences. Shall we still do something in the evening? And the German translation, sollen wir abends noch was unternehmen? You can see these black points. These are the alignment points. And from these alignments, you can induce word translations. So shall translates into sollen, we into wir. You can see the languages are very similar. And you can also look at consecutive alignments. These two words are aligned to those two words and nothing else, in this table here. So you can form a block that maybe shall we can be translated into sollen wir. Or like, still do something, translated into noch etwas unternehmen, as a block. And if you do this, if you extract these translation blocks, bilingual blocks, these phrases, then the quality of statistical machine translation really jumps. And and you use these blocks in translation. So sometimes you translate individual words, and sometimes you use these blocks. You take some input, you chop it up into all possible, chops, if you like, and then you look into your database. Do I have translations for those? And and you use those translations, and often they're longer chunks. These phrases. So, would it help to do this in a transformer as well? And would it in particular help in improving transformers' ability to model non-local dependencies? And non-local dependencies are important in each and every language. So it's two research questions. How do we improve the ability of the transformer in long-distance dependency capturing? And there's a problem, of course. Kind of like if we model phrases directly in transformers, it's just going to blow the vocabulary. Because the vocabulary size of these phrases is exponential, And we can't do that, because this wouldn't fit into our GPUs and, the softmax, everything would blow up. There's only limited vocabulary with neural machine translation. That's all the motivation for things like subword representations, like byte pair encodings, etc. So a naive implementation of phrases and transformers, no, doesn't cut it. So how do we do this? How can we come up with a smart way of implementing phrases and transformers? And once we've come up with a smart way of modeling this, how can we utilize this? And does it actually help? Okay, so this is the problem. As I said, we can't do it naively. We can't just use a large phrase table because of the huge vocabulary size in neural machine translation. That's not a problem, by the way, in statistical machine translation, but in neural machine translation it is. So the solution that we came up with is that we're generating these phrase representations from the corresponding token representations on the fly, and we call this the attentive phrase representation generation mechanism. And it works like this. So we take a token sequence, we chunk it into blocks, and we summarize over each block. We just use min or max pooling, and then we have attention over word and phrase representations in the encoder. We also allow the decoder to see these phrases, in addition to the normal stuff that you find in the transformer. And so we come up with a system that's completely end-to-end trainable using backprop. And yeah, we investigate translation performance and the long distance or non-local dependencies. So how do we do this in practice? We just chop up sentences into blocks of 8 words. It's that crude, very, very crude. And we do this because you always want to pack things into tensors in neural approaches, because that makes it fast and efficient, etc. If the sentences are short, we use this formula here to come up with some optimal decomposition. And if we use this, we also pad, of course. We also run experiments using parse trees and fitting them into these chops of 8 or for shorter sentences, these blocks over here. Okay, so in here you can see an example. So here's the parse tree. And here's how we fit this, because this is a short sentence, into things, into chops of 3, which is the optimal for this length sentences over here. And we show you experiments where we use parse trees and we would just do the chopping, like, without the parse trees. So here's a little bit of technical background. So we do this in the encoder, okay? And given some sequence of tokens, remember these would be 8, blocks of 8. We get their embeddings or their hidden representations, like in some transformer layers, etc. And then we summarize over these guys. That's this function here, the glance function. We look at them at a glance, and this just stands for mean pooling or max pooling. So we run different experiments. So we have a summary representation, of this sequence of token. And then what we do is we take that summary representation over this one here, and we take each of the original ones, we concatenate the 2 vectors, and when we have a simple feed-forward neural network with one nonlinearity in order to compute a score for each word with respect to the summary representation. And you have 2 weight matrices, so some learning can happen over here. So this is kind of like a cheap way of doing attention. We want to do this fast and really, really cheap. Okay, and then from those weights over here, we get probabilities, because we take those weights and we use softmax to compute probabilities. And then the final representation of this 8 token phrase is just the weighted sum of the individual representations with those probabilities, that we learned from these scores here using softmax. You see that? And of course, if you look at this closely, that's kind of like a version of attention. So to compute these blocks, we use a fast and efficient version of this. Okay. And then from the decoder side, we allow the decoder to look at the phrase representations in the encoder using a version of transparent attention, where each decoder layer has access to a weighted version of all the encoder phrase representations. And this is similar to Babna et al. If you're familiar with that. So it's kind of like an attention over the encoder layers, if you like. Okay. Right, so in terms of architecture, it looks as follows. So here's a single encoder layer. Here's our input. From the input, we compute the attentive phrase representation. And then this here allows every word in the input to look at the phrases. So this is attention of each and every word at the phrase representations. And so the phrases, we bake in context from these phrases into the words. And then we do normal self-attention as in the transformer, the feed forward, and we didn't write the skip connections and the normalizations here, just to keep it simple. So each of the encoder blocks look like this. Even each of the decoder blocks looks like that. So we start with just the normal self-attention. This is masked self-attention. So, the fella is not allowed to look at the right, because it would just copy. It's just masked self-attention, just the normal masked self-attention. And then we have the attentive combination. So each of the words then are able to look at each of these guys, from each of the encoder layers. And that's the transparent attentive phrase representations. And then, and we bake this into the representations of each individual word. And then we have cross attention, just the normal cross attention, where this layer here is allowed to look at the top layer encoder representation of the transformer, and then the usual feed forward. Okay, so you see that, all the phrases in this architecture, they're ghosts. They don't exist. They don't exist actually as, as the sequence of word, but just as embeddings. And that's why we, the whole thing doesn't explode, and, we do this on the fly, and we avoid that vocabulary explosion. And here's some results, on German English and English French. These are to compare with Vaswani et al. So the transformer base, gets these results on English German and English French, and with the phrase representations, with our phrase representations, we can improve by about a bleu score. And interestingly, the method also scales to transformer big, which is like bigger embeddings and everything, and you get similar performance increases. And this is really cool because a lot of these methods, usually a lot of these augmentation or enhancement methods work if you have small data sizes, but then or small architectures, and they don't scale to big ones. And here are some ablation studies. You can see, like, if you kick out some of the like the attention and the transparent attention, you get different results. That's the transformer base. But what's interesting here is that when we use the linguistically informed parse trees, that is actually very, very similar to just doing brutal chunking. So it's a little bit better. But this is also interesting because for many languages or language pairs, you might not have parsers or good parsers. So you can do the brutal chunking yourself, and you probably get similar results compared to really fine-grained and nice linguistic analysis. And here you can see, like, in terms of sentence length, that's the normal transformer, and this is the transformer with the phrases. That's the transformer big, and that's the transformer big with the phrases. You can see the improvements, and they increase with sentence length. Of course, that's an artifact of bleu, with longer sentences. If the sentences are good, you get higher bleu scores. But what's important here is the differences between these systems. And then finally, in terms of these tests that come from Rico Senrich's team, these are subject-verb-object agreement, where there's not subject-verb. Yeah, subject-verb agreement, where there's a lot of linguistic material between the subject and the verb in terms of relative clauses and stuff like this. And you can see here that, with the phrases, that's the yellow one, and this one here, the performance is always better than the baseline. So yes, you get better translation quality, and you get better treatment of non-local dependencies or non-local phenomena in natural language with these phrases. Okay, so now I'm at the end of my presentation. I hope I haven't gone over time too much. I talked a little bit about self-supervised neural machine translation, an architecture that does online a learning of both finding and supervision signal in comparable data and translation at the same time. And I talked a little bit about learning source phrase representations, like trying to improve the transformer architecture, in particular for neural machine translation, but it might be applicable to some other things as well. Any questions?
Yeah. Thank you, Professor Joseph. Okay, the stage is now open for questions. So those who are present online, they can mention their question in the chat box.
Some echo is coming.
Yeah. Okay, I think those who are present in the auditorium. So,
Professor, can you hear
you
me?
can. Yeah.
Hello, Professor. Am I audible? Okay. So I'm Michael Singh from NIT Silchar. My question would be like, in a self-supervised neural machine translation, as the comparable data is the key. So what would be the role of the proximity of candidate parallel sentences in the performance of a self-supervised neural machine translation?
Sanai, could you repeat? There was a lot of echo. I found it hard to understand. If you just briefly try to repeat.
You can type the question in the chat box.
Or maybe you can ask a question in the chat.
Okay. Hello.
So big echo somewhere.
Dr. Joseph, Michael has a question.
Yeah.
So bring this here. It's okay, sir. So, in a self-supervised neural machine translation, comparable data is crucial. So, what is the role? What is the role of the proximity of the candidate parallel sentences in the comparable data in the performance of the self-supervision?
Good question. Actually, in theory, it doesn't need comparable data. It can just use parallel data. Not parallel data, sorry. It can just use monolingual data. It's just that computationally, comparing everything with everything else is practically infeasible. But theoretically, it will also find, if you just give it parallel data, like not comparable, like, like the Wikipedia links or anything like this, it will just go through all the data, compare everything with everything else, and find things that are close, initially from the word embeddings or something like this, and then start learning and training and getting better. So in terms of an abstract theoretical approach, the comparable data is not crucial. It is crucial in order to make it computationally feasible, to constrain the search space. That let's say you have like 100 million sentences here, 100 million sentences in the other language there, you would have 100 million times 100 million comparisons. That's like, very, very tough. And that's why we use comparable data, topic aligned data, just to make it computationally feasible. But it's a practical thing,
From my side.
My question is, you said that in the transformer, yes, you said that in the transformer model, we need to improve. We can encode different words, different phrases instead of words. So my question is how to encode different phrases like noun phrases, verb phrases in different ways so that encoder can learn easily, and also decoder part, how can it decode differently noun phrases and verb phrases? Am I clear, sir?
Yeah, thank you for the question. So at the moment, we don't use anything special. So we just chunk the input every 8 words if it's long enough. So first chunk 8 words, then second chunk 8 words, then third chunk 8 words. And we back off to something smaller if the sentence length is not so long, using that flexible formula, if you like. We don't do anything special about noun phrases or verb phrases or anything like this. And when we use the parse trees, we also we parse, but we just fit them into these 8 token slots. And from our results, we can see that it gets a little bit better, although it's not statistically significant. So I think your question is still an open research question. Would it be worthwhile to encode noun phrases differently from verb phrases to make the transformer be able to learn better from these 2 different guys?
Said about only blue score evaluation, and I have seen that in blue score evaluation still there is some phrases, but it gives good score, but in human evaluation it is not good. And also I have seen that some sentences the human evaluation is good, but blue score is not efficiently provide that much. So how can we context how can we handle those problems? Am I clear, sir?
Yeah, you're clear. And it's, again, a really good question. So we only use automatic evaluation in this because human evaluation, unfortunately, is time-consuming and costly. But you're right. Like, ideally, it would be better to also carry out human evaluation. We also carry out an evaluation on these long-distance dependencies, these subject-verb agreements, but you're right. This is also completely automatic, because what we do is we just let our system force decode the results, the good results and the bad results, and then we just use the higher decoding scores as an indication of what the system would have found. And that's the same as was done in the original experiments in Rico Semrich's group. Again, so it's a trick. So you can do this fully automatically. And yeah, but you're absolutely right. Like a full human evaluation would always be good. Yeah.
Okay, Professor Joseph, there is a question from in the chat box saying that this is the question from Musica Supriya. And her question is, Professor, can self-supervised NMT be applied on low-resource languages? If so, what can be the minimum size of monolingual data? So that's the first question.
Yeah, thank you again for the question. All very good questions. And you're right. So self-supervised neural machine translation has been applied to really low resource settings. Like French English is not a low resource setting, but it becomes difficult, and it's struggling with the same problems as unsupervised neural machine translations. So if the languages are pretty close, and that initial induction of the word-based translation dictionaries from having the word embedding spaces and aligning these spaces, if that works well, then usually unsupervised neural machine translation works well, and self-supervised neural machine translation also works well. But if you have distant languages where, like, you don't have any anchor points for automatically aligning these word embedding spaces in this language and in that language, like numerals, for example. They're often used as anchor points, a little bit of extra information. If there's the number 5 in this sentence here and the number 5 in that sentence, then yeah, that's cool. And, maybe I can align these numbers in the embedding spaces. That's cool. But if you don't have that information, then it's very, very difficult for these methods, and they often don't really perform very, very well. There's another problem. If you have truly low resources, you actually have to go through this, like, word embedding alignment. If you have not much data, the word embeddings themselves are not going to be very good. You need actually quite a bit of data in order, monolingual data, to compute good word embeddings. And if you don't have much data, the word embeddings, because you've seen the word only like 3 times or something like this, you won't get good word embeddings from that. And then a third theoretical problem is that in most of the embedding space alignment methods, we assume a linear transform between the spaces. But that may not be how languages are, or like, how best to bridge differences between very, very distant languages. So it's still an open problem. Very good question.
Chat box. Okay. Professor Joseph, there is one more question from Radhika Selvamani. She sent this message asking that has the self-supervised learning applied for translating ancient text to contemporary text in the same language?
No, very good question again. Thank you for the question. So we haven't done that yet. You could try. You could use this for dialect translation, like, between an old version of the language and a modern version of the language. Or many languages are pluricentric. I believe Hindi is pluricentric as well. Like, there are many strong dialects of Hindi, and they have also some difference in writing, I believe. I'm not quite sure, but that's true. For example, for German, there are a number of versions of German. There's Austrian German, there's Swiss German, there's the German spoken in Germany, and there are differences between them. So you could use these unsupervised or self-supervised methods to translate between them. Or English. There's so many. English is very strongly pluricentric. So we have the UK English, we have American English, Australian English, Indian English, many Englishes in the world, and they're really different. But they're part of the same language family. So yeah, and there has been work using unsupervised approaches to translate between different versions of the same language. But if I'm right, it might be that the idea that you have, translating between an old version of the language and the new version of the language. If you have this if you have data in those, that might be a new application. So good luck if you try.
Oh, okay. So I'm repeating the question, Professor Joseph. Okay. So the question is, this is the question from Thanmozi, and is saying that, hello, Professor. This is a general question. We see that neural network learn a lot of linguistic information themselves. You even saw that in WMT 2019, NMT performed well than human. So what is going to be the future of linguists and linguistic studies?
Yeah. Very important question. I think it's still an open question whether neural machine translation has achieved human parity, because in 2019, it turned out that half of the test data, I think there were about 2,000 sentences test data, about 1,000 sentences in the source language that were supposed, I think was English-German translation or the other way around. Half those sentences were actually already translated. And that has an effect, because sentences that are already translated are tend to be a little bit easier in terms of like lexical variation, not quite as varied, etc. So it's easier for machine translation. And a colleague of ours, Antonio Toral, at Groningen University in the Netherlands, he did a very good study of some of the claims of human parity of neural machine translation. And he showed that if you only look at source data that was originally authored in the source language and not already translated into the source language, then actually it turns out that the human translation is still a bit better. Now, the more recent evaluations in WMT have tried to factor this in, so that the test data is only the source, is only originally authored data, and still, like the neural machine translation is up there with the best human translation, but it still makes mistakes, and I think that in the future, maybe forever, we will need really good human translators, really good human linguists, because the systems do make mistakes. Often they make very subtle mistakes. You know, they might forget to translate a negation. They might forget to translate, I don't know, a small relative clause, but which is really crucial in a long 80-word sentence or something like this. And the work of the human translation professional will be to look at the output of machine translation systems, to identify these mistakes, to correct them, and then to guarantee the correctness, to vouchsafe the quality and correctness of the data. It's more like a notary. And of course, like this is only the case for those language pairs where we have a lot of training data. For most language pairs on the planet, we don't have enough training data, and the quality results achieved also by neural machine translation is nowhere near what you can achieve for like I don't know, English French or English Chinese or English German or something like this. And their human translation, even from scratch, sometimes is very, very, very important. Also, if you look at translation of novels, poetry, etc., then there's some first work in neural machine translation on addressing this, again by Antonio Toral, by the way, our colleague. But I think human translation will be important in the future, and also human linguistics, the study of language. But of course, we should compare it with what neural networks learn about language, and that'll be interesting. And this is what the neural network learns. It's feature and representation learning. Is that in any way similar to our abstract theoretical categories that we use in linguistics, or are there interesting differences? And maybe the two can learn from each other. Will be interesting.
Okay, Professor Joseph, Sanai has a question.
Okay.
Hi, Sanai.
It was a nice talk, Professor Joseph. Thank you for your talk. And I have one question. In the transform model, in your opinion, with the alignment installation compared to the learning the phrase alignment jointly, what is your opinion of the performance between them? Alignment installation and the learning the phrase alignment jointly in the transform model. And will this approach will be applicable in the low resource setting also?
Can you briefly repeat the first part of the question? It was a little bit distorted again. If you can just briefly.
Hello.
Yeah.
In
yeah.
your opinion,
Mhm.
in the transform model, we have alignment initialization, and with that compared to the jointly training the phrase alignment. So, what is your opinion on that? And will these approaches will be applicable in the
Yeah,
low
yeah.
resource setting?
Yeah. Good question. Thank you. And so I think one thing that I have to highlight more is what we have done in our work is only sources on the only phrases on the source side. Yeah. So we're not learning phrase pairs. We only have phrases on the source side, but there are no phrases in the target in the decoder. The only thing that we do in the decoder is we allow the decoder to look back at the phrases that we compute in the source side. So in that sense, it's really different from phrase-based statistical machine translation, where we actually have phrase pairs. So source side and target side, and they're aligned, they're linked using the alignments. And what your question is it would be really maybe interesting further work. Can we come up with a model integrated into the transformer that actually uses something like phrase pairs? Where you have a source side and a target side. At the moment, we only do phrases on the source side. And we allow the decoder to look back at those phrases in making its decisions, but it's not phrase pairs. Very good question. This is open research.
Okay, so Professor Joseph, we had a very question answering session. I just want to share you something what you did 2 years ago when you came down to NIT Silchar.
What is the current status
Yes.
of those trees?
Yes.
So you shared those photos.
Professor Joseph?
I think, Joseph, you identify the trees. So they have grown older.
Thank you very much. That's wonderful. Yeah. I think they look in better shape than me.
So those
Wonderful.
trees are going to bloom maybe very soon.
That's wonderful. Thank you
So
very much.
we'll send a snapshot of these to you also separately.
Thank you.
And to all those who are present online also, that is whenever a guest arrives in the campus. So we plant a tree, that is the guest plants a tree and they bloom and making the campus like the nice green one. And maybe some other photos. So Doran?
Yes. I'll be opening. So, okay.
And Joseph, I think you remember this is one of the beautiful places in the campus. And this has been completely newly built.
That's fantastic. It's a lovely boathouse.
What was that experience?
It's really nice. I hope we can try it again in person. was wonderful. Thank you.
Professor,
He has already given. Okay. Okay. Thank you, Professor Joseph, and we wish you back, that is to our campus sometime next year. That is when the situation normalizes. And thank you for the insightful talk.
And
So
thank you.
we are closing now.
Yep.
I think from 2:30 Indian time. So we'll be back again.
Professor, we have the machine translation session after the lunch break. Please join us.
Yep.
In the same WebEx, Cisco WebEx link.
Great. Thank you very much. And thank you to
Okay,
all the
Professor.
questions. And I wish you a good conference and
Take
a
a
very
break.
successful conference.
Badal sir. Badal sir.
Yes, yes.
Are you
Hello.
using computer or mobile?
I will use laptop. I'm just checking the link.
Your voice is clear.
1 minute, 1 minute. Actually, I'm joining from the laptop now. Hello, Naresh sir.
Yes, sir.
Yes, yes. This is the link for that first session.
Yes, yes. This is for session 1. So your audio is clear, your video is clear.
Okay, okay, fine. Thank you. Hey,
We just announce 3 more minutes.
স্টার্ট করছি ভয়েস ভয়েস আপনার ল্যাপটপ থেকে এটা তো অসুবিধা নেই তাই তো
ঠিক আছে
ঠিক আছে
একটু সময়ের মধ্যে
হ্যাঁ 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 ঠিক আছে
we will
হ্যাঁ হ্যাঁ
hello sir Prasudev sir.
Hello, namaskar.
hello sir how are you sir
All good, all good. So we're waiting for it.
yes okay
Okay. Who is Pinky Roy?
Pinky Roy madam is she is from the NIT Silchar.
Oh, okay, okay.
She is joining from one of the control room.
Great.
NIT Silchar host. She is joining there.
Fantastic.
Okay.
This is session 1 now.
Yes, WebEx is session 1.
Vasudev sir is in session 2 actually.
That's right. So how do I go to session 2?
Google Meet link. You might
We have shared a link for Google Meet link.
I don't think so.
Okay, in that case, I will share you once more, sir.
Okay, please.
Please
Yeah.
wait.
Thank you. Yeah. Okay. Then I'll quit from here. I'll join from there.
Yes.
Okay. Thank you.
yes
Dorian sir, proceed with
Yes.
session 1.
Okay, just a minute. That she's calling. Joined. Okay. Okay, so we are going to start the first technical session 1, machine translation track. This session will be shared by Dr. Partha Pakre from NIT Silchar and co-chaired by Dr. Badal Soni from NIT Silchar. So now I want to hand over the session to Dr. Partha Pakre and Dr. Badal Soni. Please proceed.
Okay, thank you, Dr. Doran sir. So now the first session is technical session 1, which will be the machine translation topic on the machine translation. So I welcome you all the participants as well as the respected faculty members and researchers. So in this session, so there are four short paper and 8 long papers there, as you know. So total you will get for 13 minutes for the short paper, 10 paper for your presentation, 3 minutes for your question answering session, and the long paper for 18 minutes, 15 minutes for your presentation, and 3 minutes for the question answering session. So now this session will start. So first paper is constant decoding for technical term retention in English Hindi machine translation. So presenter is Martin Vastar. So please welcome. So and please start your presentation.
Thank you. So I will start sharing. Can you see my screen? Can you see the screen or not? Do you hear
Yes,
me?
it is visible.
Yeah? Okay.
Okay.
Thank you. So, hi, my name is Martin Vastel, and today I would like to present constraint decoding for technical term retention in English and Hindi MT. And this is the project which I did with my colleagues Niyati Bafna and Andrzej Boya. So, first of all, what is the motivation behind this project? So imagine that you have some technical terms that you don't want to translate. The reason why you don't want to translate them is that the equivalent may not exist in the target language, or it is not like the common usage of the word. For example, you can have the sentence, you may now install these Python libraries, and you didn't want to translate it as you may now install the snake-like room of books. I'm really sorry, I can't speak Hindi, so I don't read the translations. The resulting Hindi sentence should be fluent and grammatical. Problem statement is that we have some source sentence S, and we want to keep some target output T. Keep the certain words in S as they are. And which words do we retain? The assumption is that we know this. Situation to situation, and we wouldn't want to retain the model for each situation. Is to provide some kind of signal to the model and hope that he will obey, or it will obey the signal. How did we prepare the data set? We selected the data set, identified the English source words that should be retained in the Hindi target, and introduced these English words in the Hindi target without disturbing the meaning of the sentence. Target sentence should be fluent. And there comes one question: how should we, which verbs should we switch or not? It's not really straightforward. What we did is that we saw that there are many transliterations in the target Hindi, for example, names, cities, numerals, etc. For example, Chola dynasty. And these verb pairs are aligned with each other, vertical. So we can run some word alignment algorithm to find such. So for each alignment, we need to check whether word pair is transliterated or not. We used some basic transliteration tool, which gave us a phonetic output, which is not conventional spelling. It roughly contains the right consonants. We used normalized edit distance to make the decision and replace the transition with the. We used Giza++ to find the alignments. And first of all, we find a word, transliterated to English, then calculated the normalized distance between source and translation. And then if the threshold goes smaller than threshold, then we replace. Larger than the threshold, then we did not. Threshold did we use? We just use some number based on the held-out data set, which precision and we used English in the data set, which contains roughly 200 sentences for the training set. For the test set, it was 10,000, and which I will talk later. And as you can see, the most code switch were Hindi, Islam, Muslim. It was code switch. It had on average 1.9 code switch per head. We tried two different approaches. The first one is an approach where we don't know anything, and we train the model on our parallel corpora. We didn't give model any other information, and we expect the model to guess which words we would like to retain, which obviously doesn't really work great. Approach is approach where we injected this information during runtime, and we did it by using special tags ref and closing graph, which indicated start and end of code switch. I think that this model should generalize better, since and there's some example of the preprocessing. So as you can see, transformers are ref tags around the word transformers. For the model, we have the usual transformer models with hyperparameters as the Google WMT German English, and we have used Marian framework to train the models. We have trained the models up until the blast card didn't improve on the validation. You can see the blast scores on validation set are quite comparable. So they perform roughly the same. We wanted to assess this using automatic evaluation if the output and fluent, and if the words were retained. To this, we created two data sets. The first one contained unseen sentences, which may contain the keywords that the model has seen. Also, for example, the model could see word African closing graph, but it couldn't see the whole sentence. Test set was a set which contains keywords which did not see during the training. So the model could see the camera in Hindi, but never could see the ref camera closing graph. This is the true use case, which would also introduce the tort metric, something which we call tort metric, which is a metric which precision and recall of the written. As you can see, the tagged model is better in all metrics. For the unseen dataset, it's not really a surprise, since the baseline model doesn't know which words to retain. For the blast scores, you can see the baseline model is slightly better on the seen dataset and on the node. Adding these ref tags. And we also tried manual evaluation, where we had source, where we asked the user if text or the baseline translation was better, and we gave the user the source text and the recording of the reason why we gave the recording of the translation is that our natural way of teaching, and the second reason was words, since the tag model were naturally output more English words, so the user could guess which model is baseline and which word, which output is from the tagged and which one is from the baseline. As you can see on the scene test set, the models are quite comparable. Tagged model is slightly better on the number of English words, which means same number of English words, and the same set of English words means the English words were same. And for the unseen test, baseline model was better on the same set of English words and the number of English words. Overall, they are quite comparable on both seen and sim tested for the manual evaluation. So that's all. Thank you for your attention and feel free to ask any questions.
Yes, from the participant, any questions?
Thank you for the nice presentation. My question is that you have tagged that noun word, mainly proper noun, named entity, right? Proper noun. So my question is how you have tagged that multi-word. There are many proper nouns are there. So you have tagged both source and target, or in single side English?
We always used only one word. So, for example, if there would be multiple words, for example, if we would Chola dynasty, then there would be ref, Chola, ending ref, dynasty, ending ref. So we didn't handle the multi-word.
So you have used tag in both source and target.
Yeah. Yes.
Okay. It's okay.
Okay. Any questions? Any more question? Okay, so if there is no question, so I have only one question, Martin. So what is that the dataset size, parallel corpus?
The dataset size is 250,000 sentences.
Okay, and you only evaluated with that blue score. Is there any other score taken care?
No, we just used TORP metric, which is just precision and recall, and then the manual evaluation.
Okay. Okay, thank you, Martin. Nice presentation. Thank you.
Thank you.
Okay, so next presentation, next paper is name entity factor transformer for proper noun translations. So any authors in this paper? Huh? No name is there. So.
So you can ask the others to post their
Okay. Now,
such that you can easily.
Okay. So please present your work.
Can you see my screen?
Yes.
Thank
Yes.
you. Okay, so hello everyone. It's good to see you all here. My name is Koichi Takai. I'm working at KDDI Research Incorporated. And I also a doctoral student at Nara Institute of Science and Technology, Japan. Title of my presentation is named Entity Factor Transformer for Proper Noun Translation. In this presentation, I want to talk about this translation and dropping of proper nouns, and also these reduce the quality of machine translation. I'll be talking research background. As drastic advance in natural language processing, machine translation system is becoming a realistic tool. However, there are remaining problems for practical usage. One of them is out of vocabulary and also impact to social implementation. When we go to foreign country, important words should be accurately translated, such as landmark, restaurant, product name, and souvenir. In Japanese to English translation task, proper noun translation is important. Do you know Angry Games in Japan? This title is modified and the Japanese title is Red Hairs Ann. An example like this proper noun is translated as shown in blue and red words. Japanese people hope to translate accurately, but actually its result is a little wrong. This problem is one of out of vocabulary. For the problem of proper noun translation, there are two major approaches. The first approach is contrasting to handcrafted bilingual corpus or dictionary. This is able to for accurate translation and it contributes to social improvements. However, it is high cost of building the dictionary and collecting bilingual corpus. Secondly, we can use subword-based MT. In NMT, the subword-based approach is widely used and subword decreases the number of out of vocabulary and keeps the translation quality if input sentence includes out of vocabulary words. However, even if using subword doesn't always work well. Our motivation is to work well for proper noun translation. We use same training data and effectively training NMT model. We propose a method to enhance accurate proper noun translation using subword NMT by factor transformer and NU features. Subword-based NMT is almost free from out of vocabulary words. However, it doesn't not always work well for proper nouns. We propose a method to use named entity feature with factor transformer for accurate proper noun translation. The proposed method only uses a parallel corpus and named entity recognition model here, without use dictionary as an external knowledge. We inject any feature vector into factor transformer. And also we use any probability distribution together with subwords. Sometimes any symbol of proper noun is annotated in a given sentence. This is same for human annotation and any symbol estimate is unclear. Any probability distribution can explain subtle any features. I'm talking about factor transformer of conventional method. Factor transformer has linguistic information and integrate part of speech information into NMT decoder. And also conventional method of factor transformer sometimes used in low resource NMT. Proper noun corpus usually is little than general nouns and could be low resource too. These grammatical feature made from external knowledge and its additional information improve MT results. We introduce named entity feature vector into factor transformer model. In this slide, I explain factor transformer structure. Instead of part of speech, we use any feature with word-wise BIO tag, which are beginning, inside, and outside symbols. I'll talk about any features on next slide. Now, I propose a factor transformer model by using two factors of subwords and any feature. We present two types of any feature and two model variants in factor injection layer, as shown in this slide. Left side is one encoder model. The embedding vector are summed up with the corresponding positional encoder vector and sent to the following encoder layer. The rest of the model remains unchanged from vanilla transformer. Right side is two encoder model. The output from encoder are summed up and are used as factor out as encoder outputs. In this slide, I'm talking about any feature of factor transformer. We use two types any features. One is one hot vector and another is any probability distribution vector. Any features are obtained from any model, any R model on a source language sentence. Here, In embedding layer, one hot vector presents one best categories. NEP, on the other hand, an any probability distribution vector, the sum any categories. Sometimes any symbol of proper noun is annotated in a given sentence. This is same for human annotation, and any symbol estimation is unclear. Against one hot vector, any probability vector can represent normalized any features. For experiments, we use JParcrow, WMT 2020, and our field experiments. Use different data set for training and test data. There are two translation directions. Proposed method is evaluated in both Japanese to English and English to Japanese task. We use different condition training data and test it due to the effectiveness. We use a vanilla transformer as a baseline model. And next, we evaluate proposed method. At first, we use any symbol with one encoder and two encoder. Any symbol is one hot vector and represent one best any category. Secondly, we evaluate any probability distribution with one encoders and two encoders. And we use two NER model. That NER model is used as Japanese NER model, and also Stanza is used as English NER model. For the Japanese to English experiment, we use NER model based on pre-training, but NER model and fine-tune it. Stanza released in Stanford NLP Toolkit. According to the performed of any feature and structure evaluated. For evaluation metrics, we use proper noun accuracy, the percent of proper nouns correct translated over entire of ones in test set. This indicates how to accurately translate proper noun. And also we use blue as translation quality metrics. In the table, proper noun translation is left side and blue is right side. We conducted Japanese to English and English to Japanese MT experiment to compare the performed of proposed method. Table shows the result. Left table is Japanese to English task, and right table is English to Japanese one. In Japanese to English, two encoder model outperformed the baseline. The result by two encoder model with any probability distribution shows the best performance. However, the one encoder model outperforms the baseline in English to Japanese task. Okay. I'll move on the conclusion for enhanced NMT. Any feature injection as factor. We use two types any feature. One is one hot any vector, another is any probability distribution. In Japanese to English, two encoder and any probability distribution vector is 9.6 in proper noun and 2.5 in blue square vanilla transformer. In English to Japanese, one encoder any one hot vector is 3.6 and 1.3 in blue square. The result of proper two experiments could be compared enough because the condition is different. The most important point is that the effectiveness in feature contribute to proper noun translation. That's all I have to say. Thanks for your attention.
Thank you. A nice presentation by Tai. So any questions from participants, audience? Any questions? Okay, so I have only one question. So how you do that your any features means how you extracted that any features like name entity features from the corpus?
So in Japanese to English, we use about 30 feature, so of any feature, and so in English to Japanese, so we use 50 feature of any symbol.
Okay.
Yes.
Okay. Okay, thank you. Thank you once again. Nice presentation. Thank you.
Thank you.
Okay, so next title is multitask learning for improving gender accuracy in neural machine translation. So
Hi, I will
yes,
share
hello. Yes,
the screen.
Gracilia, so can you start presenting? Can you
Yes,
please share your slide?
yes, one moment. Can you see the screen?
Yes, I can see. Okay, please start.
Okay. Good afternoon, everyone. Thank you so much for attending this presentation. My name is Graciela. I'm a bachelor student of physics engineering at Universitat Politécnica de Catalunya in Spain, and I'm about to present you the paper that was a result of my bachelor's final project. The paper is titled Multitask Learning for Improving Gender Accuracy in Neural Machine Translation, and I did it at the Machine Translation Group at UPC. I'm super glad to be here, and first of all, I would like to thank my advisors, who are the co-authors of this paper, for giving me this opportunity. So the presentation is structured as follows. First of all, I will give you a little introduction to the topic. Secondly, I will talk about our proposed methodology. Then I will make a few comments on the implementation, and finally we will talk about the results and conclusion. Okay, as introduced by the title of the paper, our main goal is to improve gender accuracy in machine translation. It has been shown that empty systems present different types of social biases, such as gender bias. This type of bias is more visible when you try to translate from a gender-neutral language such as English to another with grammatical gender, such as, for example, Spanish. In this type of languages, noun and also adjectives and verbs carry gender inflection. So, for example, when translating a noun from English into Spanish, the system has to associate an inflection to that noun in Spanish. And the problem here is that most of the times the system uses a masculine or a feminine inflection following stereotypes. We have an example here. In this sentence in English, we can see how the pronoun her refers to the boss, indicating that she's a woman. And in the translation into Spanish, the system associates the masculine inflection to the word boss in Spanish. And as for the secretary, there's no information in the sentence that suggests the gender of that word, but in this case, the system uses the feminine inflection. So this is a clear example of how an empty system can perpetuate stereotypes. Okay, so gender bias is mainly attributed to the already present bias in the data used to train empty systems. And it also has been shown that models trained on this data tend to further amplify this bias. So in this sense, with our research, we aim to reduce this amplification. So in the end, our proposal is to mitigate this bias by jointly learning the translation, the part of speech, and the gender of the words of the target language. With this approach, we hope that the more information the system has, the better the translation will be in terms of gender. So with this little introduction, we can move on to the methodology. As the baseline for this project, we use a language-specific encoder-decoder architecture based on the transformer. As you probably know, this is the basic structure of the transformer. And in order to get the part of speech and the gender of the words in the target language, what we basically did was adding two new linear layers at the output of the decoder attention block. The idea is that our system is able to predict all three things at the same time, but in order to see which is the effect of each of the new classifiers, we also train them separately. So in the end, we had three different configurations as illustrated here. All three different configurations were trained with the same dataset. In this case, we used the Europal corpus, and they were all trained for all possible combinations of English, Spanish, German, and French. For the extraction of the part of speech and the gender from the sentences in the dataset, we used the stamps library. And as for the transformer implementation, we used the one provided by First. Okay, well, also, so once all the different configurations were trained, we assessed the translation quality using the Bleo score. Looking at their average performance, we observed that the addition of tagging tasks doesn't significantly impact the average performance, with a difference of less than 0.2 points between all systems. If we take a look at each language pair, there's some significant improvements. The most important is the one in the French-English pair, in the case of applying both classifiers with an improvement of 0.51 points compared to the baseline. And this is followed by the English-German pair with the gender classifier with an improvement of 0.31 points compared to the baseline. Finally, in order to measure the gender bias, we use the WinOMT test set. This set allows to measure gender bias when translating from English to higher morphological languages. So here we present the results from English to Spanish, French, and German. In general, as we can see, all three different configurations outperform the results of the baseline model for all languages and for all the metrics of this test. As we don't have so much time, I will focus on the accuracy as it is the most representative. We can see how Spanish and French benefit the most from the configuration with both classifiers. In the case of Spanish, it improved 6.8 points compared to the baseline. And in the case of French, it improved 6 points. For German, we obtained the higher accuracy in the case of with the post classifier with an improvement of 5.6 points. So in this paper, we have shown how giving more information to the system really helps mitigate gender bias while maintaining the average translation performance over the tested languages. As we have seen, the translation quality doesn't differ more than 0.2 points on average, and the gender accuracy it improves up to 6.8 points. Yes. So all in all, with our simple methodology, we impact significantly in gender bias. And more than the methodology that we are proposing, which is simple and effective, we would like to encourage the community to evaluate their methodologies, not only in terms of translation quality, but also in terms of social biases. So that's everything for the presentation. Thank you very much for your attention. And if you have any questions, I will be more than happy to answer you. Thanks.
Thank you, Gracilia. Any questions from the participants? Yeah, hello. Gracilia.
Yes.
Can you hear me?
Yes.
So what is the corpus which you have used, and what is the size of the corpus?
2 million sentences, I think. I don't know if I can.
Hello.
It's yes, the Europal corpus. 2 million sentences.
Okay. What is the size of the corpus?
Yes, this it has 2 million sentences. Do you mean this? The number of sentences and the words? Oh, I don't remember, but I think that you can check in the paper.
Okay, fine. Thank you. Okay, so Professor Joseph having some questions. So please ask. Yes.
Yeah, very nice talk.
Thank you.
I have a question. The numbers you present, are they single run numbers or are they averages of multiple runs?
Sorry, can you repeat, please?
The blue scores, for example, that you present,
Yes.
are they results of single runs of the system or are they averages? Did you train the system like 5 times or 10 times and then reported averages, or is it like a single training?
Yes, we trained the system once, like for 25 epochs, I don't remember.
Yeah.
And this is the result.
Okay, for one training for each of the
Yes.
configurations. Yeah. Okay, thank you.
You're welcome.
Any more questions? Okay, so I have only one question. So did you try with that human evaluation?
With what? Sorry?
Human evaluation?
Okay, I don't know about that. I'm a bachelor student, so we only focus on that topic. I don't know
Okay,
more.
okay.
Sorry,
Okay.
sorry.
Okay, no problem. So, Vasilia, thank you very much for your presentation. Thank you.
Thank you.
Now, the next presentation, next title is Small Batch Size, Improved Training of Low Resource Neural Machine Translation by Alex. So, welcome.
Thanks. Yes. Can you see my screen?
Yes, visible. So you can start.
So, hello, I'm Alex, and I will be presenting the paper they wrote together with Andrei Popescu-Bellis on how small batch sizes improve training on low-resource neural machine translation. We are from the University of Applied Sciences of Western Switzerland, HSSO in French, and the Swiss Federal Institute of Technology in Lausanne, DPFL. So we want to minimize loss. What is the general practice? In general, we're going to be using a mini batch gradient descent, and typically we're going to be wanting to set our batch sizes to be as large as our GPU memory will allow. This is because large batch sizes typically are understood to provide a more accurate update of the gradient, although it has been observed that smaller batch sizes can offer a regularizing effect, likely due to the noise that they introduce in the estimation. Nonetheless, typically practitioners and documentation of toolkits will recommend using larger batch sizes. So why do small batch sizes regularize the gradient? Well, we can get some insights from studies on convolutional neural nets on images, in particular Keskar et al., where they introduced this notion of a flat minimizer as opposed to a sharp minimizer. So a flat minimizer or a flat minimum is going to be a local minimum of the loss function, in which this function varies slowly in a relatively large neighborhood of parameters. What this means is that we can define it with a relatively small, low precision. In general, they observe that large batch sizes will tend towards the closest minima from their starting point, and so will tend to sharp minimizers, whereas small batch sizes, due to the noise in their gradient estimation, will be able to explore a broader range of minima, and so will tend towards flat minimizers, which they observe to be better, to produce better generalization abilities for the model. There have been some recent studies on batch size in neural machine translation. The main one and the one that served some inspiration for this study was done by Popel and Vojar, where they experiment on a transformer in a high resource setting. And they observed that larger batch sizes improve the scores, although with diminishing returns. Zenrik and Zhang, however, use a recurrent neural net in a low resource setting, and they instead observed that smaller batch sizes improve the scores. And Arabi and Mons, using the same dataset as Zenrik and Zhang, but using a transformer, do not in fact observe that smaller batch sizes improve the scores, and towards the larger samples, while still being low resource, they observe the opposite, that larger batch sizes in fact improve the scores. For this, it is worth noting that batch size is not the main objective of their study, and by the time they experiment with different batch sizes, they have already introduced several hyperparameter changes that introduce regularization to the models. Finally, in Xu et al., they also experiment with a transformer on a high resource setting, and likewise, they also observe that larger batch sizes improve the scores as they stabilize the gradient direction. For our experiments, we used two datasets, both 60,000 lines. The first one was the WM20 very low resource task on Upper Sorbian to German. And the second was a random sample of German to English news commentary. We used transformer base with sentence pieces as tokenizer on OpenNMTPy, and we set all our hyperparameters to the defaults, to the recommended settings on OpenNMTPy, except the batch size with which we experiment. In particular, we trained several models with different batch sizes ranging from 100 to 10,240 tokens. This last number is because without providing additional gradient accumulation is the largest that would fit in our GPU, and we trained for 800 epochs. The two smallest batch sizes, 100 and 250, do not reach scores significantly above zero, so we do not report on them. And we also note that although we train all these models for the same amount of epochs, if we instead look at real time, the rankings among the different batch sizes do not change. So we observed that well, first of all, the three smallest batch sizes, we can see that outperform the largest batch sizes. In particular, we see that the highest scores that the larger batch sizes reach are reached well before by the small batch sizes. So they not only overperform the larger batch sizes, but they also train much faster. And in particular, we see that we obtain best score with a batch size of 1,000 tokens in both High Sorbian to German and German to English on both our development and test set with all the measures that we use, BLEU, cross-entropy loss, CHRF, and TER. And furthermore, we also observed that the scores degrade as batch size moves away from this value in either direction. With these results, then we can ask ourselves two questions. Firstly, do large batch sizes simply require more time to converge? And if given that time, they would just outperform the smaller batch sizes. For this, we take our best performing batch size, 1,000, and almost the maximum, 10,000. And we continue training them for double the amount of time. And we see that the difference in BLEU only changes from 385 BLEU points to 325. So the difference in ranking is not overturned by training for longer. Although we could note that the learning schedule could be optimized nonetheless for larger batch sizes. The second question we could ask is if this optimal value changes when using different tokenization methods. For this, we compare the shared sentence piece vocabulary that we had been used until now with an unshared vocabulary, as well as a BPE. And we observe that the same differences hold. 1,000 batch size continues to overperform. And in particular, our previous shared sentence piece vocabulary was the best of the tokenization methods tested. So what is the main takeaway from this? It seems that for low resource neural machine translation, when using a transformer, a smaller batch size leads to both higher scores as well as shorter training times. And it is likely due to a better regularization of the gradients during training due to the noise introduced by the small batch sizes. Questions for future work would be, what is the range of low resource for which small batch sizes are better? Since it seems that when using higher resources, larger batch sizes in fact are better for the model. Then what is the best learning rate depending on the batch size? How can we best proportionally adjust it? And finally, if a dynamically scheduled combination of both batch sizes, varying batch sizes, and learning rate could provide an even better regularization than just lowering the batch size. So that is all for me. Thank you so much for your attention. And if you have any questions, don't hesitate to ask.
Thank you, Alex. Nice presentation. Yes, one question from Professor Joseph. Yes, please.
Alex, thank you for the presentation. I enjoyed it. It's more a comment, like you mentioned the Shu et al. Paper. That paper actually has dynamic batch sizes. So for each step, we compute that the optimal batch size can be small, can be large, and it develops. It kind of like goes larger, goes smaller again, etc. And it just it stops accumulating when the gradient direction starts fluctuating. So would that go somewhat in the direction that you said, like at the end, like this dynamic batch sizes, etc., and learning rates?
Indeed, definitely it would be in the direction. I'm not sure if we can draw definitive conclusions from that paper because of two main reasons. First, it is on only a high resource, if I remember correctly, English to German and English to French, both on the millions of sentences. And secondly, the smallest batch size allowed in the schedule, I think it's 5,000 tokens, if I remember correctly, or something like this. So it doesn't go low enough to properly observe these changes. But yes, it could be on this direction indeed.
Sir, my question is how many GPU you have used in the training purpose?
All models were trained on 2 GPUs.
Okay, 2 GPU size
11 gigabytes.
means 11, right? So it's 22. Am I correct?
Yes, yes.
Okay. Thank you.
Okay. Any more question? Okay. One question from the participant asked that is the batch size determined based on the tokens or source or target? Even you can see the questions in the chat box. Okay.
Can I see them? Sorry,
Yes.
can you repeat the question?
Question is that is the batch size determined based on token, on source or target?
On the source side.
Okay. Okay. So thank you. Thank you once again. Thank you.
Thank you.
So we can switch, move to the next paper. The presenter is Sripati Siripada. The paper title is like the science of literary study in Sanskrit, its applications to literary machine translations and other NLP tasks. Okay, so please, you may start, please.
Can you hear me now? Am I audible, sir?
Yes, yes.
Yes. And can you see my screen?
Yes, it is visible.
Yeah. Firstly, thank you to the organizers and thank you to everybody for taking time and being here today. It's a pleasure to present to you all. The Upanishads in the Vedas make a very bold proposition, Vidyaya Amrutam Ashnute, meaning real knowledge or education leads to immortality. Now, we at MIT ADT SVS School of Vedic Sciences have always been inspired by this statement, in the sense that if real education or knowledge leads to immortality, the real education or knowledge itself is immortal or eternal. And hence there are aspects in ancient knowledge, in the Shastras and Sanskritam, that are applicable to today's technological advances. As a part of this effort, inspiration, myself, Sripati, and my co-authors, Dr. Anupama and Raghuram, from the MIT School of Vedic Sciences in Pune, have presented this paper where we took a framework from Kavya Shastra called Lakshyartha, or indicated meaning, and applied it to solving problems in literary machine translation. Before we get into what we did, let's understand what the challenges are in literary machine translation today. For example, if we take sentences like, she was showered with blessings, which are very common kind of usages in literary works, and we give this to a Google Translate for translation, some of the translations look like this. For example, in Hindi, it translates to Vah Ashirvad ke saath tanhaya gaya tha. Another example, he stretched the truth, And if you put it in Google Translate, you can translate to many languages. Again, for example, in Hindi, it will say, Ushne sach phailaya. One more example, I buy peace of mind by being silent. And Google Translate would translate this as my chup rehkar man ki shanti kharidta hu. While the literal word-to-word translations of Google Translate are very good, if you put the words together into the sentence, the sentence does not mean much. It is not conveying the actual meaning of the original sentence. And if you then compare with blue scores against a standard translation by a human, the blue scores are literally all over the place. They're either very low, or even in places where the blue score is very high, the translation is not necessarily conveying the intent of the sentence. Now, if we look at closely as to what's happening here, the challenge here is that the literal meanings of the words in the sentence, when added together, do not become the meaning or the intent of the sentence. And hence the translation is inaccurate or inconsistent across languages, and in a lot of cases, both. Now, this is not a new problem. This problem has been around for a while. And with a little bit of thought, we can also see that if there was a way to paraphrase these sentences in a manner such that the literal meanings, when added together, convey the intent of the sentence, then a translation engine like a Google Translate would be able to translate these sentences appropriately across languages. Now, for example, if the sentence "she was showered with blessings" could have been paraphrased as "she received lots of blessings," then the problem is solved. So what we are looking for here is a mechanism to paraphrase such sentences into a form where the literal meanings of the words can be added. Now, even this is not a new problem. There has been work in terms of training models to identify and paraphrase sentences with figures of speech, but that has a challenge of needing huge labeled data sets because the figures of speech could be different in different languages, etc. And hence we are after a much more fundamental approach which can solve this problem of training the models quickly. This is where we turn to the science of literary studies in Sanskritam, Kavya Shastra. And our hypothesis was the framework of Shabda Vyapara, which literally means function of a word within a given sentence. And within the framework of function of a word, there is a definition of a Lakshyartha, which is indicated meaning of a word. Our hypothesis was this was give us a clue to build an approach to do economical training of NLP models to be able to identify and paraphrase that sentences, and that too, if we can do it in a language independent manner. So Shabda Vyapara, the author of the seminal text, Kavya Prakasha, Mamatacharya, defines it as Syad Vachako Lakshanikaha Shabdo Atra Vyanjakastritha. He's basically saying, in a sentence, there are three kinds of words based on the function they do. The first one is the expressive word, where the literal meaning of the word fits in exactly into the intent of the sentence. That's called the expressive word or the vachaka, and it gives rise to the vachyartha or expressed meaning. Now models can, like T5 can or Google Translate can very easily translate such kind of sentences. The second kind of word in a sentence could be lakshanika, where the literal meaning of the word does not fit into the intent or the meaning of the sentence. So we have to borrow an indicated meaning. That's called the lakshyartha. And the third, there is another third category where the literal meaning also makes sense. And there is also a secondary meaning which also makes sense in the sentence. So that's called the suggestive word or the vyanjakaha, which gives to vyangyartha. Now, our interest in this paper was to explore the framework of Lakshyartha, and if we can leverage it to identify and paraphrase sentences I showed earlier as examples. Now, Lakshyartha is defined by Mamatacharya as Mukyartha Badhe Tat Yoge, a very language independent definition of where there is a problem with the literal meanings in a sentence. For example, she was showered with blessings. We can very easily see that the literal meaning of the word showered does not go with the intent of the sentence. And hence, this sentence is an example of where Lakshyartha needs to be adopted or the indicated meaning need to be adopted. He further classifies Rudito Ata Prayojanat. He says that this indicated meaning can be of two broad categories based on usage and based on special purpose. The indication based on usage is very common very similar to idiomatic usage in English. For example, do not beat around the bush when expressing your viewpoint. Now, beating around the bush literally does not have anything to do with talking, but we use it as a widely accepted idiom or a phrase. Similarly, it's time to hit the sack. Again, there's no connection, but it is widely used, accepted usage with a particular kind of a meaning. So that is called the usage-based. And our interest in this paper primarily has been around the special purpose-based indication, which is further classified into two. One is based on sadrushya, which is similarity, which again gives rise to two subcategories of indication called the qualitative indication. And the other one, which is based on other relationships and not similarity, that's called the pure indication. And it further gives rise to 4 subcategories. Now, in total, we have 7 categories of indication defined in Kavya Shastra. Now, the interest here is to understand these categories and find out if there are patterns for paraphrasing the sentences based on the categories of the indicated meaning. So I would quickly go through a few examples, laying some stress on the patterns which we can see. The first one, based on similarity or the qualitative indication, is the superimponent, very similar to a simile. For example, if I say her eyes are lotus petals, I mean that they are like lotus petals. So a very simple use case to paraphrase, I just need to add a word like in between, and the sentence starts making much more sense. Very similar is the second category, introsusceptive, but only one of the two objects is mentioned. That which is being compared to is mentioned in the sentence. The other one is left out. So if somebody looks at a lady with a beautiful eyes and says they are lotus petals, they are obviously referring to the eyes of the lady, but the word eyes is missed out in the sentence. Similarly, in the example, your conduct is teaching even the learned ones. The conduct is the teacher, but the word teacher is left out in the sentence. So in this case, we need to add the missing word and also add other words like in a metaphor, for example, itself. Right? That's the path to paraphrasing this kind of indicated meaning sentence. The other broad category is the pure indication. The first one is inclusive indication, very common. Everybody says your pizza is delayed or is on its way, but the intent is your pizza delivery person is delayed because the pizza on its own cannot walk. So we need to add a word or a phrase into the sentence in which has some connection with the meaning of the sentence, so to make it complete. That's called the inclusive indication. There is another variety which is called the indicative indication, where the secondary meaning replaces the first meaning of the literal meaning. For example, if I say she jumps to conclusions, I replace jumps with she arrives at conclusions easily. So we are replacing a given word in the sentence to make more meaning. Similarly, the sound of war cry shattered their hearts. That word shattered needs to be replaced with created fear in their hearts or something equivalent to make sense. So here the path to paraphrase is to replace the word with a more meaningful set of word or a pair of words. There are 2 more categories of pure indication, one being the superimponent. Here, there is a relationship between 2 objects expressed in the sentence, like cause and effect, like knowledge is power. Knowledge is cause, power is the effect. So I need to paraphrase in a manner so that I'm explaining the relationship between the two objects being presented in the sentence. Similarly, another example, when desire blinds the mind with delusion. Now, desire is the cause. Now, blinding the mind is the effect. So there is a bit of work we need to do around explaining the relationship. The last category is similar to the third one, the superimponent, just that only one of the 2 objects being discussed is presented in the sentence. I look at a knowledgeable person and say he has the power. I'm obviously referring to the power of knowledge, but the knowledge piece is omitted in the sentence. So within the context of where it is said, we need to add something into the sentence. So these are the 7 categories of like indicated meaning that are defined. And we can see that for most of them, there is a path to paraphrasing the sentence, and the patterns are consistent. So our key takeaways from the framework to apply to literary machine translation is that the framework of Shabda Vyapara and Lakshyartha, or the function of word and indicated meaning, provides a more fundamental classification of words in a sentence. Now, there are 7 distinct categories. The characteristics are very well laid out. They also lend to patterns of paraphrasing roughly consistent with the category of the indicated meaning. And because we are talking at a word in a sentence, and if we use word vectors in NLP, the word vectors also would be aligned to the meanings of the word. So hence we should be able to programmatically do a function of the word vectors to be able to map the kind of category indicated meaning in a sentence. And if we are using word vectors, it should be language independent as long as we are relying on a reliable set of word embeddings. And lastly, because the framework is so tightly structured, we should be able to train economically with supervised learning. With this as the background, we set out on a small experiment to train an NLP model to do this. First, we tried out if it is able to identify the indicated meaning, whether the indicated meaning exists in a sentence. That was step one we did. Then we tried to categorize the given sentence based on the category of indication. And then the third step we did, after we had confidence in the first two steps that the models are able to do it, we then attempted paraphrasing the sentence. After paraphrasing, we then gave the sentences back to Google Translate to translate, and then compared the blue scores before and after paraphrasing. So roughly that's what we did as an experiment with a small data set. Step one, we had 400 sentences, both with indication, without indication, and we trained the model. We got about close to 80% accuracy. Some of the results are on the slide. For most of the sentences, CNN 2D model was able to pick out with just black box implementation, not making any changes in the fundamentals of the model. We were able to identify 7 to 8 sentences out of 10 accurately, whether there's a Lakshyartha or not. Second, we did a CNN 2D training with 300 sentences across all categories of indicated meaning. And we got close to about 70% test accuracy. 6 to 7 sentences in a validation sample set. We got the right classification by the model. And then we took Google T5 and we fine-tuned the T5 to paraphrase these sentences with just 300 sentences. That was the database. And with 2 epochs of training, we saw some interesting results where the model was able to paraphrase these sentences appropriately and meaningfully. Some it did not do, some it did, but the results were very encouraging, where it was able to identify and paraphrase as well. We then took these paraphrased sentences and put them into Google Translate again. For example, she was showered with blessings. The model, which was fine-tuned on our database, we call it T5i. The T5i was able to paraphrase it as she received lots of blessing. Now you can easily guess that the blue scores would be very different across languages for the 2 sentences. And the sentence which has been paraphrased, the blue scores were much more consistent across all languages. Any language you would pick, you would get a 0.5, 0.6, 0.7 kind of a blue score on that sentence. Another example, he stretched the truth. The model was able to paraphrase this as he used falsehood. Again, he used falsehood would be consistently translated by Google Translate, and the blue scores will show the numbers as to how consistent it is. One more validation example, I buy peace of mind by staying silent. The model paraphrased this sentence as my peace of mind comes from staying silent. And it's a no-brainer that the sentence on the right will be translated much more consistently across languages. Even when the blue score is low, the sentence makes a lot of sense, and the meaning of the sentence is close to the original intent of the sentence. So this is the experiment we did. In the validation sample set, our blue scores improved from, as a corpus blue score, it improved from 0.39 to 0.6 in one run of training and one run of validation. And it also showed it indicated that the framework of Shabda Vyapara and Lakshyartha provided a fundamental way to classify words in a sentence. They also gave us a framework to train the NLP models. And also the results were consistent across languages. And we also believe that if this is further fine-tuned and trained, the model can then work in a language independent manner. Thank you very much. Happy to answer any questions.
Okay, thank you, Sripati. It's very nice presentations. Any questions from the audience?
I have some questions.
Yeah.
So thank you for the presentation. It's very nice, very interesting.
Yeah, Professor Joseph has some questions.
Yep. So one question would be, how important do you think is language distance? If you have very distant languages, I mean, you used Hindi, English, for example, do you think that it's harder for the machine translation system compared to, like, let's say you have a high resource pair, English, French, English, German, English, Chinese, or something like this. Do you think they will be in general better with figurative language?
I think the result should be consistent across all languages, because the definition of lakshyartha, what we are looking, the definition of indicated meaning is where the literal meanings when added don't make sense. So when we are working on word vectors, and we are trying to map the function of word vectors to whether the indication exists or not.
So sometimes when you have closed languages, like the examples you gave, they would be, a lot of them, literal translations into German would be fine and have the same meaning, because English and German are Germanic language family. So close. That's I kind of like what I was wondering. Like, sometimes, it's okay. It's because so close, so like, a figure of speech is actually preserved in the other language. But if you have very distant languages, it's less likely, perhaps.
Yeah, but we are not identifying figure of speech. We are going one level, a much more fundamental classification than figures of speech, where whether when I add the literal meanings in the sentence, is it making sense or not? That's what we are after. So we have not tried in European languages. We have tried only the translations in Indian languages. We would try, but I would think it should work consistently across whether the languages are close or not. We are not after the figure of speech. We are going at a much more fundamental level of classification, which is called the indicated meaning, the suggestive meaning, whether the word is an expressive word or an indicative or a suggestive word. That's what we are after.
Thank you.
Thank you. Thank you, Sripati. Okay.
Thank you.
Any other question from? Okay, then we can move to the next paper.
Thank you, everybody.
Thank you. Thank you. So the next presenter is Mingan Wang. The paper title is Diformer Directional Transformer for Neural Machine Translations. Mingan Wang. Are you there? Wang. Mingan Wang. Okay, I think he is not there. So we can move to the next paper. So the presenter is Jiasin Gao, GOU. The paper title is Self Distillations Mix-up Training for Non-Autoregressive Neural Machine Translations. The presenter Jiasin Gao. I think he is absent again. So we can go for presenter is next paper presenter is Ramakrishna Apicharila. The paper title is Irumet Developing Machine Translation System for Educational Content in Indian Language. Ramakrishna, are you there?
Hello.
Yes.
Okay.
Can you please present your paper?
Yeah, I'm sharing the screen.
Okay, fine.
Is the slide visible?
Yes, it is visible.
Yeah, thank you. Hello, everyone. My name is Ramakrishna. I'm a PhD student from Department of CSC, IT partner. I'm working under Dr. Asif Iqbal and Professor Pushpak Bhattacharya. I'm presenting the paper titled EDUMT, Developing Machine Translation System for Educational Content in Indian Languages. So here is a summary of the presentation, motivation of the work, creation of the parallel corpus, NMT experiments with domain adaptation, multilingual NMT, and data augmentation strategies, results and analysis, and conclusion. So MOOCs have gained a lot of attention due to the popularity of e-learning. However, most of the content is available in English only. So one potential solution to mitigate this issue is to develop machine translation systems which can translate content. However, developing systems between English and Indic pair is quite kind of simpler than developing between Indic and Indic pair because of the unavailability of resources. So in this work, we focus on developing neural machine translation system for Hindi to Bengali language direction for computer science domain. So since we do not have any parallel corpus for this particular domain, we create parallel corpus in two ways. First one is synthetic corpus, where we crawl lecture subtitles and lecture transcripts from YouTube and NPTEL website, and using Google Translate to translate it to Hindi and Bengali. Along with that, we also do post editing by extracting some part of the synthetic corpus and created the post-edited version of that by crowdsourcing as well as annotation. So here are the statistics of the data. The two domains that the subdomains are programming, data structures, algorithms, that is one, and second one is AI. So total synthetic corpus we have collected was 5,95,000 sentences, and the subtitles, post-edited subtitles for around 40,000 sentences. So still there is no overlap between these two, between post-edited as well as synthetic. Total data was around 6,35,000 sentences. So we majorly focus on developing NLP systems with the domain adaptation objective only. So we first tried two baseline models. First one is out of domain, which we so we are also using Hindi Bengali Samanantar corpus as a general domain data, which consists of 2.5 million sentences. So the out of domain baseline, we train on the Samanantar corpus only, and we all the models are tested with manually created Hindi Bengali educational domain test set. So on the in-domain baseline, so we train the model only on prepared in-domain clean data set of 40,000 sentences. Then the domain adaptation techniques. So we train three models where the objective is to fine-tune the out-of-domain baseline with different in-domain corpora that we have created. First one is FT clean, which is fine-tuning clean. So where we fine-tune the out-of-domain baseline with in-domain clean corpus. Then FT both, fine-tune both, where we fine-tune with the synthetic data as well as clean corpus. So the main reason is that we want to check whether clean corpus would be enough, or if we can use synthetic corpus also, will it be able to benefit the model. So since NMT like neural models are resource heavy, so adding data is more helpful, even though it is synthetic. Like both source as well as target, both are synthetic, so still it is helping the performance of the model. And the third one is FT both mixed. So here instead of fine-tuning the model just based on the in-domain data, we are adding same amount of out-of-domain data also, so fine-tuning on that. So those are the three models. And after that, we are experimenting with two other techniques, source token mixing and target token mixing. So the main idea in this is that previously we have to train two models, which might be time consuming, but in source token as well as target token mixing, we can train a single model by adding both in-domain as well as out-of-domain data. Here in the source token mixing, we are adding domain-specific tags to the source sentences. In the target token mixing, we are using the domain-specific tags to the target sentences. However, due to the data size mismatch between in-domain and out-of-domain, we are oversampling the in-domain corpus. And after that, we are experimenting with multilingual NMT. So here, since we create the parallel corpus from English, so we essentially created a three-way parallel corpus. So we wanted to experiment with how the addition of English will help the translation between Hindi and Bengali. So for that, we use the outer domain baseline, which was trained on Samanantar Hindi Bengali corpus. But instead of fine tuning with Hindi Bengali corpus, we are fine tuning with Hindi Bengali, Hindi English, as well as English Bengali parallel corpus. So that is the fine-tuned multilingual model. And also we were experimenting with data augmentation. So here, when we create post-edited data, so we have the sentence pairs between synthetic Bengali as well as post-edited Bengali. So we can train automatic post-editing model which can post-edit the synthetic Bengali sentences. So which can be used to train the model further. So for that, we were experimenting with two objectives where auto-encoding, where source is synthetic Bengali and target is post-edited Bengali, and also denoising auto-encoding. So same as auto-encoding, however, with source sentences are corrupted with two forms of noises. One is random token dropping with 0.1 probability for each token, and random token swapping between its neighboring words with 0.1 probability. So, so source is corrupted in this way, and target would be post-edited clean Bengali. And we also combine these two objectives to make a third model. So these are the post-editing models. Then we use these post-editing models to post-edit the synthetic corpus, and we are denoting it as semi-synthetic corpus, where the source is synthetic Hindi, where target is automatically post-edited Bengali sentences. So we are adding this semi-synthetic corpus with the prepared corpus to train the models further. So we tried three models on that. So first one is fine-tuned both with denoising post-editing model, where the model was trained with the output from the denoising model. Same as that, fine-tuned both with AP, where automatic post-editing, where it is auto-encoder based post-editing module, and the third model is combination of these two objectives. So all the experiments are conducted with transformer architecture, with the shared subword vocabulary. We use open sentence piece to get the shared vocabulary. So these are the results. So as we can see, our best model was FT multilingual, which is fine tuning on multilingual corpus, which with a blue score of 34.8 and TER score of 0.466. So one is that since we couldn't find any existing Hindi Bengali educational test set, so we manually created test set of 2,630 sentences. So these sentences were carefully selected to avoid any overlap between training data. So, and however, we observed that all the fine-tuning models are working fine, better than both the baseline models. However, source token mixing as well as target token mixing, these models are not performing well in our case. The observation is contrary to the existing research. So here we observed that first one is oversampling, since that is one reason that why it is underperforming, and also because the model is converging faster than the other models, we observe it as overfitting. So that might be the reason why it is not performing well. And also the semi-synthetic data augmentation methods, where we post-edit the data and use it to train the models, it is performing well actually. But the interesting thing is that we are training the post-editing models with relatively less number of data, like 40,000 sentences only. But still, it is performing as good as our best model, multilingual model, with the FT post denoising model is achieving second highest TER score of 0.481. So to conclude the presentation, so we developed an NMT system for Hindi Bengali pair for computer science domain. So we prepared the corpus by crawling as well as post editing, and we trained NMT models with the domain adaptation objective, and our multilingual model achieved a highest score on a manually created test set of 34.8 blue. So we also conducted manual analysis on this best model by taking random 50 samples and asked four annotators to give the scores based on 1 to 5 scale. So when we calculate the average adequacy was 3.5 and average fluency was 3.85. So, and also we made the model deployed, and it is accessible at this link. Thank you so much for the listening to the presentation. Thank you.
Thank you, Ramakrishna, for your nice presentations. One question in the chat box from Kanaya. What do you mean by domain being algorithms and data structure and AI? The question is given in the chat box.
So here we are considering in the computer science domain, since we have a lot many subdomains there, so we focus on mainly programming algorithm and data structures as one domain, and artificial intelligence as second domain. So we are essentially extracting the lecture subtitles from these two specific lectures.
Okay, thank you. Any other questions from the audience?
Yes, I have one question.
Sure, please ask.
My question is about the fine-tuning technique. So can you explain that how you have actually that fine-tuning, which technique you have used for means is it first trained your model on outdoor and then just reload on that model on your in-domain training data set?
Yes, it is the case. So when we train the model on outer domain baseline, so we essentially trained one model and we use it to warm start our in-domain training.
Yes, so my question is, when you have trained your outdomain data, right, using your transformer model, then the vocabulary is different, right? And when it is loading on your in-domain data, then how you handle those problems? Am I clear?
Yeah. So essentially here, since it is existing, since it is known problem, so we use the vocabulary from the open domain only. So whatever the vocabulary that we create for the outer domain corpus, we use the same subword vocabulary to tokenize the in-domain data also, so that there won't be any vocabulary mismatch.
Okay. So you have used that common vocabulary, is it?
Yes. The vocabulary created on out of domain corpus.
Means you have created that vocabulary using in-domain and out-domain, and then you have trained the out-domain, then it is reloaded on in-domain data. Am I correct?
Yes.
Yes, good.
Okay, thank you. Any other questions? Okay, then thank you, Ramakrishna.
Thank you
can
very much
stop
for
your
the
presentation.
Yeah. Okay.
Yes, so next presentation title is assessing post-editing effort in the English Hindi direction. Presenter is Arafat. So are you there?
Yeah, I'm here. Can you hear me okay?
Yes, I can hear you. So please present your work.
Just 1 second. I'm trying to share my screen. So can you see my screen?
Yes. Please start.
Wonderful. Thank you. So good afternoon, everyone. My name is Arafat Hassan, and I'm going to talk about our paper, Assessing Post-Editing Effort in the English Hindi Direction, co-authored along with my colleagues Vandan Mujadia and Professor Deepti Mishra Sharma at IIIT Hyderabad. So the motivation for this study came about when we asked the question that for any Indian language, or as many as we could look into, does machine translation help in a typical translation workflow? So while there have been many studies on European languages and other languages within the Asian subcontinent, but we couldn't locate anything which had tackled this head on in some depth. And we decided to conduct a controlled study to look into this question. And one way to do it is through post-editing effort estimation, that if your machine translation quality is good and you have a mature engine in the language pair that you are interested in,
then the amount of post-editing effort required in that language to generate a target language text would tell you something about its quality. And post-editing effort typically has been measured along three directions, or rather three dimensions. The first one is a temporal dimension, where it's nothing but the amount of time taken to generate a target translation, often measured per segment or per word. Then you have the technical dimension, which is an estimate of the labor of the translation activity, how many keystrokes do you hit, and how much amount of work you have to put in that sense. And then finally, the more elusive one, which is the cognitive dimension, which tries to say something about the underlying difficulty of translation from segment to segment. So is there anything that we can say about the cognitive part of the task as well? So based on these three dimensions, the research questions that we posed were the following.
Sorry, actually slides are not moving.
Oh, the slides are not moving?
Yeah, now we can see the research question on
Please put your
PowerPoint
camera
mode.
on.
Okay, let me just try and share again.
Please put your camera on. Yes, and share your slides.
Okay. So I've tried to start my video as well, so I don't know though if it's working.
Okay. Arafat, please put your camera on while presenting.
Yeah, so my webcam is not working. I apologize. I'll just
All
try to share my screen on. So can you see my slides now?
Yes.
And are they moving for you?
Yes.
Okay. So apologies for the little bit of an interruption over there. So the research questions that we are posing are the following. That what we want to do is post-editing effort measured on the three dimensions that we talked about, lesser in the post-editing condition, which is when you are introducing post-editing into the translation workflow, compared to the HT condition, which is the translation from scratch, where you don't use any machine translation. So that's, we want to say something about that. Then we also want to look into the quality of the segments that are generated in either of those conditions. Is the quality comparable? Is one better than the other? And then finally, the commonly used machine translation evaluation metrics that we have today, how well do they correlate with post-editing effort indicators? Can we say something about that as well? These are the three aspects that we wanted to cover, but for the most part, we'll focus on the first aspect that we are more interested in. But we will slightly touch upon the latter two as well. So this is what a summary of the experiment design looked like. So this was, like I said, a controlled study. We are studying two translation conditions, the HT condition, which is the unaided without MT, and the PE condition, which uses a machine translation proposal. And then the data that we have is 200 source segments, English source segments that we want to translate into Hindi. And then we contracted 10 professional translators for this study with varying translation experiences. And then the machine translation engine that we use is a neural in-house engine that was trained on W80 data. So the quality was ascertained on certain publicly available test sets. And the methodology that we follow to roll out the experiment is basically a mixed design setup. And finally, the analysis of the data is conducted using linear mixed effects models. So quickly, something about the mixed design setup that we have. So if you can see my slide over here, this basically shows you that over the 5 days that we conducted this study across 10 translators, how did we roll out the translation task? So mixed design is important over here because it prevents any kind of priming and carryover effects. If we had gone for a within subject design, then you can't present the same sentence in different conditions to the translator because they would always they would already be aware of the translation. So in this case, what happens is that each translator sees both the conditions, but they see each segment or each task that was assigned to them only in one condition. So while they are dealing with both the conditions, the stimuli that they see would only appear to them once, linked to only one condition. So what we also did was that we also counterbalance for any kind of order effects. So if one translator was doing or seeing the HT condition first in one session, in the next session, we will flip it over and have them posted it first and then present the HT task to them. So that also takes away any bias that might creep into the data when you are organizing this kind of an experiment. So this is what shows us. The interface that we used was a simple web interface. What you see over here is a screenshot in the HT condition where a translation has already been entered over here. Initially, when it would appear to them, it would be without the text over there, but in the PE condition, the machine translation proposal would be there, and they would be editing in the blue box over there. There would also a timer, but it didn't really do much other than create some sort of a time pressure for the participants, because it has also been said that time pressure helps create focus in these kind of behavioral experiments. So we introduced a timer over there, and this timer would reset every time they navigate to a new segment. So this is what the interface that we used looked like. The data set, we pulled a corpus of recent English language news articles from 2 distinct online sources. These were India-based sources, so the articles were mostly related to Indian news. And we preserved the running context, which means is that we did not scramble all the sentences. So our translators saw their tasks where the sentences were in order in which they would appear in the news item. And this table just shows you the average word lengths per task that they encountered over the 4 sessions spread over 5 days, and the source IDs of the articles that we used for this. We also gave them certain guidelines around how to handle terminology and so on, because there had been some previous work on how terminology is very challenging in post-editing tasks, especially for Indian languages. So we made sure that we had some good guidelines around that as well. Then for an analysis, like I mentioned before, we utilized linear mixed effects models. And the advantage of these models is that it makes the results of your experiments more generalizable, because they account for the inter-item and inter-subject variability that is there, right? So for example, amongst the translators that we had, they would have different competencies. So there will be variations in terms of inherently how slow or fast they are when they are translating from scratch, for example. But also there will be some variability in how they adapt to the change in condition. So someone might adapt better, others might adapt worse. Similarly, not all linguistic items or sentences are created equal. So there is some variability over there as well. So using these kind of models helps us account for that variability and makes our results therefore more acceptable and more generalizable. So this is just an example for the speed for the speed when we were measuring the speed of the task, the kind of equation that we used. So let's quickly dive into the results. So the results on the first dimension, which is the temporal dimension. And as you can see on the graph on the right side, what we see here is that in the HT condition, or the translation from scratch condition, we saw an average throughput when averaged across all translators of about 350 words, which increased to about almost 900 words or 960 words in the post-edit condition. And this is an overall productivity gain of almost 172%. And you can also see a lot of variation in the productivity gains that different translators have made. The table on your left kind of provides more insight onto why that might be, because over here, what we have done is that we've given you the percentage of segments from machine translation that were just accepted as is without any kind of edits. So when you accept it, then obviously it leads to faster translation times. But it also raises then questions about the quality of the end translation that's produced, which we do check later on for. So the key thing over here is that we see a huge productivity gain of 172%, which tests highly significant according to our mixed model results as well. The next dimension, which was the technical effort dimension, over here we measured the number of keystrokes that were used per source character to generate the target text, right? So we normalized it according to sentence length, measured as per the number of source characters in the sentences. And over here, again, we see that in case of the HT condition, you have almost 1.33 keystrokes per source character being used, and which drops to 0.54 in the PE condition, which leads to a technical effort reduction of almost 59%. And this is in line from what we have seen in previous studies on other languages as well, where high quality MT exists. This was the technical effort reduction estimate that we had. The table on your left, what we also did was that we classified all these keystrokes into different categories of content, navigation, and deletion. The idea being that in case of post editing, there will be more deletion and navigation going on rather than more new content being added. So, and that's what we see according to the percentages in these two tables, that a whole lot more deletion and navigation on the post edit side, whereas a lot more content keywords on the HT side that we see over here. And finally, the cognitive dimension, which is the hardest to estimate, and we actually use 3 different indicators for this. Since we were not doing an eye tracking study and we had all this keylogging data. So the first thing that we did was we calculated the number of pauses per segment, and the intuition being that more the number of times a translator or a post editor pauses, the more cognitive difficulty they might be having in translating that particular or post editing that segment. And how do we define a pause? It's defined based on a particular threshold. In our case, it's 1000 milliseconds, which is also backed up with some previous study, and literature suggests that this is a good cutoff threshold. We experimented with a couple of other thresholds as well, but this turned out to be the best for our purposes. And over here, again, we see that there is a reduction of almost 31 pauses per segment in the human translate condition to 12 pauses per segment in the post-edit condition. So the number of pauses that we are seeing in the post-edit condition is a lot less, almost 63% less than what we see in the HT condition. Does that mean that there's lesser cognitive effort? That's what the indicator says. But then for some contrast, we studied a couple of other indicators as well, this time in terms of duration. So we break down the duration as to how long these pauses are. The previous one was frequency, but now we look at the time duration of the pauses, and we classify them into 2 kinds of pauses. One, what we call an initial pause duration, and this is the amount of time that a translator takes before when they first see a segment appear on their screen to when they first start post editing on them. The intuition was that in the PE condition, since you have to comprehend 2 segments, the source segment as well as the machine translation proposal, you would take longer perhaps. And we do notice a slight increase of about 5%, but I think it is also kind of being negated by the machine translation proposal acting as a prompt. So which is why we didn't see as big a difference as we expected initially for this. And I think some eye tracking kind of studies might help shed some more light over here in terms of how long does it take for comprehension of those segments in either of those conditions. Then we also had pause duration, which was the mean pauses for the remaining duration after that initial pause. And this also shows that a slight increase in the PE condition. So essentially the behavior that we are seeing is that there are fewer pauses in the post-edit condition when something is being post-edited, but these pauses are longer. So overall, a little bit longer than what you see in the HT condition. And one way to summarize would be that the translator in the post-edit condition takes a long pause, but once they have taken that pause and begun their activity, they get through that task quite fast in the ST condition. So that's in terms of the mixed effect models and the significance of these results. This is what we did. For the fixed effect segment length, you can see that it's positively correlated as segment length increases. Both the temporal effort, technical effort, and cognitive effort increases. For the post-edit condition, this is what we were studying. It's negatively correlated. So when you are post-editing, it takes less time, it takes less effort, and in terms of the number or frequency of pauses, the cognitive indicator, again, it takes a less cognitive effort as well. This is as per the mixed effect models. Finally, the translations that were generated in either of those conditions, we did a pairwise quality judgment on those. So it was a small sample size, and we made sure that we sampled from all the translators that were part of the study. And each human translated segment was paired with a post-edited segment, and 5 other evaluators who were separate from the original post editors and translators that we had for the study were asked to rank those or present quality judgments as to the translation quality. And you can see that they stack up quite similarly. The differences are not significant. They did not test to be statistically significant. So we can say safely that the quality is perhaps comparable in both the conditions. And finally, you can also see the correlation of the more popular MT evaluation metrics like Blue TR and CHRF with these indicators. And the interesting bit over here is that they correlate most strongly with the technical indicator, then the temporal indicator, before they fade away a little bit for the cognitive indicator. And this also, I think, is apparent because the technical one is the most surface one of the post-editing indicators, whereas the cognitive one is the one that's most indirect. So that was about the quality evaluation. So the research questions that we posed, so these are the answers that we got, that yes, we do see a huge reduction in terms of temporal, technical, and cognitive indicators for post-editing on the English-Hindi pair. The quality of the segments in both the conditions seem to be equal, and correlations get stronger along the cognitive, temporal, and technical dimensions. So the next steps, I think we realized that the quality evaluation was based on a smaller sample size. So we had about 50 or about 60 pairs that we evaluated. So we might want to do that ranking exercise again with a larger sample size. But we do see other options as well in extending this, where include another machine translation engine and see what the quality differences of the engine as indicated by the metrics translate into post-editing effort. There has been some previous work in this direction as well. And then, of course, add more languages. We started out with a single language pair, but very much would like to study between Indian languages. How does this pan out? And these are just some examples that were generated in either. So for the same source sentence, you have these 5 translations given an empty proposal in the PE condition. So you can see over here what kind of post-edits were generated. And similarly, the other 5 were without an empty, which was human translation from scratch. And over here, again, very interesting results in terms of the differences in translations that you see in both the conditions. So that's about it. So thanks a lot for listening. And if there are any questions, I'll take them now. Thank you.
Arafat. So, any questions?
I have a question. So thank you for the presentation. So it's a lovely study, really nice. Do you think it would be an idea to have a study where the human translators have access to translation memory and compare that with machine translation?
I think yes, and I think people have done that where the third condition is the condition of any kind of CAT tool, either paired with an empty engine or not. But we would very much love to do that in the Indian language scenario as well. But yes, that's a very valid scenario as well to show whether machine translation on its own, how much does it help versus the use of CAT tools.
Yes, any more questions from the participant audience? Okay, so there is no question. So thank you once again, Arafat. Thank you.
Thanks a lot. Thank you. Thank you, everyone.
Okay, so next paper title is an experiment on speech to text translation system for Manipuri to English on low resource setting. So presenter is Sanaya Meti. Can you please share your slide?
Yes. Hello, am I audible?
Yes, you are audible.
Is my screen visible?
Yes, it is visible.
Good afternoon, everyone. I'm Dr. Sanay, currently doing my PhD in NIT Silchar. Today, I'll be presenting our work on speech to text translation for Manipuri to English on low resource setting. So this presentation provides the overview of our work from different aspects. First, we have introduction, followed by problem statements, then contribution, and then methodology where we will discuss our approach, then data calculation, and the experiments that we have carried out, and finally conclusion and the avenues of our future work. So basically, machine translation can be defined as a automated system that analyzes text in a source language and then applies some computation to it to generate the target language without any human intervention. So, for example, we are using MT system text in source language English is machine translated to a target language Manipuri. And following are some of the commercially available machine translation systems that includes Google Translate and Microsoft Bing, and we have RTL. So all this system can be helpful in building a reasonable synthetic MT parallel dataset. But however, for low resource language, there is no such system available. So you can see that in the current trend, the MT resources are mainly concentrated on a few well-studied languages with limited attention to low resource constraint language pair. So, and especially for low resource languages, the MT system suffer from the lack of training data set, and more so with the involvement of multiple modalities. And lack of professional translators for low resource language is also a major challenge. And at the same time, it is also time consuming compared to other major languages. In this work, we collected a monumental dataset from all local daily newspaper and built a dataset for an extremely low resource language pair, which is Manipuri in English. So, and we also collected speech record for the source language Manipuri. And using this dataset, we carried out an experiment to evaluate the performance of the speech-to-text machine translation system for a language pair. Okay, next we have this figure shows our overall methodology. As we can see, at the initial step of our work, we have English text dataset collected from the news articles, which is machine translated to the Manipuri language. And in the next step, we have speech is recorded for the Manipuri text. And this overall collected dataset is then used to train using two approach. The first one we have a pipeline approach, and next we have end-to-end model. So in the pipeline approach, we have two content-related system, an ASR model and the MT system. And then in the end-to-end system, we use a speech encoder and a character level decoder to get our final English text output. So we will discuss more in the further in the section. So this is the approach that we have collected our dataset. We collected our dataset reported in English from Ifal Free Press, which is a local daily newspaper based in Manipur. So from the website, we scraped this news articles where the title references of the news articles. It is treated as a caption for the image present in the article. So we have collected image for our future. For now, we will use only the text dataset. And these articles are collected using our custom scraper with nows. Here are some of the steps that we have used as data processing steps. Include some of the removal of unnecessary filters and filtering the multiple spaces. So in the building our dataset approach, we follow an incremental approach where the English text dataset is machine translated using a PVSMP system of of English to manipulate system, and which is then posited, and again the positive data is used to retrain the system in an incremental approach. So to get a brief idea about the possibility, here we have English text which is fed to our empty PSNP system, then which will output the text in the Manipuri. So as we can see here that the output requires correction. So to get the our final desired target output, so we use the English text and the Manipuri output and as a translation memory, and it's fed to a positing tool. In our case, we use the MATLAB tool, and later after positing, we will get our final posited Manipuri text. So using this generated parallel dataset of English tool and posited dataset, we again retrain our system, and this task is repeated until we get our final collection of the dataset. And following the development of the parallel dataset, we also recorded speech is recorded for each of the Manipuri sentences by the native speakers of Manipur. And the total number of participants for the speech records is 5 one male speaker and 4 female speakers. And also at the same time, any embedded speech found is again recorded to collect the quality speech record of the 4 experiment. So overall, the dataset that we have collected is comprises of 5,300 Manipuri to English parallel dataset text, and speech records it comes around 5 hours to 5 hours and 30 minutes. So as we have explained earlier, we use two approaches. One is a pipeline approach consisting of ASR system and the machine translation and the end-to-end speech text translation system. So in the pipeline approach, we use male frequency structure coefficient MFCC, which is used to as audio features for the ASR system, and the same is also used for the end-to-end speech text translation system. And in our pipeline system, the model consists of two individual models. We have automatic speech recognition system and then neural machine translation system. And again for the ASR system, we experimented with the two separate models. Okay, and the first one is the Gaussian mixture model, and the second one is the time delay neural network. And after getting the output from the ASR system, it is fed to the NLP system to get our final desired target text for the entire pipeline system. As for the end-to-end system, we follow the Virat architecture and attentive encoder-decoder model, and we use the FairSec speech-to-text tool which was released in 2021. And in the model, the speech encoder takes audio features as an input sequence, which are fed into two non-layer 10H layers, generating and just size features. And later, in the decoder we have LSTM with a global attention mechanism. The decoder generates the target language sequence at the character level. So in the system design, we have the training and development and the test dataset for speech translation models. Is shown in the table 1. And for the NNT systems, we train two separate systems. One is the NMT-IN, which is the model trained with end-to-end dataset as shown in the table 1, and another with the NMTG, which we will indicate as the NMT training in the general domain, which is a combination of in-domain and the additional parallel dataset collected from the TDIL and the Vikas area. And the domain comprises of agriculture and medicals domain. So based on experiment, we evaluate the ESR systems in terms of what frequency rate and the final hypothesis of the transition from the pipeline and the end-to-end systems in terms of blue score. using Scrabble. From the table, we can see that the TDN model performs the sorry. From the table, we can see that TDN model outperforms the JM model with an improvement of 2.53 WER rate score. And as for the final MT output, the pipeline model with the TDN ASR and plus with the NLP system with the train in the domain model outperforms the remaining systems. And also, the result also shows that the usage of additional dataset where the size of the domain is substantially larger than the in-domain dataset has a negative effect on the score. As we can previously see that only in the in-domain we use only 3,310 dataset, whereas the additional dataset is 19,000 around. Next, we also did a qualitative analysis of the monetary ASR systems. In the table, we can see the sample input and output from the monetary ASR systems. We have we have selected different examples considering some of the linguistic features of our Manipuri system, language. So in the transcript one, the word highlighted in the green is read as home super, which is generated in this meaning third. Okay, and it is generated in the neutral form by the GMM XMM, whereas in the TDNN it is correctly transcripted. And so from this we can see that now, although both the efforts uses the same speech features, the TDNN ASR system performs better in the n-gram match. And in the latter cases, we have the words highlighted in red in the ASR output, so the incorrect generated transcript of the word highlighted in the green. So from the sample results, it is observed that the ASR system suffers from the word containing B, the one shown in the transcript 2 and the transcript 3. So both contains the word but B, the phoneme B. So and one more case is we can it is not to note that the Manipuri in Manipuri a single phoneme could be represented using different graphemes in the Bengali script. So one such case is shown in the transcript 3. So where the ASR system generates the word transport as the using in this form. Okay, and then okay. So although these two yeah, the characters are different, both the spellings are correct. And in transcript 4, we have the word Imphal, and here also the same case we can see that the one highlighted and green and the olive both are the correct representation of the word Imphal. In the latter cases, the joined words are generated separately. So these two, mainly these two cases on the transcript 3 and 4, as we can see that as we know that in the automatic evaluation metrics, it is computed at the word level. So the cases highlighted in the transcript 3 and 4 can often lead to low evaluation score. Going further, we have analysis of our manufacturing English system, is a speech-to-text translation system using at the sentence level. So in the figure, the figure shows the analysis based on the number of sentences with respect to the blue score. As we can see that the majority of the translation of the end-to-end model is observed to score a blue score of less than 10. And as compared to the translations generated by the pipeline model, the one highlighted in the green and the blue. But however, it is interesting to note that the high score level blue is achieved by the end-to-end model. So even though the overall performance of the pipeline model performs the end-to-end model significantly. At the same time, we also evaluate the performance of the systems with shorter and longer sentences based on the length of the reference length. And the result in the figure, we can see that the systems, all the systems performs well with the longer sentences, and while the sentence with the length below 20 scores a blue score less than 10. So from this two analysis at the sentence level, we can see that only very few samples achieve Blue score above 50, and from this we can conclude that the massive amount of effort is required to for the development of the Manipuri to English speech text translation system. Apart from the automatic evaluation, we also carried out the human evaluation on our test set. The adequacy and fluency ratings are reported by our human evaluators are shown in the table. So among the translation systems, the pipeline model with the TDNN IN except the highest adequacy score, and the adequacy scores of the systems are also to be in correlation with our automatic evaluation score. However, our the fluency scores of the to be non-correlated with the automatic evaluation. And in terms of evaluation, the end-to-end model achieves the highest score. So this indicates that despite not preserving the information of the source language, the system is able to create a fluent text. So in coming to the conclusion, we have a comparative study of the conventional pipeline model and the end-to-end systems of speech-to-text translation on an extremely low resource language and to English is investigated. And using the NMT, and we from our experiment, we also know that using NMT systems trained with dataset from mixed domain results to decrease in the automatic evaluation score. And though the end-to-end speech-to-text translation has various advantages over the traditional pipeline model. The limited size of our dataset led to the poor performance of the end-to-end model as compared to the pipeline model. Here are some of our references. Thank you.
Thank you, Sanaya. So, any questions from the participant? Professor Joseph, okay, so carry on.
Sanaya and Alok,
Yes.
nice work. It's lovely. In pipeline system,
Yes.
which component is the bigger bottleneck? Is it the ASR or the machine translation, or is it both?
From our experiment, we can see that machine translation is the bigger bottleneck.
Yeah. And how do you see that?
How is that? We can see that if we go back to the, let me see the slide. So in a NMT system, yeah, okay, we have done it is not included here, but we have concluded that the separate training from MT system to NT system without using this ASR record, the blue score is almost comparable.
Ah, okay. Yeah. Thank you.
Any more questions from anyone? Okay, thank you once again, Sanaya.
Thank you.
Okay, so next presentation. So the topic title is on the transferability of massively multilingual pretend models in the partext of Indo-Aryan and Tibeto-Burman languages by Salam Michael Singh. So are you there?
Yes, sir. I'm here.
Oh,
Am I audible?
yes, it is audible.
Okay.
So
I'm sharing my
please share
screen.
your slide.
Yes. Is my screen visible?
Yes, but no content.
Okay, let me reshare it again. Is it visible?
Yes, now it is visible.
Okay.
Yes.
So hello everyone, my name is Salam Michael Singh, and today I would like to present my paper titled on the transferability of massively multilingual pre-trained models in the pretext of Indo-Aryan
Michael,
and
make the screen full screen.
Please make it full screen.
Make your presentation full screen.
Actually, I've made my full screen in my system.
Slideshow.
Now?
Slideshow. Slideshow.
Yeah, I've made it. I'm enabled.
Share your entire screen.
Actually, I've shared it.
If you click to the slideshow and presentation.
Okay. Is it okay now? Hello, am I audible?
Yes, you are audible.
And my screen?
Screen is coming, but it's half.
Yes,
Sound is fine.
Okay. So my name is Salam Michael Singh, and the title of the paper is on the transferability of massively multilingual pre-trained models in the pretext of Indo-Aryan and Tibeto-Burman languages. This paper is worked together with Loitombam Sanaya Maitai, Alok Singh, Tautam Dharan Singh, and Shivaji Bandyopadhyay from National Institute of Technology, Silchar, India. These are the overview for my presentation. First, I'll give the introduction of the machine translation, followed by the motivation behind the work. The next section, I will give the contribution, followed by the briefing of the pre-trained models that are used, and which is followed by the data set and pre-processing. In the next slide, the experimental setup and the results are presented, and then I'll conclude the presentation. So machine translation is a task of translating from one human language into another human language, and it is considered to be hard as there are multiple issues, such as the different languages have different word orders, such as subject object verb agreement, and same sentence can be said in multiple ways. Now, the motivation behind this work is that most of the languages faces non-availability of parallel data, which is crucial for the machine translation, and acquisition of the parallel data is expensive. And some linguistic tools such as the POS tags or the name entity recognition tags, they are not available for most of the languages. So, and maybe we can infer from higher resource languages through a multilingual scenario, and which is evident in recent success in the massively multilingual neural machine translation models. However, these models are computationally costly to train. So we can leverage the transfer learning from these pre-trained models into the scenario of the low resource translation. So the contribution are as follows. We explore the effectiveness of the transfer learning from the large-scale pre-trained models for the low-resource machine translation task, and we transfer into, to be specific, we transfer into the unseen languages which were not present during the pre-training steps, and we investigate the relatedness of the effect of the relatedness of the languages in the pre-trained models as well as the fine-tuning step. And finally, we also investigate the robustness of the fine-tuning from this large-scale pre-trained models into a general domain, using a general domain test data. We use MBART50 and MT5 pre-trained models. These are massively multilingual pre-trained models. So MBART50 is pre-trained using 50 languages using the BART objective, which follows the denoising of the multilingual and fine-tuning in these respective translation task. And the MT5 is also a kind of pre-training, but here the pre-training involves multiple different tasks in a multitask scenario, and the task is, and the decoder is conditioned to generate the task outputs as a sequence of text. So we consider the Assamese English to Assamese, Bengali, and Manipuri languages. Translation of English to Manipuri, Assamese, Bengali, and Manipuri. So Bengali and Assamese belong to Indo-Aryan, while Manipuri is a Tibeto-Burman language, and only Bengali language was present during the pre-training step of the MBART 50 and MT5 model, while Assamese and Manipuri were totally absent during the pre-training steps. So we use publicly available parallel corpus, a multilingual parallel corpus from PMI and CVIT PIB for training, while for our evaluation and development, we use the PMI dataset for Assamese, Bengali, and Manipuri, as Manipuri is not, as publicly available Manipuri test set is not available. So we make a subset from the PMI dataset. And for the Bengali in inclusion to this PMI test set, we also use the WAT 2021 and the Flores 101 test set. So WAT 2021 is in domain with the training data, while Flores 101, which has the Assamese, Bengali, and English data, this is a general domain data. Now, these are the stats for the statistics of the dataset that were used. And for the data pre-processing, it involves the tokenization and normalization. For the English, we use the openly available Moses toolkit, while for the rest of the languages, we use the Indic NLP. And for the creation of the dictionary, we learned separate BPE using sentence piece of 3,000 merge operations from each of the languages independently, and we merge. Actually, we took the unions of tokens from each of from those sub tokens as the dictionary, as a common dictionary. For the evaluation, we use both the automatic and the human evaluation. For the automatic, blue is used. So the blue, we use the Sacker blue, and the blue is computed on the detokenized text. For the English, for the English side, we use the Moses tokenizer to detokenize, and then Indic tokenizer is used for detokenizing the output into its normal form, and we use the and for the human evaluation, adequacy and fluency matrices are used, which ranges from 1 to 5. And we computed the human evaluation score across the 3 translation directions, that is from English to Assamese, English to Bengali, and English to Manipuri, for which we outsource two translators each from each languages, and we make the average as a score. Now, as far as the experimental setup is concerned, the first baseline is the simple one-to-many model trained from scratch, which is a shared transformer decoder encoder with 6 layers, and these are the some of the details for the hyperparameters that were used. And for the MBART 50 and the MT5 base, we use the default settings as reported in the paper. The MBART 50 was fine-tuned using the FairSec toolkit, while MT5 was fine-tuned using Hugging Face. Now, this is the first experimental result, which is tested upon the PMI test set. So here we observe that across all the translation direction, both the pre-trained model, both the fine-tuning, fine-tuning over both the pre-trained models in a multilingual scenario, in a multilingual setup, is superior than the one-to-many multilingual model trained from the scratch. We have also compared with the NDIC-BART and the one with Samanatha, which is a paper by Ramesh et al. So in for this one, we evaluate our score on what 2021 and Flores test set. So for the what 2021, we observed that MT5 plus fine tuning over the MT5 in a one-to-many setting is superior than all the other models, while training from the scratch is the least. And this in this setting, this indic bar is also is also a massively multilingual pre-trained model, but the difference between this indic BART and MBART is that indic BART uses only the Indian languages for the pre-training and for the fine-tuning step, while MBART uses a mixture of different languages for the pre-training step. So one can one can argue that this should have technically given better result than the other models, as this is using only focusing on it is only pre-trained and fine-tuned both only on the Indian languages. So this may be due to the fact that this arises a question that whether the relatedness of the languages involved during the pre-training is really important, or the number of languages, different languages pre-trained is more crucial. Or it may be due to the fact that in the fine-tuning step, we fine-tune using only 3 languages. So there may be a case of like a negative transfer in the indic BART, and which led to the downfall in this score. While on the general domain test set, the difference that indic BART has produced is substantial. It is due to the fact that our system was trained only on the PMI and CVIT dataset, which is mostly news domain, while the indic BART was also pre-trained on multiple dataset, and most importantly, it has also used the parallel Samananta dataset, which has the largest publicly available Indian dataset. So this may be due to this. So this is the reason why it is working so well for this general domain data. And this also makes this also puts some kind of like intuition behind that our model may be like heavily biased with only these 3 languages only. And we also fine-tune the model, both the pre-trained model using the Flores depth set for some more additional update steps, and see whether if the performance improves. But the performance just stalemates. So this suggests that just randomly fine-tuning from pre-trained model is not that effective. So rather we can include more general domain data during the pre-training and the fine-tuning step. So these are the human evaluation scores, and this correlates well with the automatic score that we have seen. So here we find that the pre-trained models perform much better than the models which was trained from the scratch. So for the conclusion, the transfer learning from pre-trained model outperforms the one-to-many model trained from scratch across all directions, and this suggests a strong transfer of interlinguistic information from the pre-trained model, even for unseen languages. And these are the references that I've used. So thank you. With this, I conclude my presentation.
Thank you, Salam. So any questions? Okay, so I have only one question regarding the human evaluation. So you have evaluated like around 3 score. So is it good, bad, or what?
Sir, can you just repeat your question once again?
Yes, the question is that you have evaluated human evaluation.
Yes, sir.
Given score. So that score is good, bad. How can judge that part?
Actually, we have scored it from the range of 1 to 5 scale. So based on that, they gave their own score for each sentences, and for all the sampled sentences, we averaged score.
Okay, thank you. Thank you, Salam.
Thank you, sir.
Any question? So now we can close the session. No more papers are there. Okay, so thank you all participants. Okay, so next maybe 6:30 to 7:30 there is an keynote lecture. So all participants are requested to attend that one. Thank you.
Okay, so we have now tea break. Then the next 7:30 we have a keynote lecture, mental health as an applications area for natural language processing, prospects and challenges by Professor Philip Rancic. Okay, so we'll again meet at 7:30 the same
6:30,
link.
sir, 6:30. Keynote talk is at
6:30 to
6:30.
7:30.
So the next keynote talk will start at 6:30. Keynote talk on mental health as an application area for natural language processing, prospects and challenges by Professor Philip Resnick. See you at 6:30. 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 CM 630. 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 Yeah. Welcome to Professor Philip.
It's muted. Can you hear me okay?
Yes, you are audible.
Wonderful. So I guess we're on a break and just getting set up. Is that right?
Okay, so you want to share your screen?
Yes, please. So let me get my. Let's see. Here is the PowerPoint.
So click on share button.
Yep, I'm going into presenter mode in PowerPoint. Nope, that's not going to work. Bear with me 1 second. Let's see. Back to WebEx. And the share button. And I need to apparently open my system preferences and allow it to share.
So you click on that screen on left side, there is a one button, a screen one, entire screen you share.
Yeah, no, the problem is that my system has not given WebEx permission. Oh boy, okay. So I'm on a Mac. It told me that I needed to give WebEx permission to share my screen. The problem is that in the place that it's gone, allow them to record the content of your screen. No, I don't want, oh, I see. Okay, so wait 1 second. It's just a privacy setting. Okay, so WebEx. Yes, okay. It says that I need to quit and reopen. I'm giving it permission to record. It's requiring me to do that for some reason.
Sir, just 1 minute. Just you follow my instructions. So so in the WebEx at the bottom you can see the share button, right?
Yes.
So click that.
Yes, it says allow WebEx to share your content, grant access and system preferences.
Left side. No, left side you can see there is one screen one is there. One pop-up window come na. One pop-up window come.
I can see in my camera. Yes. No, I'm sorry. It's let's see if I go there. I'm sorry. When I say share, I don't think I'm seeing what I should be seeing. It's required. It pops up saying allow WebEx to share your content, and I have the grid of various people participating. So where should I go from here?
Yes. You can click on share button, sir. We'll see.
I'm sorry. Say again.
You click on share button. We can see the screen. Your screen.
You can see my screen?
No.
I hit the share button, and it gives me a pop-up that is saying open system preferences.
No. Come again, sir. What is happening when you click on share?
When I click on share, it opens a pop-up window that says.
Yeah, in the pop-up window, left side there is one small icon like screen one.
No, there is that pop-up is not what I am getting. I'm getting a different pop-up that says open system preferences.
Oh, open system preferences.
All right, I'm gonna see if I can change my preferences to give WebEx permissions that it did not have before. It's requiring me to quit and reopen WebEx, so I'm gonna go ahead and do that. I'll be back in just a second.
Okay, sir.
Again, can you hear me?
Yes, sir.
Okay, now it says recording in progress. Let me see if I can share my screen. I gather you are recording these? No, it is still telling me to open system preferences. Yeah.
Notice, sir?
It's requiring me to quit and reopen again. I will try doing that. Wait 1 second.
Naresh sir, can you hear me?
Just barely, yes.
So again, you are getting the system preferences.
What it's allowing me to do, what it's trying to do is get me to change my system preferences to allow WebEx to record my screen. Let's see, I made the change. Let's see if it will now allow me to share my screen. No, all I keep getting is the same pop-up when I try to share that says allow WebEx to share my preference, allow WebEx to share your content. I recommend, if somebody has not already done it, download the slides that I sent in the email so that we have as a fallback somebody else being the presenter. Say next slide. Because right now unless you know something I don't about WebEx, I do not appear to be able to get to share the screen.
Just I'm giving permissions like you are the presenter. Now you can see.
Okay. Let me know once you've given me those permissions and I will try again.
Naresh sir?
Yes.
Okay, so we are audible from here, right?
Yes, yes.
Okay, okay, sir.
And me?
Yes,
Yes.
although you're very quiet.
Okay.
Okay.
Now you try to share, sir.
Yeah, we've got a couple of minutes. Have you given me permission to be the presenter?
Yes, yes.
Let me try sharing. Nope. When I try to do share either in the menu or in the button down at the bottom, it just keeps bringing me the pop-up that keeps insisting that I open my system preferences. And I've checked Cisco WebEx meetings. It's allowing it to share my screen. So I'm honestly not sure. I'm gonna exit and come back in one more time. And other than that, because I believe we're coming up on the start time.
Otherwise, you share your PPT with Doran Singh.
I sent a link to my PPT, my PowerPoint. Yes. Does somebody have it and they can share and I can speak?
Yes, you should.
Okay. So I'm going to leave the meeting and come right back one last time to see if I can make this work. Okay. Is that okay?
I have got. I have sent the link.
Doran Singh's voice is getting echo, whereas that Nazmul otherwise are okay.
We'll join again now. Yeah. Hello. 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 Ini download itu kan lagi ada yang lo. Download itu kan lagi ada yang lo sih. Mai PPT download itu ni aku berah. Jarmila saya mai gila ni. Tunggu dulu. Ha. Kau boleh ambil tu. Ini biar kayak ni. Kan download tu dah. Download tu dia tu. Open a new window.
Hello again.
Hello, Professor Resnick.
Yes, sir.
It's working now.
Thank you very much.
Oh, great, great.
Oh, that's nice.
Let's see if I can do this successfully.
Oh yes.
Yeah.
Okay. Can you see PowerPoint?
Yes, yes. Go to the presentation mode.
How's that?
Yes,
Ah.
perfect.
Thank goodness it only took about 4 tries.
Yeah. So we, in fact, wanted to show you the campus tour of NIT Silchar before we start your presentation. Since we could not come down here in physical mode, we just want to show you how our campus looks like. So.
Oh, thank you. Except that I've got PowerPoint on my screen now. When are we starting?
It's a 4 minutes video, so we will just have a look of that campus tour.
Okay. Well, I'll go out of presenter mode so that I can see that.
Yes, exactly that will do.
Doran sir, can I start?
My screen is blank.
Yes.
No, there we go. Application sharing is ending. Yes, I should be able to see now. Thank you.
Yes, please. Please start the video. Naresh. Naresh? Naresh, can you hear me? Can you hear me? Hello?
Hi. You're audible.
Yes,
Yeah,
so-
but it's very faded. I mean, I can't hear very clearly. I don't know about others.
Okay, so in fact,
It's very.
So we just want to welcome
Azmol?
Joseph, and we want to felicitate Professor Joseph with
sir.
traditional Japi
Voice is very low.
of the.
Voice is
Very low.
Yes. So we want to felicitate Professor Philip Leshney from University of Maryland with the traditional Japi of this region, and we also felicitate with a gamocha and a buki. With this, I want to give a brief introduction of Professor Resnick. So, Professor Philip Resnick is a professor at the University of Maryland in the Department of Linguistics and the Institute for Computer Advanced Studies. He earned his bachelor's degree in computer science at Harvard and his PhD in computer and information science at the University of Pennsylvania. Prior to joining UMD, he was an associate scientist at BVN, a graduate summer intern at IBM TJ Watson Research Center, subsequently awarded an IBM Graduate Fellowship. While at UPenn and a research scientist at Sun Microsystems Laboratories, Resnick was named a fellow of the Association of Computational Linguistics in 2020. Outside his academic research, Resnick has been a technical co-founder of CodeWrite, NLP for Electronic Health Records, acquired by 3M in 2012. And he is an advisor to FiscalNote, Machine Learning and Analytics for Government Relations, Solo Segment, Website Search and Content Optimization, Conversion, Social Strategy and Analytics, and the Coleridge Initiative, non-profit focused on effective use of data for public decision-making. Resnick's most recent research focus has been in computational social science, with an emphasis on connecting the signal available in people's language use with underlying mental state. This has applicants in computational political science, particularly in connection with ideology and framing, and in mental health, focusing on the ways that linguistic behavior may help to identify and monitor depression, suicidality, and schizophrenia. He has also been ramping up a new area of research in the computational cognitive neuroscience of language, developing models using brain imaging data with a focus on the role of contextual prediction in sentence understanding. Welcome, Professor Resnick. In your session today, there will be session chair. The session chair is Professor Dipti Mishra Sharma from IIIT Hyderabad. Now the session is yours. Stage is yours, Professor Resnick and Madam Dipti Mishra Sharma. Now stage is yours. Now the stage is yours, Professor Resnick. And today's
much.
yes, and today's session chair is Professor Dipti Mishra Sharma from IIIT Hyderabad. Madam, please go ahead.
Thank you very much. So the first question is how to now once again to see if I can successfully share my presentation. Please bear with me one moment, since it appears to have disappeared. Nothing like a technical presenter and a technical audience for all possible challenges from a technical perspective. There we go. And presenter mode.
Yes, it is visible.
Thank you so much. Well, let me begin by saying thank you so much for the kind invitation What a beautiful campus. We're still in a remote world, but I do appreciate the chance to have gotten a chance to see the video and see what the campus looks like. It's really quite beautiful. So I just also want to thank you for inviting me to speak. Today, I'd like to speak with you about mental health as an application area for NLP. Before I begin, I'd like to emphasize that when you give a talk about mental health and certain issues in mental health, this can raise challenging issues for some people. This is a difficult time. And so I always like to begin talks by pointing out that there are resources available to help people, particularly on university campuses. This slide is rather U.S. centric, but if you notice in the last bullet, there's a pointer to a source of information about ways to get help worldwide. And so, you know, if there are concerns or issues, please bear that in mind as you listen to the talk, and don't feel obligated to continue as I speak if it's not a good fit for what you need right now. So let me begin by pointing out that mental health, mental illness, is a huge problem. What you see in this table is the costs of various non-communicable diseases. And this is in trillions of US dollars. And the thing to note is that in that second to last column, mental illness, the projected cost from 2011 through 2030 of mental illness is the largest number in this table, even taking into account cancer, respiratory disease, cardiovascular disease, diabetes. It's more than diabetes and respiratory diseases and cancer combined. And here in the US, and it's worse in other places in the world, even if you know that you have a problem of some kind that needs to be addressed in mental health, it is very difficult to find a mental health care provider. Literally a third of the population in my country are living in federally designated areas where they have recognized that there are not enough mental health providers. In addition, in the United States, suicide has become a leading cause of death for young people. And so this gives you a sense of both the economic cost, but also the human cost of this as an issue. And if it seems like I might be trying to convince you this is important enough for you to work on, that is probably a good impression. I think it's an important problem. And one of the goals of this talk is to help people become familiar with some of this as an application area for their technological intelligence and skills. Now, what clinicians do in mental health, roughly speaking, can be thought of in the categories you see here. So there's screening, where you have a set of individuals, a population. You don't know that they have issues or problems, but you're basically looking to see whether somebody rises to the level of needing attention. If somebody is flagged in that way, then there is some form of assessment in order to evaluate the condition, and if there is a condition, its severity. Then there are interventions of various kinds, which can be pharmaceutical interventions, it can be talk therapy. There's a whole range of ways of intervening when somebody has an issue in a single time or over a period of time. And if it's over a period of time, or even if it's a single time, there is a time period when one is monitoring in order to keep an eye on the status of whatever condition it is that one is talking about. Now, these are really difficult problems, even for the clinicians. I'm married to a clinical psychologist, which is one of the reasons why I've gotten into this as one of the areas of my research. And you know, the whole thing is really very difficult even for them. Just to give you a sense, often the process of assessing or sometimes even screening or monitoring takes the form of a structured interview of some kind. And one of the reasons this is challenging is because there is no single definition like there is, say, in vision, where we have a test of visual acuity and you define, you know, 20/20 vision or something. There are multiple underlying theories and ways of categorizing in the mental health space and in the space of mental illness. Another problem is that clinicians are often going on instinct, right? They have a base of experience and they are relying on that base of experience in addition to formal assessment measures. And this creates an interesting problem because it creates a risk of bias among clinicians. For example, if you have a clinician who comes from a demographic or say socioeconomic or racial group, and they are seeing a patient who is in a group where they are less familiar with the culture, they may have biases that influence the way that they see the patient and assess the patient. In addition, if we're talking about populations and subpopulations, often there is no specialized training for clinicians with regard to particular populations that have their own particular issues. This includes things like military veterans, people with drug addictions, and so forth. Right? Finally, clinicians have a limited window into what's going on with the patient. Typically, they get to see what they see when they see the patient, and that's it. And if you think about how much time patients are spending with clinicians, it's a tiny sliver of a window into their actual experience. Now, all of these problems, of course, are now getting worse. We are still in the midst of a global pandemic, and it is being widely recognized that this is exacerbating mental health as a problem area as people experience stress and anxiety and the additional difficulties of day-to-day living. Now, one of the main points that I'd like to make here is that there is an enormous potential for technology to help. This is a quote from a paper by Franklin and colleagues where they looked at 50 years of research in looking at suicidal thoughts and behaviors. And what they found is that in terms of prediction of suicidal thoughts and behaviors, zero progress has been made in 50 years. This is an area where, I mean, if we look at other areas of healthcare, I don't know, tuberculosis or, you know, pick what infant mortality, pick whatever you want. The idea that there might be a severe problem where there's been zero progress in being able to identify that there may be a severe crisis or problem is just astounding. And so they point this out, and then, and there are a number of other papers that make this argument as well, the clinical community is starting to recognize that instead of the traditional approaches that people have taken, which has been a kind of a traditional psychology-oriented study of risk factors and theory-driven theories of risk, the facts on the ground suggest a need for shifting to machine learning kinds of approaches where you have a lot of data and you build predictive models. Now, let me give an example of this. This is work by Glenn Coppersmith and colleagues, an article in Biomedical Informatics Insights back in 2018. And what he did was he worked with a data set of social media posts from people who had or had not made a suicide attempt. And we'll talk about the fact that he actually had this data in the first place a little bit later in this presentation. But he had data with ground truth, made an attempt or did not, and then used NLP and built binary classifiers in order to predict that basically a label is going to make an attempt, is not going to make an attempt. And you can see the ROC curve here, where you have essentially misses and false positives. And there is, you know, an operating characteristic to this curve that is actually very promising, right? If you look at, you know, say 20% false alarms, right? So you're seeing people coming into the system who actually don't have a crisis or a problem, or not going to be. If you're willing to accept that level of false alarms, you can get extremely high. You're talking about 80 or 90% of true positives. And this is remarkable because in his paper, he does an analysis looking at the typical rates of success by clinicians. And just to take out one particular thing that he points out, if you were to use a typical base rate of 6% as the rate that you're of what's going to happen in the population. In a theoretical population of 1,000 individuals with that base rate, if you use this model's predictions, 40 to 60% of the people labeled as being at risk are in fact at risk and would attempt to go on and commit suicide. This is a factor of 10 greater than the comparable rate if you use the typical rates of success for clinicians making a similar kind of prediction. So I'm making the point that there is enormous potential in the technology. Now let's look at some language and this idea of what the technology is doing. This is an essay written by a college student about their first semester, I think, at college. This is data collected by Jamie Pennebaker at University of Texas at Austin. And you know, you can look here, and a typical binary classification approach will identify, as you see here in bold, things that are likely to be signals. These are features that will contribute to the predictions. But it's actually a lot more nuanced than that. Any clinician looking at this would observe that the things that are predictive here actually fall into categories that relate to things that they know about. So you see here that in blue, some of what you see in this piece of language involves social isolation. You see in green indications of anhedonia, that is the failure to be able to take pleasure in things that you used to be able to take pleasure in. In red, you see things related to vegetative symptoms, that is, things having to do with energy level. Right? So it's interesting. I came to this area of work from work that I was doing in computational political science, motivated in part by, as I said, my wife who's a clinical psychologist, and realized that some of the models that we were using in NLP could potentially be applied to this kind of problem as well. And so some of you are probably familiar with topic models, the most popular of which is latent Dirichlet allocation. I'm not going to go into details on this model. I will simply summarize the most important characteristics of the model. What you see here is a plate diagram for a probabilistic generative model, which is what LDA is. And to translate this into more modern terminology, you can think of each document as a mixture, well, that's the probabilistic way of looking at it, as an embedding, if you will, over some number K of latent categories or topics that are induced from the data. And each one of those latent categories is represented as a probability distribution over the vocabulary. So for example, if I have a probability distribution for a discovered latent category and words with high probability include, health, doctor, nurse, hospital, I might then infer that that inferred category is about healthcare. So one of the things that we did a while back was apply this to a data set of college student essays like the one that you just saw. And so what you're seeing here on the far right are the most probable words associated with 20 categories that emerged inductively from this analysis. The other columns, the regression value column, relates to the fact that we used a version of LDA called supervised LDA that's actually a joint model with some kind of indicator or response variable. In this case, we used the individual score on a personality test related to the characteristic of neuroticism. And neuroticism is often correlated with or comorbid with clinical depression. And therefore, this was an attempt to use this kind of bottom-up technique to identify things that were salient for clinical depression. And one of the things you'll notice that I'm just highlighting here to make it easier to read, if you look at things that are negatively associated with neuroticism, and therefore possibly negatively associated with a depression, you see going to sports games, you see listening to music, you see a category related to going out to parties and having fun. If you go look at things that are more related to neuroticism and therefore by hypothesis depression, you see things like the vegetative symptoms that we were talking about, sleep, night, being tired. And one of the things that you notice here is that by using an inductive model, something that's driven by the text data in an unsupervised fashion, you're actually identifying things that a clinician could look at and identify as relevant. That's the leftmost column in this table, right? Where a clinician could look and say, this is social engagement. This is, negative affect or somatic complaints. By the way, that's a really interesting one. Somatic complaints, 4 from the bottom, which has to do with the fact that when people present with depression, they often don't say, I'm depressed. They often say, I'm itchy all the time. I have headaches. My back hurts, and so forth. But you notice that what you're getting here are things that are particular to this population, right? If you were looking at a population of, say, women who were experiencing postpartum depression after childbirth, their way of expressing these symptoms would be very different. A college student is talking about, when they're talking about being tired, they're talking about being late to class and falling asleep and taking naps. When they talk about anxiety down there toward the bottom, they're talking about being anxious and nervous about tests, right? And stress associated with studying. So the NLP techniques here are enabling us to take an inductive bottom-up step that is specifically giving us information that is relevant to a particular population. And that's something that can be difficult to do when you're driven top-down by the theory. Now, I will point out that there's a problem with topic modeling. In fact, at the Neural Information Processing Systems Conference last week, students and I had a paper entitled, Is Automated Topic Model Evaluation Broken? And you have to realize, as I'm sure you know, evaluation is what drives everything. If you're building a model, how you're going to evaluate it is defining what is considered a good model, and that goes into how you build the model. It becomes the loss function, for example, in neural topic models. And we pointed out that there are 2 major problems with topic modeling approaches in general. One, which we call the standardization gap, which is lots of people using topic models, but the evaluations are incredibly inconsistent with regard to all of the details. Everything from, you can do stuff on related data sets, but the pre-processing, how you do tokenization, normalization, a whole list of things you'll see in the paper can be very inconsistent. And even more important, there is a notion in the social sciences and in science in general of validity. If you're evaluating or measuring something, are you actually measuring the thing you want to measure, that you care about? And there was a history in topic modeling of validating models against human behavior or human judgments that dates back to the 2010s. And then there was this big shift to neural topic models, and everybody's like, neural topic models, they do even better. All of these evaluation scores that we do show that the scores are higher. The problem is nobody, it turns out, had bothered to go back and validate that the scores, when you're doing neural topic models, actually are in fact strongly related to the human judgments. Nobody had validated this for the neural topic models, and it turns out it's just not a good measurement. The standard measurement called normalized pointwise mutual information is just a bad measure for neural topic models. It will tell you that model A is better than model B when it's not, according to the human evaluation metric. And so finally, this relates to a broader problem, which is the notion of curation. So much of the time, we simply take our automated methods and we just think, okay, we're just going to use their output in some fashion. But if the goal is insight and understanding and putting things into categories the way that social scientists do, for example, and that will include things like mental health, then a lot of the time, quite honestly, and forgive me for putting it this way, the output of models can be crap. And so there is a step that often is not taken, which is taking the model and then curating it, transforming it into something where you actually trust it. And so we've been working on taking fully automatic topic model output and developing a protocol for human interaction with the model to create a curated model that is valid and trustworthy. Now, I want to shift gears here a little bit. I've pointed out a supervised method, the stuff that Glenn Coppersmith did. I've talked about semi-supervised, that's the supervised LDA topic modeling. And of course, LDA is an unsupervised method. So we've seen a range of kinds of techniques that you can apply to problems in this space. The problem, as I'm sure you're aware, is that progress depends crucially on data. And data is a real problem. I want to show a contrast here. And this is a problem not just for mental health, but for healthcare in general. On the left here, and this slide is a couple of years old, but it gives you the idea. What kinds of text are people in NLP working with? Well, you've got machine translation. You've got millions of pairs of, aligned, sentences, bilingual text. You can scrape all of Reddit. Here it's 2015. You can go all the way up to the present now, and it's even bigger. Twitter. If you're doing question answering, there are websites that you can scrape and get. It's just enormous quantities of data. Let's look. As I said, it's an old slide, but the points here are still completely valid. Let's look at some recent exercises in work that people have done on shared data sets in healthcare, right? So in semantic evaluation in the clinical space, 400 manually de-identified clinical records, right? Synthetic records in the middle, in the order of hundreds. Even the biggest data set of electronic health records that is commonly used is only 2 million, right? It's, documents from 40,000 patients, all of whom are basically in one area of one medical center. I refer to this as the data crisis in healthcare. Privacy is an enormous issue, but privacy has created enormous obstacles, concerns about privacy, really fear of contravening relevant regulations, some of which are more permissive than you might realize, has actually created an enormous fear of people providing data. And so what happens? There's less data there, and smart graduate students are going to go work on the problems where there's interesting data. They want cool problems, and they want data to work on. And so they go work on other things instead of working on things in this space. So what is one potential way of approaching this problem? I'm going to talk about that in this next section of the talk. Glenn Coppersmith, who I cited earlier, coined the term the clinical white space. It's very evocative. So what you see here is a set of healthcare interactions in red, tick marks for one individual over the course of a year. And you can see that they apparently had 6 interactions with the healthcare system. In blue, you have their social media posts, right? You can see that there is literally white spaces in between their healthcare encounters that are just filled with social media activity. So tapping into the clinical white space in order to better understand what's happening with people and having that be sources other than specifically their healthcare records is a potential approach to trying to make technological on this problem, despite the problems that you have with data. So one effort that that I got started a couple of years ago involved using Reddit. There is a forum on Reddit called Suicide Watch that's essentially a peer support forum. People post when they are feeling potentially suicidal. You also get people posting when they are like they just want to help or they're concerned about somebody else. And what we did was we took that data set and we have now built a curated form of data from that forum and distributed it. I'm not going to go into great detail. The important point is that we had experts in suicide prevention annotate the data according to their assessment on a 4-point scale of the level of risk. And there's a long form and a short form, and we showed the long form is better and so forth. We can talk about those details if you're interested. But the important takeaway is that if you measure chance-corrected agreement between these experts, you actually get, to my knowledge, the first ever reliable set of annotations for suicide risk in social media posts, despite the fact that a number of people have done all kinds of things with social media posts using other things. And so that's a first approach, is you have annotation, right? Another possibility is you obtain actual ground truth data, that is clinical measurements or outcomes, for example, whether somebody made a suicide attempt or not. And that's a fact in the world. That's not an expert's opinion. So Coppersmith was doing this through a process called data donation, where effectively you get people to come to a platform and consent to the collection of their social media. So he elicited on ourdatahelps.org, he elicited data donors. So if I'm somebody who, for example, has lost a loved one to suicide, which is true in my case, as is true for a lot of people who work on technological solutions in this area, you actually would get people to donate. I could donate my loved one's data for research purposes, or I could, I mean, you know, healthy people who've never made a suicide attempt nonetheless could donate their data because controls are important as well. So you'd get people to donate the social media data, and this would have outcomes, including things like whether an attempt was made or a date of an attempt and so forth. Another thing that you can do is get participants to sign up to do that same kind of data donation of their social media data, but also answer clinical questionnaires. So at University of Maryland, we did something in partnership with Our Data Helps, where we had people do a survey every week for 6 weeks and then every month for 6 months following that, where they actually used a clinical questionnaire that was assessing symptoms of depression, and in this study, symptoms of schizophrenia as well. And so now you have what you need, which is the dependent variable kind of data, the stuff that you care about predicting, right? Whether it's events or clinical conditions as assessed using an actual validated clinical questionnaire, and you have the language data to work with. Now, I have to tell you that Our Data Helps was being run by Glenn Coppersmith's company, which was then acquired and is no longer running anymore. But what you're starting to see are more and more efforts to try to do this form of data donation so that you can actually gather in an ethical way with full informed consent the kinds of data that you need to develop technology like this. Now, of course, when you do this and you try to then create shared tasks, community level sets of people working on the same problem, which is the way you make progress, right? I mean, this is, if you think about, say, ImageNet and everybody working on ImageNet and the explosion of progress that took place with that, that's the way you make progress. There is a challenge here, which is these data are sensitive. And so collecting them is one thing. Distributing it out is really another thing entirely. Even if you remove personally identifying information, the data still needs to be considered quite sensitive. And so what do you do about that? The approach that I've been taking to this, which is in line with some things that other people are doing as well, I'll mention another in a second, is reversing the process. And instead of talking about doing work where you distribute data out to researchers, instead you bring the researchers to the data. You build a secure, what's called a data enclave, which is a secure environment where you log in through a virtual desktop. It doesn't even allow you to like copy paste out of the environment onto your local machine. And you do all your work inside the environment and the data can't go out from there. And so we actually did this during the computational linguistics and clinical psychology workshop. I'm working with an organization called NORC. They're a nonprofit that's involved in surveys and data gathering. They actually built this data enclave. They've been doing healthcare sorts of things related to this for years. And we built a data enclave that essentially allows people to log in. You can see the sign in at the upper left, and then SSH to Amazon instances have the full arsenal of machine learning techniques. But then at the upper right, if they want to take data off, they actually have to make a request, and what they're taking off of that platform needs to be reviewed. And I'll simply say, yes, hey, look, we got numbers. We actually got a number of teams participating, 20 originally, ultimately 5 completed the shared task and submitted results to the 2021 CL Psych shared task. And the specifics of the numbers and the tasks and so forth are far less important than the fact that we actually did all of this inside a secure environment for the very first time ever for a mental health task. Similarly, I'm on the scientific advisory board for an organization called the Coleridge Initiative, which has a data enclave. They call it the Administrative Data Research Facility. And they are doing similar sorts of things. They run Kaggle-style competitions, in fact, with sensitive data. And so this is a trend that you are starting to see now. Data enclaves as a way of addressing the need to work with sensitive data in a way that respects privacy. And I think this is going to be a very important thing as we move forward toward the future. And we're trying to figure out ways of making this a larger scale, sustainable process, because of course, running these enclaves is something that costs money, it requires support and so forth. Now, the last thing that I want to talk about is the following question. Suppose that the technology, right, was doing really good things in terms of its traditionally measured performance. Then what? A suicide prevention expert introduced me. In a conversation, the then what question came up, and her name is Michelle Kushuk. I kind of always footnote her because this is a great question to ask. Don't just think about the technological problem that you're solving and build it. I always ask my students, boom, snapped my fingers. Suppose your technology works wonderfully well, better than you expected. Well, then what? What's it good for? How do you use it? So many people work on narrowly defined problems and don't think about where it fits into the bigger picture. And these days, when you think about things like fairness and ethics and accountability, you have to think about the broader context in which technology is going to play a role. Now, what about the then what problem? Here in the US, it's a huge problem. Suppose all of this technology worked. Suppose we could identify risk of suicide or risk of a psychotic episode or major depression. We already don't have enough clinicians to handle the people we know about who have problems, right? Forget about false positives. What about when we're detecting more and more true positives? This creates an argument that the traditional thing we do, which is looking at this as a predictive modeling binary classification problem, is the wrong way to go about it. Because if you have limited resources, it's not enough to identify a large pool of people who are all labeled, yes, you are a positive instance. You need to find some finer grained way to prioritize. We can't take a technologically centric view of the problem where you're simply labeling people. What you need to do is take a clinician centric view of the problem where from their perspective, it's not about labeling people. It's about having a pool of people that you are screening or monitoring. And in all of this, we'll be talking about monitoring people who are already in treatment of some kind. And you need to prioritize who needs the most attention. And if you have multiple sources of evidence, like you have their social media posts or other information about individuals, you can't look at everything going on with an individual in every one of those blue tick marks over a long period of time. You need to decide which pieces of evidence are the most important to look at in order to assess what their priority should be. And you need to do this in a way that gets you the most people who are at the most severe risk at any given time. So I want to very briefly mention two approaches that we are taking to this. One is work by my PhD student who's now graduated and working in Amazon in their healthcare group. His name is Han-Chin Shing. The approach, so he took the approach of using a 3-level hierarchical attention network. This is just, the way to think about this is a deep network with attention at every level. And the important thing about this to note is that when you are using this in a classification setting, you only get a label at the level of the individual, even if what you have is a set of texts like social media posts about the individual. So it's a model that goes from words to sentences with attention back to the words, to documents with attention back to the sentences, to a label with attention back to the documents, right? And so all you get, right, clinicians don't label documents. Clinicians label or assess individuals. Right, so this is something he adapted. It had been introduced originally for sentiment analysis into this domain. And in addition, as a result of this, it enables you to get sentence and word level attention. This is a mock-up of the kind of thing that a clinician might look at if they were monitoring a population of individuals. And you can see the top-ranked individual. By the way, the asterisks there are for anonymization. One of the best practices for work in social media mental health research is to obfuscate because the data are sensitive, and you don't want people copy pasting and then just doing a Google search and going back and seeing who posted it. But you can see this top individual and the highlighting here, we've successfully identified, right, using this attention network way of doing credit assignment, not only individuals at risk and ranking them reasonably, but also which sentences, which posts are the ones that you should look at as the important evidence, and even within which words are the things that one should highlight. Now, in order to evaluate this, and I'm not going to go into detail on this at all, the thing to think about is the fact that evaluations are an abstraction of a real-world problem setting. I'll say that again. We often think, oh, it's just evaluation. I have a metric, precision, recall, whatever it is. No, those are formalizations of something you care about, right? In this case, we don't just care about relevant, irrelevant, like you do in information retrieval, a binary label sort of thing. We want all and only the individuals. The real world then what problem setting involves clinicians trying to deal with this population of individuals. And therefore, what Han did was develop an evaluation framework that took advantage of simulating the clinician's process of being presented with a set of individuals, where each individual, there was a set of documents that might be indicative, like you saw on the previous slide. And then effectively measuring not some kind of accuracy measure per se, but time. Within a given time budget, how successfully can you identify the individuals who are most severely at risk? The result that I'll point you at here, just to illustrate, is in the middle column here, where if you have a time budget of 3 hours in his simulated evaluation setting, if you use a baseline of, say, logistic regression, that's in the middle here, and you just go backward in time from the present time point, you would identify in his simulation 11.7 individuals who are truly at risk. If you use this hierarchical attention network approach for doing essentially your process, you're identifying more individuals, statistically significantly more. And this is an indication, a direction. And the most important point is that it's an important thing to do, not just think of classifying, but prioritizing. Since I'm just about out of time, I'm not going to go through this last bit. If people are interested in the questions, we can talk about it. This is a multi-armed bandit approach to optimizing the available resources in order, again, to identify who requires clinical attention most significantly. That's with my colleague, John Dickerson, who is a machine learning specialist here at the University of Maryland, and Deanna Kelly at the School of Medicine, and Carol S.B. Wilson in the engineering department. So here are the takeaways. First, mental health care is healthcare. A lot of people don't realize when they think about healthcare is a big issue with health. Mental health is right up there with any other form of health you could be thinking about. Second, language contains crucial signal. If you look at an ROC curve in Coppersmith's experiment, there is real value, predictive value in this that is different from what clinicians do. And this kind of algorithmic and machine learning approach has enormous potential. Third, we need prioritization, not just to label people, but not just to label them, but to go and look at the then what problem, where you have populations and you need to figure out how to allocate resources. And finally, when we're talking about sharing data, this notion of a data enclave where you bring people to the data rather than the other way around is, I think, a very important piece of the solution space. And with that, I will say thank you, acknowledge my collaborators, acknowledge my support, and again, acknowledge you and say thank you very much for the invitation. And I am very happy if we have time to take questions.
Thank you, Professor Resnick. That was really a very fascinating and contextual talk. And let us have some questions from the audience, if there are any.
I know you, for you get dinner coming up, so I know it's on the list.
If you have questions, you can raise your hand or just ask. Pushpak, is that you?
Yeah. May I ask a question?
Yeah, sure.
Professor Resnick, wonderful talk. So could you explain the ROC curve once again?
Sure. Are you able to see my PowerPoint?
Yes, I'm able to see.
Okay, so let me run back to the ROC curve. Here it is.
Yeah.
So what Coppersmith did was train binary classifiers where the variable that you were predicting is a binary variable. Did this person make a suicide attempt or not? And this was ground truth, actual data from individuals who had made attempts. And what he did was he trained different models on language in social media. I believe this included private Facebook posts, which is a whole interesting story about obtaining that kind of data. But that's where data donation comes in, right? Where people are consenting even to private data being done. He trained classifiers. If this was the time point of an attempt or the equivalent time point for a control who did not make an attempt, one classifier would only use the data up to 1 month before, another would use data 2 months before, 3 months before, and so forth. And so you'd build a binary classifier, and then you can evaluate misses and false positives, and say, you know, what are the trade-offs here? I mean, precision recall, sensitivity, specificity, misses, false positives. These are all flavors of the same form of evaluation, the trade-off. And so what this curve is showing you is for each classifier in a different color, if you were to look across the range of varying how much it's going to emphasize recall over precision or vice versa, across that entire range, what are its true positive rate and its false alarm rate? So if you look at, and of course, therefore, the diagonal is random. It's a random choice between a yes or a no. Does that clarify?
Yes. Thank you very much.
So any other questions?
Yeah.
Yeah, please.
Dipti ji.
Yeah, your voice is very faded. I am having difficulty in hearing it clearly. I don't know if it is clear to others.
Hello.
Yeah, it's better now.
Better.
Okay.
Thank
Okay.
you. Yeah.
Okay, Philip, nice thank you from, this is Shivaji. I think the program chair for this icon. I was in contact with you, basically. You responded to my invite. And so when you gave the choice of political aspect and the mental health, so I agreed to this mental health issue. I pointed out because this is so much useful in the coming days, that is in the current situation. So I have some bit of observation. That is the kind of work that you have displayed here. It focuses on the language that is in the social media or other kind of posts, say what kind of reflections are coming out of the mental health. That is, we are trying to do a mental map of the person. Now, besides this, say whether the temporal aspect, that is, if we see the social media post, for example, of a person spread over a number of, say, the time period. So how the mental map basically changes. So whether some sort of study has been done on that part. And the other issues like, say, the same language, but it may be the source of the area, that is maybe from the country, the society, the cultural aspect. That is whether the research, say, has been carried on in these areas as well, in these dimensions.
Yeah, thank you for the question. Thank you again so much for the invitation. It's worth mentioning, I mean, I'm a language person, so I focus on language. It is, in fact, worth mentioning that regardless of the things that you're talking about, there are other signals that people look at. So time of day for social media postings, people are monitoring using Fitbit devices and measuring things like heart rate and breathing and all sorts of stuff. So I have a particular slice of the problem. People do acoustic analysis of people's speech as opposed to the content of their speech, for example. You asked about two things. The first is the temporal side. Yes, absolutely. This is a very important thing, and people have, in fact, looked at temporal patterns. For example, people have done affect analysis or emotion analysis, looking at prediction or assessments, automatic assessments of emotion along the lines of sentiment analysis, leading up to, for example, a suicide attempt. And one of the very interesting things is that you will in fact find that people's affect and state of anxiety and so forth can decrease just before a suicide attempt, which is clinically most likely to reflect the fact that their agitation has been replaced by a decision. They've decided something. And so therefore, that is a temporal signal, right? Not just a point in time, but a high energy level and agitation, anxiety, and so forth. The people who are most at risk for suicide are not the people who are so depressed they can't get out of bed. If they're so depressed they can't get out of bed, then they're less likely to actually act. The people who are most at risk are variations of what is called a mixed state depression, where depression is combined with a high energy level, right? And so you're absolutely right. The temporal aspect of this, that's one example of the temporal aspect that I know people have studied. There are results, some results about that, I believe obtained by Coppersmith and colleagues. I can probably find the reference if you email me. The other question you asked had to do with, I'm sorry, I jotted down social. Tell me the second part of the question that you asked also.
I think you jotted it down correctly. That is the social aspect. For example, the kind of say the bonding with the family, because different societies in the world. So the relationship of a person with the family members, how closely they are related, how they can share. So whether that sort of classification people do.
Yeah, so that's enormously important. And so that has been done in the traditional literature, looking at risk factors, right? So social isolation, for example, being well known as a risk factor. And that includes isolating oneself from family would be, and friends would be an example of that. As an interesting thing that I've been done, not yet published, it's the flip side of this, which is not risk factors, but protective factors. And so it's an interesting just source of data that kind of dropped into one's lap. On Reddit, now over a year ago, I think, somebody posted a general query on the Ask Me Anything subreddit that said, formerly suicidal Redditors, please write and tell me what got you through the dark times. So it's essentially, the phrasing is not exact, but it's pretty close. And so they were inviting people who had been suicidal to say why they didn't wind up ending their lives. And this question got 16,000 responses over the next 24 hours. And so what I did was I did a topic model on those 16,000 responses, and then used a human protocol to refine and curate that topic model with 2 suicide prevention experts to look at what categories or themes emerge in people who did not end their lives, which you could interpret as protective factors. And this is how it's related to your question. Family-related things and social-related things were absolutely showing up there as being quite important. One big concern, for example, was financial burden on their family, right? Either because they were supporting the family or because they were worried, for example, their family couldn't afford a funeral, right? So there's one theme having to do with the financial burden, right? Another, which is related to family, is pets, dogs, cats, and worrying about who was going to take care of their pets was another thing. Another thing that was very surprising that you just would not have imagined was another protective, a reason that people said that they did not wind up killing themselves was they wanted to see how Game of Thrones turned out, or the next issue of a video game they were waiting for. They held on because they were waiting for. They got through the period because they were looking forward to something, typically in new media, whether it was on YouTube or a video game, or a Netflix episode and so forth. So the short version of what I'm saying is, yes, the social aspect, things like family and so forth, are absolutely part of both the traditional literature, and they show up when you are looking at these kinds of machine learning approaches. Yes.
Thank you. So any other question?
Thank you. I think
there is
Deepti,
one in the chat.
chat box. Yeah.
Sorry, Shivaji. You.
No. Okay, fine. On the chat box, there is a question.
Yeah, there is a question in the chat box by Musica Supriya. She wants to know that if there is any data set for mental health, this thing, if you can kind of mention and help with that.
I love the question because it implies somebody might actually be interested in working on this who hadn't been doing it before. So thank you. It's wonderful. Yes, there are many data sets out. Well, many is a little bit strong. I mentioned this sort of data crisis out there, but yes, there are data sets. Probably the first thing that I would point you to is, in fact, if I can find it, the section of the talk that says progress depends on data. If you go look for the data set that I created, this is a data set of Reddit posts. We have a large number of individuals and their social media posts. And for a small subset of them that you can use as a test or validation set, we have those expert assigned risk ratings. You can just Google University of Maryland Reddit suicidality data set. This is something that I am able to distribute to other researchers. There is a process of applying for it. And I work with the American Association of Suicidology. We have a little committee that reviews applications. It's a very easy application. The only thing that might be different from something you've done before is obtaining an ethical review of some kind. Here in the US, we have something called institutional review boards, who are tasked with reviewing human subjects research and making sure that it's an ethical protocol. Hopefully at your university, you have something similar. But please write to me. Well, first go to the data, the website, look at the application process. If you have questions, let me know. And then I'm very happy to expedite. mention that you are where you are and you heard me give this talk. I would try to be quick anyway, but I would absolutely try to expedite the processing of approval to get you the data set if you mention this. And you can also write to me and ask about, there are some other data sets, but again, because of the privacy issues and concerns about privacy, they're not as common as data sets in other research areas.
Thank you.
Thank you.
Any other question? Professor Resnick, I was just curious, you mentioned about that classification alone doesn't help because one has to, as a clinician also needs to identify cases which need prior attention or need immediate attention to some cases which can wait. But in that thing, and I'm completely not in the field at all, neither a psychologist nor working in this area in NLP, but I was curious that clinicians, there must be different kind of disorders or issues that individuals would have within depression. And the clinician may want to categorize them in different categories to do the appropriate therapy or treatment accordingly. So do we get any cues of that sort from language data? Whether it would be possible to categorize them on language data?
Yeah, so first I should point out that the work that I'm describing here, I have not yet translated any of the research that I'm talking about here into practice. And in fact, much of this research has not yet been translated into practice. Here in the United States, and I don't know if it's true elsewhere, there is an entire flurry of startup companies that are claiming to be able to analyze data from people in relation to mental health. I'm a little bit skeptical about most of them, but people realize this is a problem. And of course, if you realize there's a problem, then people realize, oh, there may be money to be made. And so, they kind of get into this. So, but I do want to emphasize a lot of the work that I'm doing is intended to lead to deployment, but none of my work here has been deployed yet. You asked about categories, finer grained categories, for example, rather than a binary label of some kind. The answer to that is mixed. So on the one hand, clinicians tend to be guided by what's called the DSM, the Diagnostic and Statistical Manual. And the DSM is effectively a set of yes and no criteria for whether a diagnosis is applicable. So it's like check boxes. Here's column A, and if they have 2 of these, and column B they have 1 of those, then yes, then they qualify for a major depression. That's the way that clinicians formally apply diagnoses. There is, in fact, an increasing recognition, and I actually wish my wife Rebecca were here because we've given talks on this together. There is, in fact, an increasing recognition that kind of yes/no DSM-like categorization is a poor fit for the actual facts on the ground. And instead, there are people who are trying to develop more flexible categorization schemes. So that instead of looking at you have these 2 things and these 2 things, and that's a yes, it's depression. Instead, you look at, for example, symptom categories, right? Like anxiety or social avoidance, or, you can imagine, I'm going like this, by the way, because the slide I have on this involves a Venn diagram of these different things. And then different parts of this Venn diagram tend to be associated with particular conditions. And so there is a categorization taking place. People are developing ontologies. There's a project called HITOP, HITOP, in the US, based at, I think, Stony Brook University. And they are developing something as an alternative to the DSM as a category, as a way of developing sort of more relevant categories and viewing the problem not as a problem of a diagnosis, but as a combination of presence in different symptom categories, if you will. And that more flexible notion of category is, I think, going to become important. Finally, I'll mention, and not to go on too long, but there is also a different sense of categories that you could also be referring to, which are things like demographic categories, right? Is this a kid having problems at school? Is this a whatever? Those things play into what clinicians do all the time. And the clinical white, social media, I believe, is a way of keying into relevant factors that they would not necessarily normally see. Like, a typical psychiatrist spends 15 minutes at a session with an individual, managing their medication. That's what psychiatrists do, at least in this country, most of the time. So getting a sense that their specific problem is that they're being alienated from their social group at school, which might be the kind of categorization you're talking about, right? That's the sort of thing that this language-based evidence can bring into the foreground and hopefully put right in front of the clinician on the equivalent of a clipboard, right? So that they know something that they didn't know otherwise. So anyway, I could go on, but thank you. That's a great question.
So thank you so much, Professor Resnick. And since we are running out of time, so I must thank you for this wonderful, wonderful talk. And let us hope that some more people in India also start working on this very, very, I would say, contextual and critical problem.
I would encourage you, thank you so much. I would encourage people to look for the workshop on computational linguistics and clinical psychology, or CL Psych, which we've helped create as a forum to bring clinicians and technologists together. That workshop will have a paper deadline coming up this spring, and will take place in, I believe, hybrid, remote, and in person in Seattle during the summer. So thank you again so very much for your attention. I really appreciate it.
Thank you.
Thank you. Thank you, Philip.
So over to NIT Silchar.
Yeah. But thank you, Dipti ji.
So we end the session.
Yeah. Thank you.
Thank you, everyone.
Thank you very much. Everybody stay
Thank
well.
you, the audience. Yes. Thank you.
Bye-bye.
Bye-bye.
Okay, so that was a very nice session. Now we have Professor Louis-Philippe Morency already joining the session. We will be starting the session soon. Before that, we want to give a brief introduction of Professor Louis-Philippe Morency. Okay, so Louis-Philippe Morency is currently a tenure track faculty at...
You are not audible, Doran.
Okay. Am I audible? Hello? Hello?
No, not very audible.
But it is low.
Am I audible now?
Little better.
Okay, fine. Here it goes. Louis-Philippe Morency is currently a tenured track faculty at CMU Language Technology Institute, where he lead the multimodal communication and machine learning laboratory, Multicom Lab. He was previously research faculty at USC Computer Science Department. He received PhD in computer science from MIT Computer Science and Artificial Intelligence Laboratory. His research focuses on building the computational foundations to enable computers with the abilities to analyze, recognize, and predict subtle human communication behaviors during social interactions. Central to his research effort is the technical challenge of multimodal machine learning, mathematical foundation to study heterogeneous multimodal data, and the contingency often found between modalities. This multidisciplinary research topic overlaps the field of multimodal interaction, social psychology, computer vision, machine learning, and artificial intelligence, and has many applications in areas as diverse as medicine, robotics, and education. So the talk title is Multimodal AI, Understanding Human Behaviors. Before we start this talk, we want to felicitate Professor Louis-Philippe Morency with traditional Japi and Gamocha in a virtual mode. Yes.
Thank you.
Yes. I just want to, can you please unshare your,
Oh, yeah.
Yeah, and then I will just, okay, so here it goes. We have traditional Japi from the state of Assam to felicitate a guest, and also traditional Gamocha with a flower bouquet.
Thank you very much. That's really great.
Okay, so now this particular session will be shared by Professor Sibaji Banopadai. And now the stage is yours, Professor Louis-Philippe Morency.
Okay.
Professor Morency.
Yes.
Welcome to India. In fact, a few months ago, when we are organizing the multimodal workshop at RNLP, we also got in touch with you. You were busy at that time. So from that point onwards, we made it a point to invite you, to listen to you. And so this is the right time, I think, that is, because multimodality is something which is quite in nature. So nature guides multimodality and interactions multimodality. So we are waiting to listen to you. Thank you. Please.
Thank you so much. Really, really appreciate the invitation. Sorry that I can't be in person. ICMI 2022 is planned in India, so maybe I'm too optimistic, but I'm still hoping to visit at that point. But yeah, thank you again for the invitation. I am effectively Louis Philippe, but people call me LP. That became my name in the US. I'm leading a lab of great students and researchers, all passionate about multimodal. And today I will present some of our work. I decided to add a few slides on mental health just because I love Philip's talk so much and just wanted to give the multimodal view of mental health, because that's a very important aspect as well that he himself mentioned. But the core of my talk is on multimodal AI. That's what I will talk, specifically multimodal machine learning. We're living in a multimodal world. We always lived in a multimodal world, but we have now access to technologies that are becoming more and more interactive through different set of modalities than we used to have before. And the last few years have enhanced that, the aspect of video conferencing being one of these. So it becomes very important to study the multimodal. And when I personally talk about multimodal, in our group, we focus on three modalities, 3V of communication: verbal, vocal, and visual. Verbal, the language, both the lexical aspect and the semantic aspect, how you phrase sentences, but also the pragmatic aspect, which is very important, especially face-to-face interaction. What is the intent behind the words? And then when we look at the acoustic and vocal, there's at least two aspects. There's the prosody when I'm speaking, but also the vocal expression when I'm not speaking, like a laughter, a pause filler, or a moan. And then there's the visual. I'm someone who moves a lot their hand. So you have beat gestures with your arms. You have head nod, head shake, emphasis. There's also the whole body language, body posture. And when it's face to face, you have the proxemics, the eye gaze. If you ask me, one of the cues that's very important in communication is eye contact and eye gaze. And that shows also cognitive and definitely facial expression. So when I think of multimodal AI, there's at least one aspect of multimodal AI, which is multimodal perception. How do I integrate verbal, vocal, and visual to infer something larger than this, something about emotion, social signals, and I will also discuss a little bit the mental health. So if you want and are as passionate as me or want to learn more about it, we've done a lot of work on this over the years, but specifically we try to do our best to create a survey that is kind of a mini tutorial on multimodal AI that highlights 5 technical challenges that had been kind of understudied in typical machine learning. And if you really want to push it further, there's a 30 hours a course that we put on YouTube with this. But when we look at multimodal, there's at least 2 core challenges. The idea of bringing together information like fusion, and there's also the concept of translating between modalities. But both of these requires representation and alignment. Representation, which in the last 10 years has become a core aspect of AI and machine learning. But one aspect that's very specific to multimodal is the alignment. How do we align modalities together? How do we synchronize? And one thing I will present today is also the fact that if you want to do sometimes things like few-shot learning or zero-shot learning, you can use another modality to help you into your unimodal problem. You can have another modality help you at least at training time. So this is the core of multimodal, but I'm going to go into talk today, and I've been giving talks on this, and we do a lot of research. I will give you some highlight of this, but I really want to emphasize that multimodal is becoming a reality. So we need to think about what are the real world challenges of multimodal. When you think about education, thinking about putting this technology in vehicles or even in healthcare, and that's why I wanted to emphasize a little bit the healthcare, because Philip's talk was great in that sense and emphasizing the importance of healthcare. And although language is a key aspect of this, when we studied this, that's been more than 10 years, we studied mental health from a multimodal perspective. We identified very important cues from language, as expected, but also from the voice and also from the facial expression. And I just wanted to give you a few of these, but we studied suicidal ideation, depression, psychosis, most recently with McLean Hospital, and we're getting closer to get those technologies in real hospitals, especially with McLean Hospital at Harvard. So, but when you think of these mental health issues like depression, you probably also think of nonverbal, and one of them will be most likely smile. You will think that people who are depressed, they smile less often. That will be kind of a preemption. But what was interesting in our research is that the number of smile was similar between depressed and non-depressed. And the real difference was the smile dynamic. The depressed patient, shorter smile and less amplitude. Very interesting aspect. So go beyond just counting smiles or counting words. We need to look at the dynamic of it, which goes with the question of temporal aspect. Another example, I have three of them here. Another example is PTSD. And you think like negative expression will go with someone with a strong trauma. Maybe it's because of some background experience, maybe even military. And what was interesting is like the difference, like are people who are with PTSD syndrome more negative expression than the non-PTSD. Again, the difference was not statistical between the two. But if you split it and look at this and analyze men and women, you get this very interesting aspect. Men with PTSD, more negative expression. Women with PTSD, less negative expression. This is very interesting. Now, we have to acknowledge that this was at one location. It was in Los Angeles. And so it probably has a cultural aspect to it, but it brings a lot of interesting research questions that needs to continue looking at. One hypothesis is that people in America, in some other Western country, there's this notion that men are allowed to show expression, and especially negative expression, but women are kind of expected to maybe show more of a positive face. And maybe because of that, then we see this effect. That's a hypothesis. I want to just show one last example because we talk about societal and non-societal, and I think language, as we know, has been very important in like identifying society versus non-society, and also about prioritizing, as was presenting in the previous talk. I would like also to go a step further and look at repeaters, because this is data we had this was with the Children's Hospital in Cincinnati. And this was like teenagers going to the emergency room. And there, the doctor has to make that very hard decision. Do I keep them? Do I give them medication? Do I send them back home? This is a very, very hard decision. And so we want to be able to build technology that not only at that point look at behavior markers for now, but also try to even predict like the future outcome, which is very challenging, but at least you would like to give more information to the doctor. You're never going to do the decision for them because we're looking at decision support tools, but you like to help in that sense. And there, what was really interesting is because we look at and contacted 30 days later, I think the original cohort was relatively small, was 40 teenagers, and the follow-up study was 300 teenagers. And there, the voice was important. It was the tenseness in the voice, but it went counterintuitively. Like people with very tense, almost angry, they were the less likely to repeat. Most likely, they just wanted help. There was a cry for help. The people with a more breathy voice, they were the more likely. They maybe made their mind, they were go. So when we look at this, we ask yourself, first, we want to share this information with the doctor. And personally, we believe in decision support tools, which means that the doctor is always in the loop. And so you also ask yourself, can I integrate these behavior markers to try to give better tools to the doctors? And what we did is integrate all of these and try to see, can we get close to what you will expect from a more clinical assessment. And what you will see here is that this is to look at distress, which is in our case either depression or PTSD. And in blue are the assessment, the clinical assessment. In the pink one, we see the one that have very strong assessment based on these clinical measures. And in green, by integrating all of this together, you get this assessment, this multimodal assessment of distress. And you don't want to be in this part, missing people, and you don't want to be in this part, over-diagnosing or over-assessment. So when you look at those very critical applications, then you have to ask yourself, it's no more about just multimodal fusion. There are many very important real-world challenges that we need to take into consideration. Efficiency, like you want to be able to make your algorithm work fast, probably, and also maybe with less memory, maybe so it runs on a cell phone. It needs to be very robust. Maybe a lot of time you have missing data. You don't see the person, or you don't hear as well, but you still want to be able to do some aspect of prediction. And diversity. We want to go beyond just like data set. A lot of them, unfortunately, are often like Caucasian English speakers. You need to go way beyond that. You need to look at trust. It's very important at two aspects. One is to build something trustworthy, meaning AI that is interpretable, explainable, that is robust at the same time. But also you need something that's human trusted, that because it can be trustworthy, but the human may still not trust it because of other aspects. Some of it can be emotional and social. And finally, we need to be aware of privacy, because these are very like identifiable data. So today I'm going to emphasize a subset of that. I will primarily talk about multimodal representation and fusion, and introducing you to the concept of co-learning that you may or may not have studied before. And then in the second part, last part of the talk, we'll talk about how do I translate from one modality to another, maybe to create a virtual character, a virtual human, or maybe a robot. But in all of these, I will emphasize the real world challenges that are important in this. And so the first most important aspect, especially being emphasized in the last 10 years in machine learning and AI, is the representation. You want to learn how to represent and summarize multimodal data in a way that exploits the complementarity and also the redundancy, especially important the redundancy when you look at robustness. And so to study this, you want to be able to, as one possible goal is to be able to learn a joint space, a space where you speak some very positive words, or you show positive expression, that you have it in your tone of voice, that they all come together. And there's been many different approaches. I want to give you a first mini tutorial on like some of the core challenges in multimodal representation. And then I'm going to bring two very important extensions, one about robustness and another about co-learning. That's what for the representation. So the idea of representation, of joint representation is that you have maybe some unimodal representation, and when you perform it in a supervised way, when you have labeled, I'm going to talk later how to do it in a self-supervised way, But when you have labels, then your goal can be stated as bringing together into a joint space all of these different modalities. And many people do this exact approach, which will be called in our world, I will call early fusion. It means concatenate all of them and then let your algorithm learn magically without any kind of expert knowledge, learn from data how to merge it. And if you have many data, like a huge amount of data, it's going to work. It's likely to work, likely. But if you have limited resources, then you often want to take advantage of theories of multimodals and integrate that into your model. And there are some well-established concepts in multimodal. The first one is about cross-modal interaction. It says that when you have 3 or more modalities, there are many ways these modalities can interact. First, they can interact with each other, with itself. So we know from a lot of great work in language that words are often best represented when they're contextualized with each other. And that's been seen with many recent architectures, self-attention and transformers. And we see some extension to that in visual and acoustic domain. But there are many times where you have interaction between 2 modalities, not 3 already, but 2 direct one, where you say something and you emphasize it with your arm gesture. And sometimes, and I will say a lot less often, there's also trimodal interaction, but there may be less often, but they're often the ones that are the most important because people, when they take and use all 3 modalities to imagine one concept, that often means that it needs to be emphasized and it's a lot more important. So although most of the time may be unimodal and bimodal, trimodal, when they happen, will be a lot more important often. So how can I build a representation that takes that theoretical problem and integrate it in my representation? And the idea is to learn a representation. Let's start with just 2 modalities. So modalities, 2 modalities, then I want to be sure that I have unimodal and bimodal in it. And there's a simple way, which will be a tensor. You create a tensor, in this case, that integrates both unimodal and bimodal. And that tensor can be created nicely by just adding this little 1 in your representation. And what is great is it generalizes. So with 3 or more modalities, you get the same thing. So you can create these tensors. And it's not just the cross product, but it's the cross product with the 1 which just really makes us. So I just wanted to give this small, simple example because this turned out to outperform by a good margin these early fusion. But in the real world, you may not want to create this whole big thing because then memory may become interactable. So that's where comes the real world aspect, where you want to do it in an efficient way. And nicely is that there's low rank decomposition approximation that can be done that to speed up this. So without really completely creating the tensor, mathematically you can get a formulation of that same tensor, but it stays factorized instead of being brought together. And you can still do same performance, and in some cases, in fact, it turned out to perform even better than the full tensor. And you're probably wondering, hey, I've not even yet talked about transformers. How can I be at an NLP conference and not talk about transformers? So yes, it is this kind of idea, this theory of multimodal can also be integrated in a self-attention model. If I am modeling a video and at every timestamp, like it could be at every utterance, I have a representation of what has been said. I have the gestures and how it has been said, and I have these utterances over time. I may want to be able to contextualize information, and I want to contextualize between modality and temporally. And I want to contextualize this with the idea that I know that there's going to be unimodal interaction. I know there's going to be bimodal, and I go trimodal, and I may not have that infinite amount of data that allows me to simply do early fusion. In this case, you want your transformer architecture to analyze that, to say that sometime I'm going to try to just do unimodal for the language, for the vision, and for the acoustic. I'm going to create representation that are bimodal in nature, and I'm going to create representation that are contextualized in a trimodal way. So when I run this to my self-attentions, what I get is really interesting, because now the same dimension of my language representation has been contextualized 3 different ways. It has been contextualized in a trimodal way, which means how is that representation best connected, related to the other modalities and itself. But it also be done in a bimodal and unimodal. The unimodal will be how is that dimension of language related to the other, but how is it also from the other modalities as well, so in a bimodal way. So that's really interesting, because now what you have is the trimodal, bimodal, and unimodal that will then be integrated together. And that gives, in fact, almost human performance level on multimodal sentiment analysis. This was, as of last year, the state of the art in that case, because you bring theory of multimodal. That's why you get such an improvement. There was another trick in this case on the way fusion is happening, but I didn't have time to discuss all the detail. So this is just an example of multimodal representation learning. But I want to go and now talk about real world scenarios. And in real world scenarios, you often have occlusion, missing data, or because of noise, data is unusable. And you want to probably learn those representations in a more self-supervised way or unsupervised way. So how can I do multimodal representation? And either you go with GAN or another approach is VAE, variational autoencoder. Here, we have to think about what is happening when you do a VAE in this kind of scenario. The goal is that the encoder is going to magically take any kind of these data, and in fact, if the data has a different missing pattern, like let's say different part of the image are hidden, it wants to create always the same vector. So if the underneath it is the same, then the latent representation should be the same, so that the decoder can correctly recreate the data without the missing pieces. So you put a lot of pressure on your encoder in this case, because the encoder, any kind of missing pattern, you could have all these different versions of like, oh, this is this that's missing, this is the verbal that's missing, or this is like, all of them should be giving you the same representation. So doing it a one-shot feed forward is very challenging. So we in our group decided to let's try to think differently. I know everybody loves VAE and GAN, but let's try to think differently and go and get rid of the encoder. And this is what my current postdoc and undergrad student did. They worked together. This variational autoencoder. It was a great idea. It's like some of it had been theoretically presented, but now to really make it work was a treat in itself. To the idea that now I will forget about the encoder, give me new data, and I'm going to, at any time I get new data, I'm going to have that iterative process, even at test time. And so there's a little bit of cost in the computation, which I'll come back later in a second. But at any kind of data point, I'm going to try to fit a decoder. And by fitting a decoder, it's 2 ways. I need to optimize the decoder itself. And at the same time, I need to optimizing my latent variable. So I'm both iteratively going to optimize the latent representation and the decoder. So although it comes at possibly a little cost in computation, this is a lot more flexible because now it's no more just a one-step feed forward. Now I'm having this iterative process that allows me to fit more flexibly new data. And what it means, like a VAD, it means that I want, if I have this input image, and I know, let's say that without the missing data, this is where I should be. This I was to encode without the missing data. The VAD, what it does, and during that optimization, it will always start with a random initialization, and then it's going to iteratively move along that space iteratively to get to that best representation that really represented without the missing data. And then you ask yourself, is it robust? And more importantly, for people who worked on robust estimation, it's not just about robust, but robust also with the difference between training and testing time. Because at test time, I may not know what will be the missing rate, like how much of the image. And at training time, I may have a disconnect between my training and missing. But if you want something very robust, it should not depend that I knew at test time what will be the missing rate. And a lot of approaches like VAE only work, that's what you show in green, in the diagonal, they only work if you knew ahead of time what was the missing rate. They don't handle that differences in missing rate. But the VAD, by being iterative, in fact, whatever the training, like it handle a lot of different missing rate at test time. And that was an issue even with GAN. I didn't explain these, but the GAN has the same issue as the VAE in this kind of situation. So this is really exciting. We are very excited about this kind of new architectures, new way of thinking about representation learning. But you have to think about real world cases where efficiency is going to be important. Because these updates, that means at test time, I will need to update at test time. And there's another issue is that each of them are almost done independently. Like if I have two images, these days, I will always like do it separately in this kind of architecture. So to do and help with this, with both of them, we develop what we call relay variational inference. And the idea is a little bit like the idea of creating highways. It's like I will find some natural clustering in my data. The algorithm will automatically learn that. There's no ourselves going to do pre-clustering, but we'll let the algorithm find natural aggregation and structure in the data, and then we will let them create these highways to speed up inference. So the idea is now that each representation will no more just be the representation of each of them, but they're going to be relative to each other, relative to that relay, to that like common point that will then bring them to very quickly bring them to the correct place. And to do that, nicely moving all of them quickly, there is a nice simple change that can be done in the formulation where now the representation for the Z1 for the first image is no more like an independent measure, but it is a related measure related to that relay. So Z1 is no more Z1, but Z1 is really a measure that's related to that. And by changing this formulation for all of them, now we also, and at the same time, reduce the number of parameters, but also will speed up convergence. And so let me show you this in practice on different data sets. This is the classic MNIST, This is Mosey that I showed, which is about sentiment, and we showed on others. I don't quote all of them, but in blue, what you see is a very quick convergence, very much faster convergence than VAD, which was the reason we built it. Our biggest surprise was this even converging faster than VAE as well. So that was really exciting because that was not our original goal. Our goal was just like, okay, let's try to be faster than VAD, but now we ended up being even faster than the VAE as well. So please think about these different way of thinking, but also think about the real world challenges. And now I would like to introduce you to a different way of thinking about multimodal, which we call co-learning, which has been very popular in few-shot learning as an example of that. And there is that I want to learn a representation and language representation. So it's a unimodal problem. At test time, I'm only going to have language. But let's say that I want to look at language representation for spoken language, which now starts having more and more resources, but up to like 5 years ago, had a much less than written language. We had a lot more written language than spoken language. So if I have less resources, then I can ask myself, can I use other modalities that co-occur naturally? It's kind of a cross-modal self-supervision. Can I use this other modality as a way of, as a kind of a supervision? And the idea will be that at training time, I'm going to have a multimodal where nonverbal will come and help me learn my language. You could see it almost, you can see it two ways. You can see it as a regularization because maybe words that don't happen as often in the corpus, but they always co-occur with a facial expression like a smile. Then I can use that knowledge about, oh, smile, I've seen it with other words that were positive. So maybe that word that doesn't happen often is also positive in its nature. So that allows me. And so then you ask yourself, how do I do cross-modal co-learning? One way will be to just do in a supervised way, which means at training time, I train with all three modalities, but at test time, I end up removing one of them. And it turned out to work well, already worked quite well doing it that way. But where we were most interested was to do it in an unsupervised, self-supervised way. And in this case, I don't have a label like I have here during training. So I need to find a new objective function to be able to model it, to optimize it. And one of solution is translation. How can I translate between modalities? And so to give you an example for the bimodal case, and the trimodal is a nice extension of that, is that you will learn a representation in such a way that you can generate the visual representation. So that means that you had videos of people speaking, their transcript from it, and at the same time you have their gesture. And so the translation means going from the language and kind of hallucinating what will be the nonverbal of that person. Now, the trick to make it work turned out that you need a cyclic loss, because you want to be sure that whatever representation you learn here is not only good to predict visual, but is also really good at recreating the original language. And so this is during training, and then at test time, you can get rid of the multimodal, and then you have your nice representation that can be fine-tuned on a task like sentiment. And what was the most surprising is this approach, which used multimodal at training in a very nice and smart way of doing translation, turned out to outperform many different approaches, and many of them use multimodal during testing. In fact, all of them here use multimodal during testing. But that approach that use it in a smart way, multimodal, turned out to nicely improve. I will say, and a big thing is co-learning will not work with all multimodal problem. This problem of sentiment analysis is special in a sense because it was originally even defined but in the world of linguistics. Sentiment analysis come from language originally. It has been extended over the years, studying also how nonverbal co-occur, but it's primarily defined with the concept of subjectivity and opinions and sentiment. So it's primarily like its primary modality is language. So if you know that there you have such case where you have one modality that's primary, then co-learning, as we just presented to you, is going to be very powerful. Now, if your model or your problem is really multimodal, where all three modalities are somewhat equal, then you should not expect that kind of very extreme improvement. So this is the first part of the talk, the main part of the talk, but I have the second part of the talk because now I want to go and not only talk about representation, that I told you about representation, multimodal representation, and talk about robust multimodal with VAD and co-learning, but now I want to go and talk about translation. How can I take language and translate it in nonverbal and maybe animate a virtual character? What is this link between language and gestures? And to do that, I'm really interested, and that's my background. I was at USC for 7 years and really love my time there, where we built technologies that really push the boundary of, and one of them was virtual human. And I will introduce to you Sim Sensei. This was a virtual human for healthcare, where she's talking to the patients and gather information. She's not there to make a judgment or make an assessment, but she's there to gather information like an interviewer. So let her introduce herself.
Hi, I'm Ellie. Thanks for coming in today. I was created to talk to people in a safe and secure environment. I'm not a therapist, but I'm here to learn about people and would love to learn about you. I'll ask a few questions to get us started. And please feel free to tell me anything. Your answers are totally confidential. Are you okay with this?
Yes,
So, how are you doing today?
I'm doing well.
That's good. Where are you from originally?
I'm from Los Angeles.
Oh, I'm from LA myself.
Okay, so this was just a short version of that. What I wanted to emphasize here, this project was a team project. There was almost 30 people over 5 years. It was 4 years. Great collaboration, David Trump, John Gratch, a lot of wonderful people, also on the graphics side, and Stacy Marcella. One of the technical challenge here is how do I animate virtual human? I may know what I want them to say because there's a lot of great theory of dialogue, but how do I animate them to show empathy, to make the person feel comfortable? And so there's many, we did many years of work on this, started as early as 2008, where one of the technical challenge is how then I can go from speech to gesture. And there's work, if you're interested in that, David McNeil for University of Chicago had done wonderful work, Justin Kessel also on this. But we wanted to build things that really integrate all aspects, not just of language, but also of the way we speak into this. And so to do this, and if you're interested in this topic, we built a wonderful data set of more than 250 hours of videos of speakers with their gesture, head and arm gestures, to help us study this very interesting problem of nonverbal grounding. In fact, how do I ground language to the gestures of a person? And not only should I ground language with the gesture, but as the first step, I should also ground language with the acoustic. And you may think, oh, this is solved because this is word alignment. But as we know from transformer architectures, is that the impact of a word can go beyond its like direct neighbors. Like, and the emphasis of a word may have an impact on the other words around it. And you want to be able to measure that and allow the model to also align with other words. So maybe a vocal emphasis may have the impact with a word five words later. So as a building block in that sense, let's just look at this small problem of like, how do I align the impact of vocal emphasis with the words? How do I align it in a way that is not too constrained? And a way to do it will be given a representation of my vocal emphasis, like or prosody, at every time in space, every point in time, and similarly for language, you're going to look at it in a similar aspect of self-attention. You will look at it in a way that you, at the end of the day, allow for the same vocal element, the same vocal element, like the same vocal emphasis, to have an impact much further than just the direct word that you have in a classic word alignment where there's a one-to-one mapping. This kind of soft alignment, I think, is an important aspect, and we'll show it empirically in a second. This soft alignment allows me to create and align language with audio in a soft way. And now how do I generate? The classic approach is to do post generation and use maybe a GAN approach to allow you to make it as realistic as possible. But we are in the real world, and in the real world, there's a large diversity of way of talking, and you should not think that because you saw LP talking, that all French Canadians speak like LP. There's a large diversity, and there's a large diversity of gestures, and sometimes the most interesting gestures are the ones that happen the least often. So let's give an example.
And it's not just the number of companies, it's the variety. You've got Fast Cash, Cash Central, Speedy.
So when you look at this, there is a long tail in the gesture and in the language. Like words that some happen very often will be usually really well modeled, but the most interesting gestures that are beyond just like a simple beat gestures, they may not be modeled, and also the words that don't happen as often may not be as modeled. And since we have a grounding problem, we want to study this long tail. And so how do you model this and do it efficiently? So if you look at the typical distribution of the words and the gestures, you see this natural like long tail that happen. And if you do nothing, then your algorithm is going to focus on the initial subset. A simple way will be to just take this distribution of the data and renormalize it. But what we learn in many machine learning, it's not just about normalizing, is about even going a step further and like push examples that are hard to recognize. And that is an idea of important sampling, is that you're going to focus on the regions that need more training. But you ask yourself, how do I identify those regions that need more training? Because that's what I will reweight my data with. And the nice thing is I want to do it in an efficient way. I don't want to train a separate model to identify what is or what is not hard to train. But if you remember, the architecture we have is a GAN architecture. So we already have a discriminator, and the discriminator can already tell us what it is. And so the intuition is samples that are identified as fake, that are identified as not real, they are the one we should emphasize. They're probably the one that needs more training. And so I will define my probability of being a hard to predict data point as a ratio of the I would directly, it's 1 minus the discriminator because I want to look at the fake, and I would just normalize this by the number, by the real one. And this factor, which we call adversarial importance sampling learning, this approach has no additional parameters because it's already in the GAN, so that in my predictive model, and no computation time, so it improves efficiency. And what it nicely does is, as you do the training, it's going to realize over time where to spend the more and more iteration, more and more emphasis. And so, to give you example of real world now completely generated videos.
moles of C. Now, as this reaction proceeds,
so here's just a simple dyadic gesture, but let me show another example where in this case, the prosody is going to be
this subject coming up, we found out this week that back in June, Trump was on a condolence call to a father of someone who died and apparently was so moved by his plight, he said, I'm going to do what no president's ever done. I'm going to write you a personal check for $25,000.
It's really interesting how the voice, and right away when the voice changes, the gesture changes. And so you can see now that when we look at the gesture and in blue, that was the ground truth distribution. And what we have in purple is a nice approach. And to get there, we needed to do a good alignment between speech and language. And you need to also do a correct weighting of the data. So I wanted to explain to you today example of core technical challenge in multimodal, but also emphasize the real world challenges that we have. And I just wanted to give you 2 examples very quickly on trustworthy and privacy, because one example of trustworthy is I am okay to have an AI system that fails. You're like, what? No, I'm okay. I expect AI system to fail, but I want an AI system that when it fails, it knows that it fails. It just should be aware of its own failure. I think we train algorithms these days with the idea that they should never fail. But that's not how we do as humans. There are moments where we just say, hey, I don't know. I barely just don't know. Don't ask me. I don't have enough evidence. And so instead of training your algorithm to force them to always say, you have to make a prediction, sometimes you may need to add another label that just say, I don't know. But you have to be careful, because if you're just not careful, it's always going to pick that. I mean, we know machine learning, that they always will pick the easy path. So we're going to do like a horse race. You're going to say, if you bet on one of those labels, I may get you some reward, but once in a while you can abstain. But if you abstain too often, then you're never going to get any kind of good. So it's kind of a gambling thing. And the second example I want to share is privacy, because when we look at things like healthcare and look at multimodal fusion on data on a mobile phone to predict something maybe as important as mood or societal ideation, you would when you look at all this data and you're trying to predict mood, when you plot these representation here, you would like to be sure that the identity of the user is no more in the data. And so here is in color, you see is the different people, and what the algorithm end up learning is less about the markers and the behavior and more about the people. But there are ways to do machine learning in such a way that identity is not kept. So if you are as passionate or would like to explore more in multimodal, I invite you to look at this data set called Multibench. that we just released last week. In fact, it was released a little while ago, but it was just presented at NeurIPS last week. It has the 20, and it has a data set, not just a data set, but a toolbox of state-of-the-art fusion algorithm. And we also emphasize the real-world challenges of performance and robustness as well. So thank you very much for your attention for this talk. I welcome your questions for multimodal and robust real world. Thank you very much. I can't hear anyone at this point.
Thank you.
Okay, yeah, hi.
Yeah.
I have a hand raised actually.
Oh yeah, push back, yeah.
Yeah.
Okay,
Uh,
push back. Yeah.
So a really wonderful talk. Great presentation. So now I had a question which is inspired by statistical machine translation, that the alignment, any kind of I think in statistical machine translation, the alignment actually boils down to an expectation maximization based approach. So the sentences are aligned. From there, you go down to phrases and words being aligned through the EM algorithm. Now, in cross-modal alignment also, is it fundamentally a kind of EM algorithm?
So there are many approaches for alignment that I have to. We give I think 3 lectures just on alignment. So there are different ways of solving alignment. EM may be one of them. The most classic way of solving alignment in signal processing is dynamic time warping, where you're warping the alignment. When you use the approach, can you clarify what do you define as alignment? Because there's maybe more than one definition. What are you aligning in your case? Video with language?
So if I take English and French parallel corpora, then say 3 rabbits, Troya Lapa. So 3 goes to Troya, rabbit goes to Lapa. Why? This is because of a maximum likelihood estimate happening, where the hidden variable is the alignment between the words within the sentence, and the parameters are alignment of dictionary words. So you maximize the likelihood of the parallel data.
Okay, I think I understood better. So while I will not argue if you can optimize in an EM way or in other ways, I think the core of the approach that you described is that you hypothesize, and maybe from a generative model perspective, that there is a latent variable that can generate both streams in a sense. And I think this is one way of doing alignment. It is not as popular these days, but I think I personally still love it. I even did a lot of my PhD in graphical models. So I think to think about it as a generative way, I think is very healthy. I think these days, there's also 2 other families of alignments. There's maybe more, but at least 2. One that you talk about generative, but another 2 families. One is cross. I would call it cross alignment, where it's asymmetric. I'm trying to align one stream to the other. So my task is no more to find how the data was generated. It's a little bit of a simpler problem. I only want to know how this streams align to this stream. And some of the early attention models, that's how they were doing when they were applied to machine translation. The first attention paper was the asymmetric attention, I would call, is that it was trying to find how the target language aligns to the source. Now these days we are seeing more and more, like I will say, symmetric alignment with the transformers, because there both of them are trying to be aligned with each other, which is a little bit similar to also dynamic time warping is doing it in a signal, is trying to do this. So I think you have at least 3 families of alignment approaches. One which will be generative, as you mentioned, another one which says, I would say, asymmetric, but it's not. It's more of a. Often it's should see it more in a discriminative way. It's not about finding how the data is generated, but more about how purely the alignment. And inside this, there's the asymmetric and the symmetric one. So I think there are different families. I still love the generative models, but the part about EM, I would not argue. I would be happy to have an offline discussion if it is, but I think there's at least those 3 families. Yeah. Does it answer the question?
Yeah, partially, but you didn't answer what you do for cross-modal alignment. What are you doing?
That's the exact same thing. Okay. Oh, it's exactly the same thing. So you can do the 3 same family in the cross-modal. So for you could look at it in a generative way, which I think VAD, variational autodecoder, is can be seen a little bit like the EM approach you mentioned. You have a latent representation that really generates my data. That's a little bit VAD also. And all of the alignment will be in that generation that you happen, which could be to just in a graphical model, just very simple, just a linear or slight one, but it could be also highly complex, nonlinear and temporal. The same way you can do those other 2 families. We talk about machine translation, like target and source, but it could be also that the source is an image and I'm trying to caption that image. So my target output is language. And so in that kind, you can do asymmetric. So that means that I will do my best in finding how language align with the image, or you can do it symmetric, where I just going to put my language and my image together. And that's what the original visual BERT was doing. And now there's these hybrid, which are becoming very popular, Vilbert and the Unitor and all the others, is that what they are doing, they look like a symmetric, like meaning like I'm doing well, but in reality, what they do is 2 different cross. So they're looking how language cross with the attend with the visual, and how the language cross attend with this with the image. So they look like when you look them in a pure system person, they look like they're doing both at the same time, like visual BERT, when in reality they're just solving 2 different problems and kind of alternating and Paga in reality doing it at the same time, but it's at the end of the 2 cross. Like, so these are like the family that I will say: generative, asymmetric alignment, symmetric alignment, and this kind of hybrid between asymmetric and symmetric. Yeah.
Okay, thank you.
Yeah.
Okay, so any further questions?
Sir, I have one question.
Okay.
Now, my question is on this cross-model concept. The cross-model is effective on similar language or dissimilar language. I'm just extending the Pushpak sir question, because that which one is more effective, similar language and different language pair?
Oh, sorry, I don't think I understood the question. You're saying what is more efficient, similar language or different language? Is it what you're asking?
Yes, sir. Yes, sir.
For what purpose?
For text-to-text translation, machine translation.
So in machine translation, are you
my
saying?
my in-depth question is
Yeah.
suppose if we targeting if we encoding word to word, Okay, so the target maybe target language is confused if source and target are very different, like Arabic and English, completely different structure and various issues are there. So in that case, the phrase encoding is good, or what encoding is good. Am I clear, sir?
Let me try to paraphrase just to be sure that you're saying that when the nature of the languages are very different in their root, possibly then there will be a lot of different structure. What is a good way of measuring or modeling such disparity or heterogeneity between the language using either multimodal approaches or other approaches? Did I paraphrase correctly?
Yes, the cross modeling. That's cross model one.
Cross modal, because but what
Well,
you
that
described doesn't have multiple modality.
means cross lingual model. That cross lingual model.
Okay, good. Okay, then I understood. So yeah, thank you. Sorry for the paraphrasing, but that's a good thing to do, by the way. I always do it to my student. Paraphrasing is the best way to move forward. Yeah, so multimodal machine learning, if you ask me, is about the science of heterogeneous data. The science of heterogeneous data. That's what I believe. And what do we mean by heterogeneity? Is that there is a difference in the modality. There's what makes heterogeneous modality is that they are represented differently, that they have a different internal structure, that they have maybe different noise models. Like all of these, they have maybe temporal dynamic, different temporal structure. So all of these makes it a multimodal problem. So if I understood the question correctly, when you do machine translation and both languages are Latin, let's say, then yes, it's a hard problem, but they're both in my book, although they are different languages, they're a lot more homogeneous then you would say maybe translating English with Mandarin or English with other languages, because they're a lot more heterogeneous. And there, when you do these, that's where multimodal comes in, because when it's a lot harder to find one joint space for both language or both modalities. When two of them are very homogeneous, getting the approach of joint space works really well, or has more chance of working. Joint space has more chance of working when you have very homogeneous language or homogeneous modalities. But when they're very different, that their granularity, the way they're structured, all of this are different, then they're different to each other. So forcing it into one joint space is a lot more challenging. And that's why we see more and more what we call coordinated representation. You're no more forcing everything in a joint space. Instead, you acknowledge that the two spaces are different, and so instead of forcing them, you're going to keep them separate, but kind of contextualize them. And a lot of transformer approaches do this. They don't force them to be in the same space, but they're slowly coordinating them. And I think there's extension of that will be great. And we see already that we call them factorized representation. So not only will I will have coordinated, but I will also acknowledge there's a subset of it that is kind of joint. So it's kind of a hybrid. There's something specific to each language, and there's something that's common to both languages. And I think we see a little bit of that. Maybe we see it in multimodal more, but in machine translation you see a little bit, but I don't think we see it as much. But I think these only happen when you have very heterogeneous language. Heterogeneous in the sense that representation is very different. So So this is the way I see it, is like there's a really nice link between machine translation and multimodal. I must say my office is right next to Graham Newbig's office, so we talk very often about these things.
Thank you, sir. Thank you, sir.
Thank you.
Thank you, sir.
Whether a fusion-based framework for hand gesture recognition using some image put modality may be called multimodal fusion. Okay, we use the term multimodal because they come from often different sources, different modality, and so there's the concept of raw modality, and then there's the concept of abstract modality. So an image will be closer to a raw modality, but often you go from it and start abstracting it. So a skeleton is an abstraction from the raw modality. So it still can be called a modality, but it's a more abstracted modality. If you go really far, you're going to get to a point where the modality is really just like a label, like a label of like, is it a person or a face or something? This is very, very abstracted. At that point, modalities are a lot more homogeneous. But when you go more and more raw, you're a lot more heterogeneous. And I will say a lot of multimodal is the most helpful when they are heterogeneous. But we're still going to call it multimodal, but it's a lot less of a heterogeneous problem. That's one concept to answer your question. The second concept is within a modality, you have multiple view. Like an image, you can look at my hand, you can look at my face, you can look at my mouth. So these are different views. And although they all come from the same modality, if these views have very different dynamic, different noise, different representation, you could see these views as heterogeneous. Although they're from the same modality, they can still be seen as heterogeneous. So if there are heterogeneous views, then yes, all the approaches that I talk about fusion and all this, are going to be helpful in this case, because they're going to bring the heterogeneity and bring it closer. And so that's why I will say, yes, you can have a vision-only problem and still look at it as a multi-view problem where you have heterogeneous views. And there, a lot of the same methodology that we see in multimodal machine learning can help you there.
So, LP, thank you for your nice talk. So we enjoyed, and obviously it started where basically Philip actually completed his talk on multimodal reactions or mental health. So you took up that from that point and multimodal interactions. So we had a nice experience of walking through your slides, your talks also. And we wish that in near future, when you are in India, we'll be able to host you also. Thank you.
It will be a pleasure. It will be a pleasure. Thank you again for the invitation. I really enjoy also questions and discussions. Feel free to reach out to me if you have follow-up, and I will be happy to share a PDF version of my slides if you want later on. Yeah.
Yes, yes, yes. Obviously, we'll be getting back to you regarding the PDF version of the slides, so that more and more kind of multimodal activities actually started by the scholars here.
And thank you for staying so late. I know it's Friday night, so thank you very much about this.
Yeah. Thank you. Thank you. Thank you. Bye.
Bye.
Okay. So today it has come to the end of the first day. of the ICON 2021. Tomorrow we are going to start the session at 9 o'clock. And the session will get over at 12 o'clock. There'll be lunch break from 1:30 and to 2:30. Then we'll have the keynote lecture for titled Human-Centered Natural Language Processing by Professor Radha Mihalsi. And this session will be shared by Professor Rajiv Sangal from IIIT Hyderabad. More details can be found in the website. Thank you very much. Good night. Now we'll go for dinner now. Everyone, please go ahead for the dinner.
एक ऑन कर दीजिए टेस्ट कर टेस्टिंग कर हेलो 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 18th International Conference on Natural Language Processing ICON 2021 no we have to inform them na Hello. May I request all the participants please leave the meeting. Just we are testing that environment. Good night. See you tomorrow.
I think it should work.
Hello. 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 हेलो 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 इसका साउंड कम हो गया अभी हेलो 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 International 18th International Conference on Natural Language Processing ICON 2021 ఎక్కువ వస్తుంది ఏమన్నా క్లారిటీగా ఉందా ఇప్పుడు చెప్పు హలో హలో ఓకే ఓకే వస్తున్నాను నేను వస్తున్నాను నేను అక్కడికి
Manas. So now I will have to catch. The bottles also I will ask.
Hello. Hello. এটো কোন দেখাতে যায় এটো ইনপুট কোনটো হয় এটো সাউন্ড কিবা এটা আছে আচ্ছা ঠিক আছে 1 2 হল এটো হৈছে
তো বন্ধ করো এতিয়া
1 2 হল কিন্তু এটো নচলাকে হৈছে
এটো না লাগে তো জানে
গম না পাও কিয় কাৰণে
कल ऐसे ही सेशन चलता रहेगा ना
हेलो हेलो
keynote तो भी तो होगा और वो भी तो अभी we are closing the meeting